C is a very flexible and well-established programming language, thus making it a mother of all programming language. Many programs, libraries, operating systems are implemented in C. Keeping this in mind, we have come up with this tutorial on data structures and algorithms in C. Before we get started, I want to introduce you to Great Learning Academy, a free initiative by Great Learning where you can access 200 plus courses with 1000 plus hours of free content on trending high demand domains such as data science, machine learning, AI, programming, cloud computing, digital marketing, DevOps, management, and many more absolutely free. Award-winning academicians and leading industry experts design these courses. You can get a free certificate of completion when you enroll and complete these free courses. You can also get access to presentations, code notebooks, datasets, and quiz. We have courses in English and Hindi to give you the best learning experience in language you are comfortable with. Check out the description of this video to access the relevant courses on Great Learning Academy. So what are you waiting for? Register now and start your learning journey today. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new updates on video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on this video, any queries or suggestions, and I will respond to your comments. In this tutorial, we are going to cover all the important data structures and algorithms, and we will also go through the implementation and time and space complexities which are asked in almost all the tech giants. Now let's see what are the things that we are going to cover in this tutorial. First, we are going to talk about data structures. What are data structures? Why do we need data structures? What is a linear and a non-linear data structure? Then we will talk about arrays and how to implement it, how to declare and initialize arrays. Then we are going to talk about linked list, and we will see different operations that can be performed on a linked list, and we will see the implementation of it as well. Then we will talk about stacks and operations associated with it, and we will see both the implementations with arrays as well as using linked list. Then similarly, we will understand queue and we'll do the implementations as well. Then we'll talk about trees, wherein we are going to cover binary tree and binary search tree. Then we will talk about algorithms, and then recursion, in which we will talk about different types of recursion: tail, non-tail, direct, and indirect. Then we'll talk about searching algorithms like linear search and binary search. And finally, we will conclude our tutorial with sorting algorithms. Data structures. Now let's talk about what is data structure and why do we need data structures. So as you can see, this word data and structure is made up of two words: data and structure. So data is nothing but the information that you want to store in a computer. And structure is how you arrange your data in the computers. Now, depending upon these two factors, right, data and structure, that means how you arrange your data in your computers, you can easily calculate time complexity of your problem. And you can also see, are you using any extra memory depending upon the structure that you're using. Now, if you talk about, let me give you an example of one of the data structures, right, and compare it with another. Now, if you talk about arrays, right, it's a data structure, and the way you arrange your data is different from how you store your data when you talk about linked list. In arrays, you have to always store data in a contiguous memory allocations, wherein if you talk about linked list, if chunks of memory are available here and there, you can use those chunks of memory to store the elements in the form of linked list, or you can use linked list at that point. But if 4 bytes are there, 4 bytes are here, and there are different places, still you can use linked list. But that is not the case in arrays. You need contiguous memory allocation. Now, in both of these data structures, one of them is using CPU much more efficiently. It is using the memory much more efficiently, right? So this is one of the basic difference between the data structure between data structures, right? There are n number of data structures available, and different data structures are used for different applications, right? Now, depending upon these factors, right, how you are storing your data in the memory, you can easily calculate what the efficiency of your algorithm, how efficiently you are implementing your algorithm, how efficiently you are doing operations, right? Are you doing operations which are costly, or are you doing operations which takes constant amount of time, right? Are you using your memory efficiently? Are you using your CPU utilization efficiently? Are you using your CPU efficiently? Are you using your memory efficiently? So all these things can be easily deduced from what data structure you are using. So this is the importance of data structures. Now let's talk about, in the next slide, let's talk about what different data structures. Are there any different types of data structures? Yes, there are two different types of data structures. One is a linear data structure and another is a non-linear data structure. Now let's talk about linear data structure. So linear data structures allows us to store data in a sequential manner, like one after the another. Let's talk about this example wherein we are using arrays. It is a linear data structures where one element, let's suppose this is 5, 6, 7, 8, and 9, and one element is stored, and it is stored after the next element, and next element is stored after the next element. So it is stored, all the elements are stored in a sequential manner. Let's suppose this is the address of the memory. Obviously, this will be a hexadecimal number. For simplicity, I'm taking this number as an integer number. Then the next available memory location is 104, then 108, then 112. Okay, so these are the available memory locations, and all the data is arranged in a sequential manner. And every element has two neighbors, right? If you talk about this element, right, it has two neighbors, the left neighbor and the right neighbor. And there are always predefined extremes. Like if you talk about array, there will be a starting index and there will be an ending index. So this is always the case when you talk about linear data structures. So let's talk about another data structure that is there, which is known as linked list, right? Again, it will have a predefined extreme, right? It will have a starting node that is known as the head node, and it will have the tail node, which is used to keep the track of the endpoint. So now let's talk about different types of data structures, right? That is linear data structures, right? The first one is the array, which is obviously the linear data structures, and all the elements are stored in a linear fashion. Now, in this data structures, we can store data in a contiguous memory allocation. That means one after the other. In memory, if wherein you have the scenario where all the memory is occupied and you have chunks of memory. Let's suppose you require 4, 4, 4, and let's suppose you require 4 5s or 20, right? So 20 bytes of memory are required. So you have 8 bytes here and you have 12 bytes here. Can you store the array inside these memory locations? Like let's suppose you are storing 2 elements here and 3 elements here. Can you do it? No, because array require contiguous memory allocation. You cannot store it. Now, what was the drawback? That obviously you cannot store in a contiguous memory allocation. So that is wherein linked list come into picture. Obviously, with array you have a fixed size, right? That is not the case in linked list. The size is variable. That means we have a dynamic size in linked list. Now, if you talk about linked list, if same elements need to be stored in the memory, like these 20 bytes of memory are available, right? 8 bytes are available here and 12 bytes are available here. We can store elements in the linked list, right? So it does not require contiguous memory allocation, right? That was the drawback in linked list. Now stack, if you talk about stack, it follows a principle of what? LIFO, last in, first out. If you have a stack of plates, right? This is an example of stack. Now you have a stack of plates, one piled up over the other. Now, if you want to add an element in the stack, or if you want to remove an element in the stack, you cannot remove any of these elements unless and until you have removed the top, and then one by one you can go down removing one by one these elements, right? Now similarly, you cannot add anywhere, you cannot add here an element because that is not possible. It follows a structure wherein last in is the first out. Let's suppose you want to insert it, you are inserting it here. Now this is the last element that was inserted. Now this will be the first element that is out. Okay, so it follows the principle of LIFO. Now this has restricted how we insert and delete our elements, right? This is the restriction that is there. So this is your stack. Okay, now if you talk about queue, it works in a different manner. Now if you have a queue, let's suppose you are there in a bus station and you want to get tickets, so you are standing in a queue, right? And the person that comes after you will stand behind you. Let's suppose this is me, and the person that comes after me will stand behind me. You will not go in front of the queue. That is not possible, right? Now, and once this person gets his tickets, this will be removed. Now this one will be the first person. Again, this will be removed, this will be the first person, and so on. So there are two pointers that will keep track of the extremes, the front end, the front part and the rear part. Now from the front end, always deletion take place. It's also known as an enqueue operation. We'll talk about these operations later on this course. Okay. So now the deletion will take place from the front and insertion will take place from the rear. So if you want to add an element, you will add it from the rear side. That means this side. You're adding the elements. This is your rear side. Okay. And if you want to delete it, you are deleting it from the front. Let's suppose this is 5, 6, 7, 8, 9, 10. Now you have 11 and 10, and still you have memory locations available. Now you want to add, you will update your rear and it will go there. And if you want to remove, you're going to remove this element and you'll increment your front pointer to this location. So this is how you work around with queue. So obviously with these two there, stack and queue, we can implement these data structures either using arrays or either using linked list. Okay, both of them. So obviously there will be some kind of difference in the way you are implementing it. Obviously with arrays you have fixed size, with linked list you have dynamic size. With arrays you have to store contiguous memory locations, right? And with linked list, even if there is no contiguous memory location, you can still use your memory very efficiently, right? So these are some linear data structures, and we will cover all of these linear data structures in this course. Now let's talk about non-linear data structure. So nonlinear data structure allows arrangement of data in a non-sequential manner. There can be n neighbors for a single element, right? So let's suppose this is a nonlinear data structure. We are talking about binary tree, or we are talking about n array tree. That means there are no restrictions of how many child this root will have, or this element will have, or this node, rather to be specific, this node will have. So there will be n number of childs for this node, right? So there is no restriction. For the next node, there can be two childs. So this is what is written. They can have n numbers. There can be n number of neighbors for a single element. And they do not have predefined extremes. Like we saw in a linear data structure, there were extremes, right? You have a front end, you have a rear end, or you have a top in case of stack, right? And you have, in case of arrays, you have to define a size. In case of linked list, you have a head and a tail. But here you don't have any extremes. There is no extreme in this nonlinear data structure. You can store them as you want, and it is not specific that every node will have extremes, right? So similarly, if you talk about binary trees, now we are restricting our number of childs that each node can have. So let's suppose this is a binary tree. So this node at max can have two childs, one on the left, one on the right. And this node can have at max either zero child, one child, or two child. So at max he can have two children, like in this case. It can be empty, or it can have one left child, or it can have, the next node can have a different right child, a single right child. So this is a binary tree. Now you can even restrict it further by arranging these data in such a way that you always store on the left hand side, you always store the lesser element than the root, and on the right hand side you always store greater elements than the root, right? So these are different variations. Now, let's talk about different types of data structures, nonlinear data structures that are there. So if you talk about binary tree, right, this is a restriction of storing your data in a hierarchical fashion. So you will be storing your data in hierarchical fashion, but every node will have either 0, 1, or 2 nodes, right? It will have left child, it will have a right child, or it can have two. This node can have two children. This node is having two children, right? This node is having zero children. This node is having a right child, thus it has only one child. So this is a binary tree wherein every node at max can have two children, right? Now we can even restrict it further by saying that you can always have, let's suppose the data stored here is 10. So you can always have elements on the left hand side that are greater, that are less than 10. That means you can have any number of elements, but they will be restricted in such a way that all those elements will be less than 10. So this is your BST, binary search tree. And all the elements that are greater than 10, that means 11, 12, 13, 14, will be on the right hand side. And all the elements that are less than 10, right, 5, 6, 7, will be on the left hand side. Now, then we have graphs, right? Again, a hierarchical data structure. Then we have AVL trees. Then we have red black trees. So all of these data structures are non-linear data structures, right? Stop. Now let's talk about our first linear data structure, that is array. So what is an array? It is a linear data structure. That means elements will be stored in a linear fashion, right? Linear fashion. Now, if you talk about array, let's take an example. Now, let's consider that this is how you represent an array in the form of a row, right? And let's suppose it contains elements 1, 2, 3, and 4, right? Now, with every memory location, there will be some address, right? So let's suppose these are the four elements, right? 1, 2, 3, and 4. And these are some addresses. Let's suppose this is 100, and this is 104, this is 108, and this is 112. Now, if you talk about memory, obviously these addresses will be hexadecimal. And when you talk about this particular array, it will be somewhere in the memory with four, or you can say 4 bytes of memory for each integer. Now, if I consider this integer, and let's suppose integer takes 4 bytes. Now, these 4 bytes are available for each integer. Now, this is an integer, right? Now, it takes 4 bytes. Now, the second address will start from 104, right? Because now again this will take 4 bytes, then 108. Again, it will take 4 bytes, then 101, 112, right? So in memory, it will be somewhere around. But the thing that obviously you might be thinking, okay, sir, let's suppose this is our memory, and now if we have 4 and 4 bytes, that means 8 bytes here and 8 bytes here. But they are available in chunks, right? This is one chunk and this is the second chunk, and rest of the memory is occupied. Can we store this array in your memory, in the memory? No, because it needs contiguous memory allocation. That means when this is the scenario wherein you have memory allocations or memory locations available in a one big chunk, right? That means if you talk about this array, it requires 4 into 4, that is 16 bytes are available, but and they are available in a contiguous memory fashion, right? Or they are available in such a way that it is a one single chunk of 16 bytes. Okay, so then only you can store the elements at that location. Now, obviously, for simplicity, I'm taking this addresses as a number, integer number, but in reality, those are hexadecimal numbers. Okay, so it is easier for me. Okay, so now one more thing is that the elements are stored in a linear fashion, right? But can we access elements randomly? Yes, with the help of indexes. So if you talk about this array, right? 1, 2, 3, and 4. Obviously, this there will be a name associated with this array, right? Now we have index 0, 1, 2, 3. Now, why indexing starts with 0, or why there is a 0 and indexing always starts with 0? Now, the question is that, right? Now, let's try to demystify this fact that why indexing starts from 0. Why not it starts from 1? Now, if you remember, right, I told you that there will be a name associated with this array, that is ARR. Now, this ARR is nothing but name of the array, and name of the array represents, right, it represents its base address, right? Now the base address of this was earlier we spoke about it. So it is 100, this is 104, this is 108, and this is 112, right? So now this is 100. Now let's talk about how you access. We will talk about in the coming slides. We will see how to declare and initialize our array. But let's suppose if we talk about how to access this, we use array and then the subscript and then the index. Okay, the index is 1. Now I told you name of this array represents the base address. So base address is 100. Now plus 1. Now this 1 represents 4 bytes. Okay, so the 4 bytes, then what internally happens, it boils down to 100 plus 4. That means 104. Now 104 is not the first location, it is the second location. Okay. Now similarly, if you talk about accessing the second element or third element in the array, it boils down to what? Array of 2, which is nothing but 100 plus 2. Now this 2 is nothing but 8, right? 100, 108. So you will be accessing the third element in the array. Now, how can you access the first element? So ARR of 0, now it boils down to 100 plus 0 because there are no bytes, right? So it boils down to this, that array indexing starts from 0, and now you know why. And this is how you can access elements randomly. So with the help of these indexes. Okay. So now you might be thinking, okay, now we have an array, can we store different elements, right? Can we store, let's suppose this is the array, can we store, in this we will store integer, then we will store a floating point number, then can we store a character? No. If you talk about any particular array, let's talk about this array. Now the data type or the type of data that you can store in this array will be homogeneous. That means you can only store similar elements. Okay, so these are some facts, and this is how array works, and what are the addresses, what are the indexes. Can you store different elements? No, you can only store similar elements in the array. Now let's talk about the applications of array. Now you might be thinking, sir, why do we need this array? What is the reason that we are using this array? So basically, when you talk about arrays, now obviously when you have a scenario wherein you want to store your elements in a linear fashion, right? And that too, you want to store them in a contiguous memory locations, right? So that you can use your CPU or you can use your memory efficiently, right? Not the CPU. You can use your memory and you can utilize your memory to the maximum, right? So you want to utilize your memory efficiently. At that time, you can use this. But obviously, it will have some drawbacks, right? It will have some drawbacks. That is why we have different data structures, right? So if you want to store your data in a linear fashion, you can use arrays. Okay. Now it is also suitable for the scenarios wherein you require frequent searching, right? If you want to search an element in an array, you can directly go and access these indexes one by one, right? So in a linear fashion, you will access, okay, is this the element that you're looking for? No. Is 20 the element that you're looking for? No. Is 30 the element that you're looking for? No. Is 40 the element that you're looking for? Yes. One by one, you can access all those elements and try to search for the element that you are looking for. Okay. So it is suitable for applications which require frequent searching. Now let's talk about one dimensional. So if you talk about 1D array, it can be related to a row, like we saw in the example, right? So that is what is a one-dimensional array. It is represented in the form of row, and we have addresses like 104, 100, 104, 108, 112, and 116. And indexing will be obviously 0, 1, 2, 3, 4, and then there will be a name associated with this array, which is ARR, and then you can store the elements in this array. Let's suppose here it is an integer array. Okay, so you can store only integer elements, and the size of this array is 5, and you have stored the elements 1, 2, 3, 4, 5. So now it can be related to a row wherein elements are stored one after the other, like you see. You have 1, then you have 2, then you have 3, and all of these numbers are in a contiguous memory, are available in a contiguous memory allocation. Okay, now when you talk about 1D array, there is only one index used, right? When you try to declare and initialize your array, at that time you will use one subscript. Okay, so how you can use that? So let's suppose if I talk about this special array that I have defined here, right? You will define it ARR, and then the index is that the number of elements that are present here, which is 5. So only one subscript will be there, or one index will be used. Okay, so this is how you declare your array. So now let's talk about the declaration and initialization of this array. So obviously, when you talk about the array, there will be a name associated with the array, and then the data type. Are you going to store integer values in that array? Then the one that one subscript or one index that we use, and then definitely the size of the array. So this is how you declare your 1D array. Now, how can you initialize it? There are different ways with which you can initialize it. Obviously, here you are declaring it. Then you might use a for loop to initialize all the elements, or you can declare or initialize your array at once. So how do you do that? So you will write, and let's suppose this is the integer array, and you don't have to specify the size. You can directly write the elements, right? And those elements, let's suppose those are 1, 2, 3, 4, and 5. In this case, when you're declaring and initializing your array at once, at that time, this size becomes optional. You don't have to specify explicitly the size of the array. But obviously, the size of this array will be 5. Okay. Now, since you are declaring and initializing it at once, so this is optional. But in the case wherein you are not initializing it, at that time, this size becomes very important, and you have to mention this size explicitly. Okay. Now let's talk about two-dimensional array. So also it is known as 2D array. So it can be related to a table like this, or you can also say a matrix wherein you have rows and columns, right? Now in this, elements are stored one after the other in such a way that you can think of it as a 1D array. Now this is what 1D array, right? As we have already seen it, right? And inside this one ND array, you have another 1D array, right? Now this is known as 2D array. So now how it works, right? Let's suppose you have numbers over here, and you have four numbers, 1, 2, 3, 4. Then you have 5, 6, 7, 8. Then you have 9, 10, and 11, and 12. So this is a 2D array of having, and this will be similar to what? Of having three rows, right? You will have three rows, not four rows. You will have three rows, and in those three rows, right, you will have what? Four columns. One, two, and so numbers will be like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Okay, done. So now obviously this will have, let's suppose this is a zero based indexing, and this will have a zero index here, one index here, and one. Now internally what is happening, it will be a 0 0, then it will be a 0 1, then 0 2, 0 3, then 1 0, 1 1, 1 2, 1 3, then 2 0, 2 1, 2 2, and 2 3 indexing, right? So similar to that, we will have this index will be 0 0, this will be like this, and this will be like this. So if you want to access the element that is present at this location, what you will do, you will run two for loops, right? One will be starting with from a, let's suppose one will start from I equal to 0 to the length of this outer array, that is 3 less than 3, right? So and the another from 0 to the number of rows that are there. Okay, so this one will be the outer loop, this one will be the outer loop, and this one will be the inner loop. That means the number of columns that are there. So this is for row, and this will be for column. That will start from 0 to less than 4. Okay. So this is how you iterate, and it will be similar to this. And now what about the addressing, right? What about the addresses that will be there? So this will be, let's suppose if this is 100, now this will be 104, this will be 108, this will be 112, this will be 116, because internally it is treated as if they are again in a contiguous memory location, but this time around you have a 1D array, and inside that 1D array you have another 1D array. So for declaring it, you will use two subscripts, right? So it will be something, the name of the array, then two subscripts. And now this will represent the number of rows, and this will represent the number of columns. So in this case, the number of rows will be 3, and in this, and the number of columns is 4, right? So this is how you declare your what? A 2D array. So dimension depends upon the number of subscripts you are using. So this time around, we are using two subscripts. Now, let's suppose you are using three subscripts, right? So similar to like this, 3, 3, and 3. Okay, so this time around, this is a 3D array. And similarly, you can have multi-dimensional array, right? And you just need to keep on adding the subscripts. That's it. Okay. Now, how do you declare and initialize 2D array? So obviously, there will be a data type that is, let's suppose, int, and then the name of the array, then the number of columns, number of rows, and number of columns. So let's suppose 3 is the number of rows and 4 is the number of columns. This is how you declare. Now, same thing like we saw in 1D array, we can declare or initialize a 2D array at once. So this time around, let's suppose this is the integer array and the name of the array, and then you have two as a rows, number of rows and number of columns. Then you have this curly brace and it will end it. Similarly, this represents these two lines, right? You can see this represents the number of rows. So you can see there are two rows, right? And this represents the number of columns. So you can see that there are two columns. Okay. So similarly, what you will do, you will create one, two, three columns, and then four, five, six. So there are two rows and three columns in this example. Okay. So this is how you declare and initialize your 2D array at once. Now let's talk about implementation. So this is how you implement arrays. So in this you have int main, wherein this is the driver function, and in this driver function what we are doing. So this stdio.h is used for standard input and output, right? So let's suppose the scanf statements that we are using, scanf, printf, all those things are available in this library. So how do you declare this 1D array? So you will write int, the data type, then the name of the array, that is roll number, and then one subscript, and then the size of the array. So in this case, you can easily say that this is a 1D array, right? Now, how do you take inputs? We will be using scanf, right? Now we will loop around it, right? So indexing starts from 0, so we will loop around from 0 to 9, right? And it is obviously less than 10. So 0 to 9 means 10 elements, right? So makes sense, right? So 0 to 9, that means 10 elements, and one by one we are inserting value in this array. Okay, we are asking user to input the array, so he puts 10, 12, 13, 14, 15, 16, like this, right? So all the elements are filled in with the help of this scanf, and then we are just printing out those elements that are present in the array with the help of this. Now for using or for inserting the value, we are using the name of the array plus the index. Okay, we are saying, okay, this is the 1D array, please go ahead and insert a value at this index, that is 0th index. The name of this array is nothing but roll number, right? So one by one we are inserting the value, and with the help of this same index we are accessing this one by one. So you can see the input, let's suppose 12, 13, 34, 56, 12, 87, 56, 78, 23, that means, and 10, that means we have 10 elements, and one by one we are printing them back. Okay, so this is how you implement 1D array. Now let's try to see its implementation in code blocks. Start. Now if you can see that we are using this hash include studio.h, then we have the driver function, then we are declaring our array, and then we are scanning through the array. That means we are inserting values, taking inputs, and then one by one we are printing it, and that's it. So why I'm not using a curly brace? Because there is only one statement within this for loop. So this is self-explanatory to this for loop, that this statement, the next statement that is there, belongs or is associated with this for loop. So that is why the curly braces are optional here. Now let's save this file, and now let's try to run this. So you'll go ahead and build and run it, and then we'll start inserting the values one by one. So 1, 2, 23, 45, 6, 7, 8, 0, then 1, then 2, 3. Okay, so you see we are printing out 1, 23, 45, 67, 78, 9, 0, 1, 2, 3. Okay, so this is how you insert values in the array and how you print them. Now this is for a 1D array. Now for 2D array, what are the things that are going to change? Or now how this is a dynamic array, right? You're not you are inserting values at runtime. But if you want to declare a static array, how you do that? You will just go ahead and just write an empty subscript that is without any size, and then you can insert 1, 2, 3, 4, and 5. Okay, so then this you will remove this. Okay, and then just run it, and then just build and run it, and it will print out 1, 23, 4, and 45. Okay, so now what is happening over here? So since we are only inserting four values, right? And the rest of the elements, right, that are we are looping around, right? If you see what is happening over here, so you see our array is four. The size of the array is four, but we are looping around and we are trying to access the elements that are not there, right? So if so roll number, we are thinking that okay, the size of this array is 10. Now rest of the elements contain garbage value. Okay, this is similar to the thing that, let's suppose if you do 0 here and then you don't write anything here, then you write 1 2, then you write 1 2 3, then you write okay. Now I'm exceeding the value. Okay, so now this time around it will only print the elements that fall under this range. That means only the first 10 elements will be printed. Okay, now let's save this. In the earlier case we were getting garbage values. Now let's run this. So you see up to 12 and 12. Okay. So you see 12 and 12. So these three elements are not printed because we are not looping around them. Okay. So this is for 1D array. Now, if you want to declare and initialize a 2D array, you will use two subscripts and then you will use two for loops, one for iterating through the rows and one for iterating through the columns. Start. So in this way, you saw the implementation of 1D array. Now you can go ahead and try to implement what 2D array or 3D array, and you can implement multi-dimensional arrays as well. As soon as the dimensions are increasing, the subscripts or the indexes are increasing, you can increase the number of loops, one for the outer loop, then one for the inner loop in 2D array. Similarly, if this is a 3D array, one for outer, that means this will be a 2D array, and inside that 2D array there will be a 1D array. So that is how it works. So as soon as your dimensions are increasing, you will go ahead and increase the number of loops, and in terms of while accessing them or while taking inputs. While inserting the values you can do that, and while printing the values you can do the same. Now let's talk about advantages of arrays. So obviously when you have indexes associated with the array, right? We have indexes. So it is easy for us to access any element, right? With the help of this index. So if I want to access the third element, you can directly go ahead and say ARR of 2 in the 1D array, right? So you can directly access elements with the help of indexing. Similarly, it is easy for us to iterate through it, right? With the help of one for loop, we can iterate through all the elements, right? One by one that is there, okay, that are there in the array. And similarly, if you want to do the sorting, we can go ahead and easily iterate through these elements one by one and look for an element. If we are trying to search an element in the array, let's suppose we are searching for 3, so one by one we will search, okay, is this element 3, 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 right? And if this element is 3, we can easily search. And also for sorting, right, let's suppose we want to sort this array, what would it be? It will be simply what, if you have 4 here, 3 here, 2 here, 1 here, and let's suppose you have 0 here. Okay, so now you want to sort this in the ascending order. So what you will do, you will use two loops. One will focus on this first element, and then the second one will compare all the elements. Okay, and then at the end of this thing you will have the largest element at the end of the array. So sorting, iteration, searching, it is easy in array. You just have to iterate through all the elements one by one. Now it is a replacement of multiple variables. Now what do you mean by this thing? Let's suppose you have an integer, or let's suppose you want to store the roll number of 10 students, right? So what you would have done earlier, prior to what, when you don't know the arrays, what you would have done, you would have said roll number 1, and then it's or you can say S1, S2, S3, S4, and one by one you can store the roll numbers in these integer variables, right? So as soon as our students increase, now let's suppose we are talking about here 10 students. Now as we talk about 100, now what happens if we talk about 500? Are you going to uh, write 500 variables, integer variables, S1 starting from S1 to S500? No, it is a very inefficient way of doing so, right? So instead what you can do, you can create an array, and you can create an integer array and name it student, and therein you will have the size which obviously represents the number of students that are there, and in this case it will be 500. Now if you want to change it to tomorrow, if you want to change it to 600, you can go ahead and easily change it to 600, right? So it is the replacement of multiple variables. So this is what it means. Now let's clear the screen, and now let's talk about disadvantages. There is one disadvantage that can be easily noticed is the size. Now obviously when you're talking about 1D array, right, the size, or any array, right, the size is there, right? So you cannot exceed this size. The elements cannot exceed this. So let's suppose you have the size is 5, you can only store 5 elements, right? You cannot go more than that or beyond that. Now if you have a size 100, and now you're trying to store only 2 elements, anyway the 100 memory allocations will be there for this array. That means you are wasting your memory, you are not utilizing it efficiently. Okay, so this is what it means, that size is fixed and you cannot store more elements, and if the capacity is more than occupancy, most of the array gets wasted. Okay, so these are two things. Apart from this, you need a contiguous memory allocation. That means if chunks of memory are available here and there, you cannot store an array which is, let's suppose here you have 16 bytes and here you have 16 bytes. Only if you have an array which is of 16 bytes, that means if you have an array of size 4, that array can be stored here. But if you have an array of, let's suppose, size 8, you cannot store 4 elements here and 4 elements here. That will not be happening. Okay, that cannot happen rather. Okay, because it needs contiguous memory allocation. So there is one more disadvantage, and the last but not the least is that insertion and deletion is difficult. Now why do you say that? So let's suppose you have an array and you are having in this array 1, 2, 3, 4. Now let's suppose you want to insert a value 0 at this location. Now what you need to do, you insert the 0 and rest of the elements, every element will be swapped. So swapping is required, right? Swapping is required. Plus there should be memory available so that you can store that element. Else if there are only 4 elements and now you want to store 0 and the size is also 4, at that time around what happens, you will store 1 and rest of the elements will be swapped and you will be losing this value. So it is very difficult to insert the value. Now same thing will happen when you're trying to delete, but at that time you will not be losing data, but yes, swapping is required, right? So let's suppose you want to delete this location, so what you will do, or delete this number, what you will do, you will overwrite this with 3, you will overwrite this with 4, and let's suppose if there is 6, you will overwrite this with 6. So at the end you will have 1 3 4 6, right? 1 3 4 6, and one memory allocation is there and it will contain the same element, that is 6. So next time around, you will just overwrite this. So again, the swapping is required. So it is very difficult to insert and delete an element in the array. Now let's talk about linked list. Let's understand what is linked list. It is a linear data structure. That means it is storing its elements, or the elements are stored in a linear fashion. Now, if the elements are stored in the linear fashion, that means all the elements can be stored as per the memory availability. Now, what happened in array, right? If we have this memory location, that means if we have a 16 bytes of size available in the memory, only then we can store 4 elements here. If the chunks of memory, right, there were, let's suppose 8 bytes here and 8 bytes here, and we want to store these 16 bytes of memory or 16 bytes of elements. That means there are 4 elements in the array. We want to store those 4 elements in the array. We cannot. Since elements can be stored as per the memory availability, that means in linked list we can use these chunks of memory, which was the problem in array, right? And that was resolved by linked list. That means we can use these chunks of memory. Now if your memory is available, that means if your memory is available in chunks, we can still use the memory efficiently. Now, this is one thing, right? Now, these two things are clear to you guys. Now, the third thing is that you can access elements on a linear fashion, or you can access elements in a linear fashion only. That means if you have a linked list, let's suppose this is a linked list. We'll talk about this, why it is that I'm writing that. So now, in order to access this, you need to access all of these elements. Random access is not possible, right? So let's suppose if you want to directly go to this place, this node, it is not possible. You need to traverse all the nodes one by one. So in a linear fashion. So one by one, you will go here, then you will go here, then you will go here, then finally you will go here and access this node. Now, like array, like array, if you have this linked list which is of in which you are storing integer values, you can only store, that means the data stored in all the nodes will be of type integer. Okay, you cannot, there is no such scenario where if you want to store a float in this and int in this, that will not be the case. Okay, so you can only store homogeneous elements which is similar elements. So in arrays there was one more problem associated when we are using arrays. That means the size was fixed. So now in this, the size is dynamic. That means if you have four elements to be stored in a linked list, you can store them without wasting any memory or without having the condition where you cannot store more than four elements, right? So if you want to store eight elements, you can store. Again, without wasting memory or without underutilizing your memory. Okay, or you can also let's suppose if I am saying in arrays the size was 4 and I want to store 8 elements, that was not possible. But here that the size is not fixed, it is dynamic in nature. Now we can easily insert and delete elements in the linked list. Now what you want to do, we want to insert an element in a linked list, right? We just need, let's suppose we want to insert a link node in here. So what we are going to do, we are going to just remove this link, add a node, link this node to this and link this node to this. That's it. So with the manipulation of single link, we were able to insert a node, which was not in the case of arrays. We need multiple swaps. Now, similarly, if you want to delete this element, right? So now let's suppose that we want to delete this node. Again, with the manipulation of single link. Earlier it was linking to this, now it's linking to this. That's it. With the manipulation of a single link, we were able to insert and delete a node, which was not in the case of arrays. We need multiple swaps. And also we need to keep this thing in mind while we are inserting, that there is a size available. Let's suppose if four elements are there already and you want to insert a fifth element, that means even if you're swapping it, the fourth element that is there, the last element will be lost. That should not happen. Okay, so again, now there's one more thing that is associated with linked list and which is very important, that the root node, that is this node, is the key, right? What do you mean by this thing? That this is the head of the linked list. That means if this head is lost, right, this is the pointer which is pointing to the first node, and this is the guy who is responsible or who makes it easy for us to traverse through the entire linked list. So we always keep the track of our head node, and it is generally termed, or root node is generally termed as the head node, right? And if head node is lost, your linked list will be lost. Okay, now if this head node is lost, your whole linked list will be lost. So you always keep track of this node, and even if you want to traverse, you always store this head in a temporary node and then change this temporary node, not this. It will always point to the first node of your linked list. Now let's talk about applications of linked list. So as we have already seen that if the memory chunks are available here and there, let's suppose 4 bytes are here, 4 bytes are here, 4 bytes are here. So we can use these in order to store 4 or 3 elements, right? And we can link them later on. So if you have a system wherein your memory is very limited, right? And you want to, memory is limited and you want to use that memory to its full extent, right? It is suitable for those applications or the condition where your memory is very limited. So you can easily go for linked list. Also, we have seen that since there is not much manipulation required, right? When you're trying to delete or insert an element, let's suppose you are trying to insert a node, what you will do here, you will manipulate this link, you will link this to this and this to this, right? And then what you're doing with the manipulation of a single link, you were able to insert the element. And same goes for deletion. If you want to delete it, You just have to manipulate this link and you are linking this node to, obviously, in this case, you are linking it to this node. So with the help of a manipulation of a single link, you are able to insert or delete the node. So it is the application which requires frequent insertion and deletion operations. It is also suitable for those applications. You can easily go for linked list because you know you will be saving a lot of time as compared to arrays. Now let's talk about types of linked list. So we have three types of linked list. We have a singly linked list, we have a doubly linked list, we have a circular linked list. Now let's talk about singly linked list first. So in singly linked list, there will be a pointer which is always pointing to the first node, right? That we have already seen. And that pointer is known as the head, or you can say the root of the linked list. And it is very important that you do not manipulate this head. If somehow you have manipulated this head, then you will get undesired results. Okay, so now this is how your node looks like. This node contains two parts, right? There are two parts associated with this node. One is the data part, another is the link part, or also known as the next. So this data contains the value, that is the homogeneous nature. That means if you're storing an integer value in this data part, you will always store data integer value in this data part. So this is what you store. Let's suppose you're storing 5 in it, right? So this is the data part. Now there will be some address associated with this singly linked list, right? Let's suppose it is 1000. Obviously it will be hexadecimal number, but for simplicity, I'm taking this number as an integer. So now, and this address will be, or the reference will be stored by the root node, which is 1000. So this address is here. So now this link will always contain the address of the next node, that is this node. This will obviously have some address. Let's suppose this have 2000. So 2000 will be stored in this because this is pointing to this node. Okay, similarly this node will also have some data. Let's suppose it is 10 and it will be pointing to the next node, which is, let's suppose the address of this node is 3000. So 3000 will be here, and this will contain also some data, that let's suppose 15. And now since this node is not pointing to anything else, we will store null in it. Okay, done. This is how your linked list, singly linked list looks like. So you have this data part and you have this address part. So these two parts will be always there when you're talking about a singly linked list node structure. Okay, so also this pointer that is pointing to the first node is the head pointer, and your last node will always contain next. In the next part, it will always contain null value. So this is how your singly linked list looks. Now let's talk about doubly linked list. If you talk about doubly linked list, there are two pointers or two things associated with it. So obviously this head node will always point to the first node that is there, right? This is the first node. And this will again be the key or the root of the linked list, or this time around doubly linked list. So this will store the previous address and this will store the next address. So in this case, there is no previous address, so it will be null. And this will contain always the data part, which will be again homogeneous. So if you are storing integer, all of them will contain integer. So in this case, let's put a value in it, 20 and 30. Done. Now what happens after that? Let's suppose now this is its previous is null. What about its next? So it will have 1000 in it. Let's suppose the address of this is 2000 and the address of this node is 3000. Now again, just like we saw in singly linked list, this will always contain null. Okay, the previous part. So you have the next part. So this next part will always contain null, and you have this previous part. You have this previous part. You have this next part. So then let's first see how we can move in the forward direction. Now there was one drawback with singly linked list, that you can always move in a forward direction. So only one direction. You can move only in a single direction, that was in the forward direction. There is no way you can move in the backwards direction. So doubly linked list avoided, or it mm, what it rectified that problem with the help of this previous and next links. So previous links will always go help you to traverse in the backward direction, and obviously when you have this next in place, it will help you traverse in the forward direction. So now what happens this, or let's first talk about the next links. So obviously now this node is pointing to what? 2000, so 2000 will be stored in the next part. So again, this will be stored in 3000 and this will be stored in finally the null values. Okay, done. But uh, what about the links which help us to move backwards? Those are previous. So it will point to the previous node, which is nothing but 2000. It will point to its previous node, which is nothing but 1000. It will point to its previous node, which is nothing but in this case, it is null because it is not pointing to anything else. So if we observe carefully, so there are two things that you should keep in mind, that the first node, its previous will always contain null, and the last node's next always contain null. So previous helps you in moving backwards, which was not possible in singly linked list, and next will always help you move forward, which was obviously the scenario in the singly linked list as well. Now let's move on to the circular linked list. So in circular linked list, again, this is the head node or the root node of the linked list. In this case, it is the circular linked list. So again, this node part will contain two things, the data and the link. So data will be, let's suppose data is 10, 20, and 30, right? Now this will have some, obviously some address. Now let's suppose these are the three addresses. Right? Obviously, there will be hexadecimal addresses, but yes, for simplicity, I'm taking this as an integer. So the link will contain the address of the next node, which is nothing but 3000, 2000 in this case, and 3000 in this case. But what happens in the circular linked list? Now, the last node, right, will point to the first node that is there. So the first node that is there is at location 3000. So you will store 1000 in it. Now you might be thinking, sir, this is similar to singly linked list, but the only thing that is different in this is that the last node in singly linked list was pointing to null, and in this case, the last node is pointing to the first node. Is that correct? Yes, absolutely. Okay. So the last node is pointing to the first node in circular linked list. But in terms of when you talk about singly linked list, at that time around, this will be null. In this case, in circular linked list, it will always point to the first node, and head will always point to this node, or it will always store the address that is 1000, and it will always point to the first node of the linked list, be it in any of the linked lists, be it circular, be it doubly. So again, it will store 1000, or be it singly linked list, it will store 1000. That is the first node. So with this, we are done with the types of linked list. So there are three types of linked list. One is a singly linked list, another is a doubly linked list, and the last is the circular linked list. So the only difference between singly and doubly is the last node, which points to the first node in the circular linked list. Now, in doubly linked list, it is similar to singly linked list. That means it has some features that means we can move forward, but it has some extra features with which we can move backwards as well with the help of its previous part. And with the help of its next, we can move forward, which was in the case of singly linked list. And it was a new feature which was added to the doubly linked list, with the help of which we can traverse backwards. Now let's talk about declaration and initialization of linked list. So you might be hearing me say over and over again, the type of this is a node, right? This is a node, this is a node. Now how do you declare that node? We'll declare that with the help of this structure, and we name this as node. And inside the structure, we have two data members. One is of type data, or you can say the data part, and the another is the next. which is nothing but a self-referencing pointer which is pointing to itself, and obviously it contains the address of the next node. Obviously now it is contains the address of the next node, which is also of type node, so that is why it is a self-referencing pointer. So now here we have defined one. With the help of this temp, we are going to access the data members of this node. When you try to allocate memory, what are the things that you can use is the malloc function to allocate memory. And once you use this malloc function along with the size of operator, which is obviously of type structure, obviously you are calculating the size of this node, and then you're allocating that much amount of memory, and then finally we are going to typecast it in to the type that is again of type node. Okay, and then we are given or we get some address that will be stored in this in this tab. So this is how you will be creating your node, and in this case the data part will contain 1 and the next part will contain null, and the reference or the address that is there 1000 will be stored in this temp, because this is the temp which is pointing to this node. Okay, then so now similar to what we have seen, the data part and the next part or the link part, right? This will contain the link and this will be pointing to this node, this will be pointing to this node, this will be pointing to this node, and the last node at that point we will have instead of this next. So instead of this address that is there, right? Obviously it will have some address. Let's suppose it is having 4000, this is 5000, this is 6000, right? And let's consider this to be 3000. So now this 3000 will be stored in this head, which is pointer obviously of type node, and it is pointing to the first node of the linked list. Okay, this is pointing to the first node and it will store 3000, and this will store 5000 because it is pointing to this. This will store 4000 because 3000 is pointing to 4000, and this 5000 will store 6000. And now finally when we are at the end of the list, this will store the null because it is not pointing to any node. Okay, so this is how you declare and initialize your node when you talk about singly linked list, because again this is a singly linked list because we only can move in the forward direction, and there is no way that the last node that is there is pointing to the first node, which is the case of circular linked list. And in doubly linked list, we can traverse backwards as well. So you might require one more self-referencing pointer that can be either previous, that can you can name it previous, okay? And this is the next. And in that case, what you will do, you will create another data member that is struct node, and it will create you will create a pointer and naming it previous. Okay. So this way around you can create a singly linked list, and the structure that how it looks is like this. The two data members are there, and with the help of malloc you can allocate memory, and with the help of this arrow operator you can access the data part and store some value, and with the help of this next part you can access the next part and store some value in it. And this is the temporary variable. Obviously it should be tmp in this case. And TMP is nothing but a pointer which is pointing to the first node or any node in that case. Okay, so you will define it and you will initialize it. Now let's try to insert the element in the linked list and try to see the implementation of insertion at beginning. So here we have this function, right, which is known as insert underscore bit. So insert at beginning, and we are passing in the argument as the element that we want to store. Now let's suppose we are obviously in the main, we will be creating the root node, right? And we will be creating this globally so that we don't have to pass it to every function. Okay. So now there will be two cases, right? Now since we are inserting at the beginning, right, there can be two cases. The first case is that our entire linked list is empty. And at that time, what will be the root that is represented here in this particular example or in this particular function is it is represented by p. So p will be null, right? And there will be a scenario wherein you have some nodes. It can be either one or two or three, it doesn't depend. Anything that is more than one will have to do a different thing, right? At that time we'll be having the address of this node, and then we'll be creating a new node in both of these cases, right? We'll be creating a new node, then this will act as the p node or head node, right? This will be pointing, this P or head will be pointing to the new node, and this will be now the new head. Okay, so these are the two scenarios. Now let's see how we are implementing it. Now here we are just creating and allocating memory to the new node that we just created, right? And when we create this, we are creating a node wherein which in which this temp is pointing to this new node, right? And after that, what we are doing in this new node, we are pointing this temp's data to the element, right? We are initializing this data part, and we have the next part, right, in this new node, and we are initializing this data part with the element, right? Let's suppose this is 5. Now this is done, right? These two steps are done. Now we're checking if root, that is this p, which is obviously globally declared, right? So we don't have to pass it to every function that we create. Now if this p is null, right, that means our linked list is empty. Now let's suppose the first case is there, right? And at time what we are doing, we are making this temps next as null because there is only one element, right? There's only one node in the entire linked list. So its next will be null. And now what we are doing, we are updating this p because this is a globally declared this p, that is the root. Now what we are doing, we are pointing this p to this new node, right? This is our root node now. And now since it is globally declared, we don't have to even pass it. So that is why the return type of this function is void. Done. But this is one case. Now let's see. Let me just erase the unnecessary things that I don't want. Now, in this case, the next case, now we have this data part, or we have this node, we have this one node available for us. Now, next time around, when we are calling this function on, let's suppose 10, and we want to insert this 10 at the beginning. Now we have this time around, there will be some address allocated to this. Let's suppose this is 1000. Okay. Now we are creating a new node. Let's suppose we are creating a new node, and it will have its data part and it will have its next part, right? Now 10 is stored in here, and the next will be obviously will be dependent on certain factors, right? Let's not talk about next right now. And the data is executed, this is done, and obviously this will have some address. Let's talk about this address, it will be 500. Now, is our p equal to null? No, it is pointing to this node and it is 1000. So it is not null. So this won't be executed. Now we go into the else part. What we are doing, please go ahead and whatever is in the temps next, please store p in it. So p is pointing to 1000. So 500's next will be nothing but 1000. So this node is linked with this node. Okay, now the next thing is we need to update this p. So in the last step after this else part is executed, p is pointing to this new temp. This is the temp, right? This will just we create. So this will be your p, that is your root or your head. Okay, now we keep track of this head, and this is not pointing to this anymore. Okay, so with this we are always what we are always inserting our element at the beginning. So in both these cases, we saw what will happen. So the first case was wherein we will have our list is empty. That means there is no element in the linked list. And in the next case, we saw when our list is having some element, what will happen, or our list, there are some nodes available in our linked list. So this is what happens. Okay. So this is insertion at beginning. Now let's talk about insertion at the end. Right? At the starting of when we talk about what is linked list, I talked about one thing, that we will we will never change our head. Never, no matter what. Because if that thing is changed, the whole linked list will be manipulated, or even in some cases, our list will be lost. Okay, so now what happens? We are trying to insert at the end. Now we know that in a linked list, we cannot access directly the state because we haven't kept track of this last node. So what we are going to do, we are going to traverse to this end and then insert the element, right? Now again, two cases are there. If our linked list is empty or if our linked list is having some nodes. Now let's clear this and let's see how to implement it. So we have this function insert end and we are passing in the element that we want to store. Okay. So now what we are doing, we are obviously if there are no elements, then this p will be null. If there are no nodes in this linked list, then p will be null. And what we are doing, we are storing that p because we don't want to change, because there will be some scenario wherein you have a single node here and this is 1000. So what we are doing, we are allocating or we are initializing this temporary node, temporary structure type of variable, right? Temp, and we are assigning this p to it. Okay, so this is also assigned to this node so that we don't change our head node, which is p. And obviously again, these temp1 are defined globally so that we don't have to return it or pass it or even declare it. Okay, so now what happens, now we are creating a new node that is tmp1, and we are allocating data to it. That means we are inserting the element that is 10, and we are always initializing it with its next part with null. Now why is that? Because it will be always inserted at the end. As we have seen earlier, what is the next of the last node? It is always null if we talk about singly linked list, not in a circular linked list wherein this will be storing the address of the first node. But since we are implementing this using singly linked list, so every time the last node, next part of that will be null. Okay, done. So every time we will be creating a new node and its next part will be null. Done. So these are two steps. These two steps are done. And we have this temp pointing to this node. It can be either empty or you have some address. Okay. So now what happens? These two steps are done, right? Now we check if P is null. That means if this is the scenario, at that time, what happens? We'll point this P to this TTMP1. That's it. We are pointing this, and this will be the last node. Obviously, if there is no node in the linked list, that will be the last node of the linked list, because there is only one node, right? That will be the first node, that will be the last node. None, but, and this part will not be executed, and we are done with our process. But what happens if there is a node? Now let's talk about this scenario, right? Let's suppose in the first case we didn't have anything, and in the next case we had this. Okay, so this is our data part, and this time around we are trying to sort 20. So what we are doing, we are pointing this TMP so that we don't change this, because this is very important. We never change our root node. We have this temporary variable which is pointing to this node, right? And this is of structure, right? This is of the same structure that the every node is, right? Now we created ttmp1, and in that ttmp1 we are storing what, 20, and in the next part we are storing null, because obviously it will be stored at the, it will be added always. We are inserting an element, inserting a node at the end. The next part is null, the data part is 20, and obviously this will have some address. Obviously this will also have some address. 2000, and this is 1000, this 1000, this is 2000, and this is ttmp1. Done. So these four steps are done. Now is p equal to null? No, in this case we're pointing to 1000, so this will not be executed. It will go into the else part. Now what we are doing, we will traverse to the end. In this case, there is only one node. So what will happen? We'll check if temps next. What is temps next? It is null. It should not be null. Unless and until it is not null, we'll traverse. So we are not traversing. So now what we are doing, in this case, this while loop will not be executed. Okay. So this will not be executed. So what we are doing, we have this temp pointing to the same, right? This TMP is pointing to this, because this while loop will not be executed. And then what is the next step that we're doing is temps next, please put temp1. That means this temp1, which is ttmp1. Let me just erase it over here. This is 2000. Please put 2000 in temps next. Temps next is null. Please put 2000. So it's successfully added this new node at the end. Now let me just quickly go ahead and reiterate what I just said, but this time around we have two nodes. Okay, so that we see this iteration happening. we see this loop working. Okay, just a minute, let me just really clear it. So now let's suppose we have this P, and in this P we have 10, and this is 2000. Okay, this is 1000, and this is 2000, and 20 is there, and this is okay. So now let's see what happens. This time around, insert and is called, and we are passing in 30. Done. We have this temp which is pointing to this because we don't want to change it. This is TMP. We created a new node with, and it is TTMP1, and obviously this will have some address. Let's suppose it is 3000. Its data part is, and it's having next part. Its data part is 30. That is passed, and its next is null. Okay, because we are adding it at the end. So these 4 steps are done, right? We check if P is null. Is P null? No, it's 1000, because this P is nothing but our head node. Okay, you can also represent it by head. Okay, now if you're not comfortable with P, so this will not be executed. Now what happens over here? We'll check if we will check the condition, and we will loop around so that we are at the end. So we check, is temps next null? Is this temps next null? No, it is not. So what? Please put temps next in temp. So temps next is 2000. So this will be pointing to this now. Okay. So this is gone. What happens after that? Is temps next null? Yes, it is null. So we will be out of this loop. And then what happens? Please put temp1 in temp1 in temps next. So temps next is null. Temp1 is 3000. So we are putting 3000 in it. So there will be a link. That means this is pointing to this now. So this is how you insert your node always at the end. Now, what will be the time complexity in this case? Now, since we are executing, in the worst case, we will be executing this in such a way that we are always traversing to the end of the list and storing that element or inserting that element. So the time complexity will be big of n. Now, if we talk about this case, wherein we were storing at the beginning, right? Always storing at the beginning. In this case, the time complexity will be what? Constant. We are always storing at the beginning. Now we don't have to traverse anywhere, right? So that is why the time complexity in this case will be big of, well, in the worst case or in the best case, right? It will be always big of 1. So now let's talk about the implementation, and we will trying to delete, or we will try to delete the beginning, or we'll try to delete a node from the beginning, and we'll try to do it always. Now again, since we are deleting, so we will not be creating, so malloc function is out of the picture. So now we're deleting. So again, there will be 2 scenarios. What? The first scenario is that obviously the ground rule is saying that P will never change. That means your head node will never change. So the first thing is that if you don't have anything in, that means there are no elements in the linked list. So if your P is null, or if your P is having some errors, that is if you are having some nodes, so can be 1000, can be 2 nodes, 1 nodes, can be anything. Okay. So now let's talk about these scenarios one by one. So in the first case, right, let's talk about this. So if your P is null, at that time around, you cannot delete anything. So you're printing a message, no element can be deleted, or no element to be deleted. Done. That's it. Now, what if you have a single node, or if you have 2 nodes available? Okay. Now, let's suppose this is 10, this is 20, and this is 2000, and this is null, this is 1000, this is 2000. Okay. So P is here, obviously the root node, or the head of the linked list, right? So we are checking. Obviously, we keep track of. We are not going to change our head node every time we are deleting from the beginning. We are changing our head node, so we need to keep track of things, right? So we have this temp pointing to the first node. Now, is P null? No, it is not. What will happen in the else part? We go and print out the data part of this, that is of this. So 10 will be printed because we are going to delete this. So we are just printing out the message. Okay, this is the element that is going to be deleted. And then what we are going to do, please store P's next in P. So P's next is 2000. So we are going to store it in P. So that means this P is now pointing to this. Done. That's it. That's how you delete. Or if you want to be even, if you want to add one more step, you can do what? Please, now you have this P pointing to this. In the next step, what you can do, you can just update this so that this link is not here. So what you will do, please add or please put temps next, whatever is in the temps next, which is 2000, please go ahead and put null in it. So this will be null, and so this link is broken. So then we can just free this. Okay, that's it. So now this is how you delete the node from the beginning. Now, if you talk about time complexity, it will be always, since we are always deleting at the beginning, so we will always have the head node that is pointing to the beginning. So we don't have to traverse anything. So again, it will be of order that is constant amount of time. That is big of one in worst case. Okay. Now let's talk about the same, but this time around we will be deleting our element at the end. Okay, so we will be deleting always. We will traverse and we will delete at the end. So it is quite evident from now that obviously we will have to traverse, so the time complexity will be big off and in the worst case. Okay, so that is out of the picture. So now how will we delete at the end? So obviously there will be these two scenarios. What first, that our linked list is empty, and the second, there are some nodes so that we need to traverse and delete the last node. Okay. So now what happens if the linked list is null? That we will just say, okay, there are no elements and we are done. So this will be executed. This else if will not be executed, and this else if will not be executed. Done. But what happens if there are three scenarios in this case when you're deleting. So the next case is if there is only one node. Okay, so this is done, right? But what if there is only one node? That means p is pointing to this node and p's next is null. We'll check. Okay, if p's next is null, at that time around, print this data and put p to null, so that we can just directly go ahead and put p to null. That means there was one element and we removed it, and now p is equal to null, and we are back to this scenario wherein p is null. So these are two scenarios. Okay, now let's talk about third scenario. And both in these two cases, the time complexity will be constant because we are not traversing anything. But we always keep when we talk about time complexity, we always talk about what the worst case. Okay, so in the worst case, we need to traverse. Let's suppose we are traversing to the end, and in that case, it will be big O of n. Okay, so now let's erase everything. So these two cases are clear to you. Now let's talk about the final case, right? So what we are doing, we have, let's suppose we have these four nodes, and let's suppose this is 100, that addresses, okay? 200, 300, 400, and this is null. Okay, let's suppose this is 10, 20, 30, and 40. So this is 200, this is 300, and this is 400. And this will be your P. Okay, so these two conditions or these two blocks will not be executed. Now what we are doing, we have this temp. Obviously this will be happening in all the three cases. So temp is pointing to this, and we are creating a new variable that is known as pre. Okay, obviously it is of type structure of type node. Okay, so this is another pointer that we have over here, pre, and this is right now, this is null. Okay, none. So what we are doing now, we have this temp in place. Now what we are doing, we are going to traverse, we are going to check. Okay, now what is happening, now this temp, we will check. Okay, now we will just traverse first with the help of this while loop. We'll check, is temps next null, is temps next null? No, it is 200. Then what we are going to do, we are going to keep track of this node, as well as we are going to move this pointer to this position. So now pre will contain temp. So temp was pointing to 100, so pre will contain 100, and temp will point to this. Done. Again, is temp next null? No, it is 300. Keep track of temp. Temp is pointing to 200. 200 is there. So this pre will point to this. We have the previous node, and the next that is there is this temp. It will be pointing to this node now. Okay, so this link is gone. So now this way we have this temp over here. Next time, is temp next null? No, it is 400. Okay, then what you're going to do, please put pre to this node. So this will be pre, and now our temp will be here. Temp is here. Okay, done. So let me just clear out everything else. So finally, when we are at this position, so pre is here, temp is here. Let's remove the rest of the things. Again, keep this thing in mind. We're not changing the p, that is our head node. So now This is our pre and this is our temp. Now, once again, is temps next null? Yes, it is null. We are out of this for loop. Now, what we are going to do? Please put pre's next to null. Okay, this is just to keep track of that node, so that of the previous node, so that we can just remove this node directly by just updating the previous next. So previous next was 400. Please put null in it. So this link is done. This link is gone. This link is manipulated. So we don't have this node anymore. We cannot access this node. And after that, what we are doing? We are just printing temps data, which is 40. So we are just printing 40. So this is how you delete your node in the linked list, and we're deleting it always at the end. Okay, so previous and temporary. Either you can use temp or you can use two pointers like previous and next. So previous will be this and next will be this. Okay, so you can put relevant names as long as you're comfortable with those names. Okay, instead of p, you can also use what head. Now, let's talk about how to display the elements or how to display the data present in the linked list. Let's suppose this is your linked list, okay? So this will contain 10, this is 20, this is 30, this is 40, and obviously this will have some address that is 100, 200, 300, 400, okay? This P will be pointing to this, okay? And this is obviously a head node, so this will contain 200, this is 300, this is 400, and this is finally null. So now, in order to display elements or display the data present in our nodes, what we are doing, we have this temporary pointer which is also pointing to the first node, so that we are not changing this head node. Then we'll check, is temp equal to null? No, it is not. It is pointing to this node, that is 100. So it is not null. What we are going to do, we are going to print temps data. So we are printing 10, and then we are updating the temp. So we are updating it. So this will be pointing to this, because we are going, what we are doing, please put temps next in temp. So temps next is 200. So this will be pointing to this now. Okay. Again, is temp null? No, it is not. 20 will be printed. It will update this. We go to here. Is temps next null? No, it is not. It is 400, right? So please print temps data, which is 30. Now again, is temps next? Again, we are updating it. Is temps next null? No, first we are going to see, we are present here, then 30 is printed. Okay, so now what we are doing, is temp null? No, temp is pointing to this, right? 400. We're not checking temps next, we are checking temp. Okay, so is temp null? No, it is 400. Print temps data, which is 40. Please update temp to temps next. So temp will be pointing to now null. Is temp null? Yes, it is. Out of this while loop, done. We have printed all the elements. Now again, if you talk about the time complexity over here, since we are traversing all the elements in the or all the nodes, the time complexity will be big off and right in the worst case. Now that we have covered all the implementations, now let's go ahead and implement this in code blocks. Now what is happening, we are including these libraries that we require. Okay, so then we are defining a structure that is of type node. Obviously it will have data part and it will have the next part. Then we are declaring these global pointers or global variables of type node. Okay, so that we don't have to pass it to every function that we have. Okay, so we have a function over here that is void insert at end. That means the return type is null, return type is void, insert at beginning, delete at at the end, and then finally we have display function. Okay, so these are some methods. Okay, so now what happens over here, we have this main method, and in this main method we have an integer that is val and n. So now this is a value that we are going to insert, right? The data part, what we are going to, then we have this root node or the head, which is equal to null. Okay, now we are creating a menu kind of a thing, so that we keep track of what we want to do. So you're here, if you see, if you press 1, we are going to insert at the end. If you're going to print 2, we are going to insert. If you're going to press 2, we are going to insert at beginning. That if you press 4, we are going to delete from beginning, we are going to delete from end, then we are going to press, if we are pressing 6, we are going to display all the elements, and 7 from exiting or from the program. Okay, done. So this is a menu. We are going to use a do while loop. So then we are going to scanf. That means then we are going to press okay, ask the user, okay, enter your choice. Do you want to insert at beginning? Do you want to insert at end? delete end, delete beginning. And now what is your homework? Try to implement insertion at any position depending upon the location, right? Let's suppose there are 5 nodes. I want to delete the third node. Try to implement that on your own. Okay, that's a little homework for you guys. So enter your choice. You just press 2. Okay, scanf does your end will have now 2. Then what we were doing, we are using a switch case. Okay, if the user is entering 1, that means enter the value, and then we are going to enter the value, and then we are going to call insert at end. So 1 is for inserting at the end. That is case 1. Case 2, if you're pressing 2, that means you're inserting, you want to insert the element that you just entered, the val. That is why we have these 2 pointers over here, the val and n, okay, for inserting the value, okay. One is the choice and another is the value. So we are going to call insert at beginning. If you press 4, we are going to delete from beginning. If you press 5, we are going to delete from end. Obviously, now since you're using switch case, we don't want to execute all these function calls. So we are having break so that we are out of this case and so that we are not executing the rest of the cases. Okay, so now we have then finally we have this case 6, which is to break, right, which is to display all the elements, and then 7 to exit from this program. And finally we are not pressing any of these 1 2 4 5 6 7, any of these. We are going to print wrong choice and then we are going to break, right? And also we are going to wait if you want to continue or not. Let's suppose I told you, okay, do you want to continue with this process of entering values or deleting values from the linked list? I'm going to wait unless and until you press Y, that is you are pressing the character Y, we are going to continue. Unless and until you are pressing anything else apart from Y, that is in the lowercase y, that is you see Y, whatever you are pressing, that is for which we are using this get function, okay, GTCH, get character, okay, function, okay. So this is our menu, and we have already seen these implementations. We are inserting at the end, we will traverse to the end and delete in one case. And if there is no node at that time we are deleting, we will print a message, or this is not for the delete, okay, this is for inserting at the end. So again, we are inserting at the end. We will, if you don't have any linked list, if you don't have any node in the linked list, that will be our new node, and that will be the element or the node which is at the end if there is no node. But if there are nodes, we are going to traverse and insert the value or insert the node there. Now, if you talk about insert at beginning, obviously there will be 2 scenarios. You can put it in that way, which I just showed you in the implementation, or you can just put it in this way. This is much more efficient as compared to that. Okay, so simply there will be 2 scenarios. In that case, what we did, we have p to null, or we have, that means there are no elements, so we'll insert the element at the beginning. And then in the next, what we are going to travel, we are going to insert at the beginning, so we are just going to update our root node in that case. So this is what we are doing, we are updating our root node at the end. Okay, just scroll through it, do it right, you will get the intuition what I'm doing. So basically what I'm doing, I'm creating a new node. Okay, I'm checking if temps data, okay, this new node, I'm inserting the values. What values? Whatever is the data part, that element I passed, as to I inserted it in the data part, and whatever is in the temps next, I'm going to store p. So p can be null in one case, right, wherein there are no elements at that time. The temps next will be null, done. And then we will update our p to temp. That will be one scenario wherein we don't have any elements, so p will be pointing to the first node. Now what if we have our node available? What at that case, what we do, we are having this temp one, that is our new node. We update our data part, we update our next part with p, because now this will be our, the p will be pointing to what, the head, earlier head. Now that will be temps next, so the link is there. Now we need to update p, so p is temp one, that's it. So this does the same thing that we did in that case. Okay, therein we were explicitly defining 2 cases. Here we are smartly doing this. Okay, you just try to implement it. Okay, then this is insert at beginning. Now delete at beginning, so there will be 2 cases. If we have null, then no element is deleted. If you don't have, then we print the data, and since it is beginning, then we update our p. So p is next, done. If you want to delete at the end, so what we are going to do, there will be again 2 scenarios. If p is null, that is if head node, there is no head, right, at that time what you will do, you'll just say, okay, no elements are found, and there are no elements that you can delete. In the next scenario, what we are going to do, you're going to see, okay, if there is only one node, right, there will be three scenarios in this case. The first, if there are no elements, if there is a one node, if there are multiple nodes. If there's a one node, you are going to update your next to null and then print the data and initialize your p to null, because now there are no nodes. Okay. And the third case, you will be just traversing to the end and then deleting that and also printing the data part. Okay. So let's minimize this as well. So finally, we have this display method wherein we are just using this temp to traverse through all the nodes that are present in the linked list and printing out data one by one and updating our temp to temps next. Okay, these are let's just minimize this as well, and let's just minimize this as well. So you have 1, 2, 3, 4, 5 functions and you have your menu in place. Now let's try to run this. So let's do a build and run. So now you have your menu in place. So now let's try to enter your choice. Let's suppose we are trying to insert at beginning. So you will press 2 and then press enter. Now you enter a value. Let's suppose we are entering 50. Okay. You press enter. Do you want to continue? Apart from Y, you will not be able to continue. If you press Y, that means yes, you want to continue. Okay. So now if you just, let's suppose if you press a wrong choice, let's suppose you are pressing 8, at that time it will say wrong choice. Do you want to continue? Yes, we want to continue. Okay. So now let's suppose we are going to insert again at beginning. So you will press 2. Okay. Do you want to press? Okay. So he said, do you want to continue? So we were only having one choice. That means whenever we press Y. So I pressed 2. So it break out of the program and our program was done. So now let's try to run this thing again and see different things. Okay. Okay. So now let's press 2 and let's insert a value. Let's suppose we have 40. Do you want to continue? Yes, press a Y. Okay, enter your choice again. So we'll press again 2. We are again going to insert at the beginning. Okay, then let's enter value. So this time around, earlier we entered 40. Now this time around we're going to enter 30. Press enter. Do you want to continue? Yes. Again press 2 for inserting a value at the beginning, right? Enter your value. We are going to enter 20. Okay, now press enter. Do you want to continue? Yes. Again we are going to insert at beginning. We are going to insert. We press 2. Again we are going to enter a value, that is 10. Now do you want to continue? Yes. So now if you observe carefully, I inserted 40, 30, 20 and 10, but all of them were inserted at the beginning. So if you want to traverse through them and you want to print the whole linked list, what should be the output? It should be 10, 20, 30, 40, right? So now let's try to display all the elements. Let's press 6. So it is 10, 30, 10, 20, 30, 40. Okay. Do you want to continue? Yes. Now let's try to delete from the end. So we are going to delete from the end. So which element will be deleted? It will be 40. So now let's press 5. So now, okay, 40 is the element that is deleted. Do you want to check if that element is deleted? Yes, we want to continue and we will display it again with the help of 6. And again, now this time around it is 10, 20, 30. Now let's try to delete from beginning. The 10 will be deleted, so that 10 is deleted. We'll also check if that function is working correctly or not. So delete from beginning, it is 4. Okay, we entered the wrong choice. Okay, we needed to enter yes. So you get the point, right? So all we need to, he said, do you want to continue? So I pressed 4. That is not the input, right? So the input should have been Y. It was expecting. So now since we entered the wrong character, so it break out of the program. Okay. So this is the whole implementation of your linked list. So this way, in this way, what we just saw, right? Let me just clear my screen. So in this way, we just saw 5 functions, right? Insert at beginning, insert at end. We also saw delete from beginning and delete from end. And we also have this display function wherein we are just displaying through the elements. We also saw the implementation where we built a menu. In that menu, we inserted all these functions, and one by one we were implementing that with the help of get character, and we were just building kind of a menu and then then calling these functions one by one. Now you can also implement this insert at beginning and end in a single function that is known as insert at anywhere. right? So depending on the position, you can insert either at the beginning or the end or anywhere in the middle. Same goes for this. You can delete anywhere. There's a function you can try to implement it on your own. Okay. Now let's talk about the advantages and disadvantages of linked list. First, let's talk about the advantages. So obviously, as compared to array, right? When we talked about arrays, they were fixed in size, right? We need to specify the size in the subscript. So fixed in size, which is not in the case of arrays. It is dynamic in nature and you can add as many nodes as you want depending upon your requirement, right? So obviously when you have that uh, independency over the size, you will never, there's no chance of wasting any memory, right? So if you require 4 nodes, you will use 4 nodes. If you require 3 nodes, you will add 3 nodes only. So in this way, the size of the linked list is entirely dependent upon your application. What are the things that you require, you make them, that's it. So you will not be wasting your memory and you will be utilizing your memory very efficiently. So this is the reason why this is written over here, the efficient memory allocation. How you are doing efficient memory allocation? Let's suppose you have chunks of memory available here and there. You can link them together and allocate the memory and use those memory location for storing the data, right? So memory can be used efficiently. Memory is not wasted. It is dynamic in size and it is very easy to insert and delete a node in a linked list just by manipulating a single link, as we have seen earlier. Just if you want to delete this, you just manipulate this link and just point this link to the next node, which is after this node. That's it. You are done with the deletion operation just by manipulating a single link. Similarly, when you're talking about insertion, at that point, you just you if you want to insert at this location, you remove this link, point it to this, and then remove and point this new node to this node that is there, that was already there. Again, we are manipulating a single link. Okay, just the manipulation of single link here, that is required for insertion, and a single link here that is required for deletion. Now when we talk about disadvantages, one of the major disadvantage is that you cannot lose your head, right? The head node that is pointing always to the first node, either in a singly linked list or a doubly linked list or a circular linked list. This head node cannot be lost. If this head node is lost, or if it is manipulated, right? If the head node is lost or manipulated, the whole linked list will be lost, right? Let's suppose this is your linked list and somehow, right, if this is the head node and somehow you made it traverse to this particular point, right? Now head node is pointing to this in a singly linked list. Now there is no way you can access these nodes and you will get undesired results. Another disadvantage is that you cannot access randomly. So random access is not possible because if you want to go at this particular node, you have to traverse through the first 3 nodes first. Why? Because this node knows the address of this node. This node knows the address of this node. This node knows the address of this node. There is no way you can directly go to this particular node. Random access that was there in the arrays with the help of indexing, you can randomly access the elements. That is not possible in terms of linked list. And the address of the first node is known to the head of the linked list or the root of the linked list. Okay. So that head is pointing to this first node. Okay. So you cannot change or manipulate or lose, or you cannot lose your head because the whole linked list will be lost. Okay. And the random access is not possible in linked list. Now let's talk about stack. What is stack? Stack is a linear data structure. That means if the elements are stored in a stack, they will be stored in a linear fashion. Now, it follows the principle of last in, first out, also known as LIFO. That means the element that entered at the end or in the last will be the first element that will be removed. As simple as that. Now, you might be thinking, okay, it follows the principle of LIFO. Now, that does that mean its removal is restricted? Yes, it is. So you can only access the top of the element. That means this element is accessed. And how can you keep a pointer or keep a track of this top? With the help of this top index, this pointer or iterator that is kept for the tracking of the top of the element. So once you have entered this, the top will go up. Then you have entered this, the top will go up. That means you're incrementing top. And finally, the top is here when you enter this. Now, since you're removing this, that means only you have the access to the top of the element. You are removing this, then you will decrement your top. Okay, that's it. So with the help of this top iterator, you can keep the track of the last element, and you can also keep the track of the elements which entered in the stack. Insertion and deletion can take place only from the top, which is obvious, right? Let's suppose you're trying to insert the element. What you will do, you will increment your top and then insert your element. And if you want to remove it, you just decrement your top. That's it. So this is what you mean by pushing and popping, right? So the elements that you are inserting, that is nothing but your push operation, and you will increment your top. So elements you are removing is nothing but your pop operation. If you take an example of stack of plates, right, one after the other, the plates are stacked upon each other, right, one by one. So you can only access the top plate and you cannot access anything that is in between. So that is the restriction that is there. So in terms of stack, there are four major operations: push, pop, is empty, and peek. So push means nothing but to insert an element in the stack. So you're inserting. And now you might be thinking, okay, what is the time complexity of this push operation? Since we can keep a track of this, the top of the stack, right? With the help of this top, we can have a track of what are the elements that are on top, right? So only, let me just show you. Since the top is here, right, at this, now you want to push, so you just update your top, that's it, right, and you insert value. So this takes a constant amount of time. So inserting a value takes a constant amount of time. That is the big O notation, right? Big O of 1, that is constant amount of time. So similarly, we can remove the element, and it can be done with the help of this pop operation. That means we can remove this top of the element just by decrementing our top. Once we decrement our top, this top of the stack element is removed. So now again, we are just accessing, or we are just manipulating this top in a constant amount of time. Again, this push operation and pop operation, both of these operations take big O of 1 time. That is the constant amount of time. Similarly, if we check is our stack empty or not, we just check the value of this top. If this top is having any value other than -1, that means we have elements in the stack. So we return false. So again, this is empty operation, takes constant amount of time. Similarly, peek is nothing but it is similar to pop. Only thing is that we will not be removing, or we will not be overwriting the top of the stack value. We will just see what is the top element. That is, if we are implementing it with the help of array, we will see that it can be implemented using arrays and linked list. So if we are implementing it with the help of array, as we have already covered it, and if we are implementing it linked list, we'll see both of these implementations one by one. So let's take an example wherein we are implementing it with the help of array. So what we will do, we'll just return this value. That's it. We will not be either removing it or overwriting this value. We'll be just returning the top of the element. So peek is similar to pop, but the only thing is that in pop we are removing the element, in this we are not removing the elements. Again, this will take a constant amount of time. So all these major operations are taking constant amount of time. That means with the help of this top iterator, we can do all these operations in a constant amount of time, because he is the guy who keeps track of what are the elements in the stack, and with the help of this we can remove the element from the top of the stack, we can add the element from on the top of the stack, we can push, we can pop, We can check if the stack is empty or not based on the value of this top, and we can also peek the element, right? We can take a peek of the element, right? So with the help of this top, okay? So again, that is in a constant amount of time. Now let's talk about the applications of stack. Now, whenever we use recursion, right? Whenever you use recursion, what happens internally? A stack is created, right? Let's suppose you have a function call, and in that function call, you are calling this function again. Obviously, this will be called from the main function, right? Let's suppose this is our main function. Let me just erase it and write it in. Yeah. So this is our main function, and it's calling this function, and this function is calling this function. That means it's calling itself again and again and again, unless and until a base condition is reached. Right now, once the base condition is reached, it starts popping it out. Right. This is all these are push operations. Right. And now pop is performed one by one, unless and until all the function call return its value, and finally it returns to our main function, and finally then main function is popped out of the stack. So whenever we are using recursion, a stack is maintained. And we also find out when we talk about recursion more in depth in this tutorial, we'll see how we to create this activation record that is created, and activation records are created, and with the help of these we can easily detect what are the statements that are yet to be executed, okay, in a function call. Let's suppose you have three statements in a program, and one of them is to check the base condition, second is to the function call itself, that is this function calling itself, this is a function outer function, and in that function you have three steps, and then this is a simple print statement, okay. Then let's suppose this is an activation record and one, two, three. So this is checked and this calls the function again. So again, an activation record is created. So again, one, two, and three are checked. So this is checked. Again, this calls a activation record. So now these are all push operations. So once it returns, now the pop is performed. Now it returns to this point and it executes this value. That is prints out the value, whatever is the value, and once it is done, so it returns to the function who called it, and once that is done, this will be popped out of the stack, and then once this is executed, it will return to the main function. So in recursion, stack is maintained internally. Now what about parsing? So whenever we talk about automata, right, automata is one of the subjects in computer science. Therein the parsing happens whenever your program is divided into tokens. Tokens are nothing but keywords. What are the keywords in this program? What are the conditional operators in this keyword? What are the constants? So all these in your program, all of these things are divided into tokens, and then parsing happens. Okay. What about the browser, your application? Whenever you open up any website, right? Let's suppose you are opening Great Learning Academy. Before that, you go into the Google Chrome, you type in Great Learning, therein you will get the link of Great Learning Academy. Click on it, it redirects you to the Great Learning Academy. Then in Great Learning Academy, you look for the popular courses, or let's suppose IT and software courses. When you click on it, let's suppose it directs you to the another course that is related to IT and software. In that you have, let's suppose, C. You click on it and it will direct you to the C program. So one by one, these are all push operations: P1, P2, P3, and P4. All these are push operations. Now once you press back, what happens? You pop out, this pops out of the stack, and you go on to this courses. Again, you press back button, you go on to the Great Learning Academy. So these are all pop operations, and finally when you click on the back icon, you go on to the Google page, right? So this is all that happens while we are working in browsers and in editors. Whenever you do redo operation or undo operation, again a stack is maintained. So these are all the applications of stack. Now let's try to implement stack using arrays. Now before we do that, let's try to understand the declaration and initialization whenever we are implementing our stack using arrays. So we define a structure here and we named it stack, stack, okay. And in that stack structure, we have three data members. What are those data members? The top, which is used to access the top of the stack, which is used obviously for push and pop operations. Then we have the size of the array, and then we define the array. Now also, whenever we are going to create this array, we are going to call it in the main function. And in the main function, when we call this create method, we are sending the arguments, that is the size of the array. And in this we create, and we are returning, after that we are returning the stack. Okay, so how do you allocate memory to the stack? So we use malloc operation, and we define the size according to this structure of the stack. And once the size is there, we just typecast the stack. That's it. And then we assign values to these data members. And we assign, for example, in this case, we assign the size to the size data member, and top equal to -1 to this top of the stack. And then we allocate memory to the array with the help of malloc function. We allocate size to the array with the help of this size of, and according to what is the size of this int. Okay, so we allocate memory to the array, and then we finally return the stack. So that is why you see the return type of this is struct stack pointer. Okay, so this is how you declare when you're dealing with array implementation. Now let's try to understand the implementation of push method in stack using arrays. So the first thing that you see in this push method is the array that we have passed and the item. So now let's suppose this is an array. I have written it in this way. So the element that we are going to push is obviously, let's suppose this is 5. Now we are going to push a 5. Now next time around we are going to push a 10. Now next time around we are going to push, let's suppose 15. So we have a pointer that is pointing to -1 at the starting, and as soon as we are going to insert it, right, we're going to insert it, we're going to update our top, right? So it will be from -1 to 0. So that is what we are doing. So we have the stack, and in that stack we are going to insert this in array, and we are going to update first the pointer, that is this top that is present in the stack, right? And we're going to pre-increment it. First we're going to pre-increment it. That means in -1, from -1 it will first go to 0, and then we access this ARR of 0, right? And then we insert this item, that is 5, in that particular array. Similarly, when we next time around we're going to insert 10, we're going to pre-increment, because this time around the value of top is 0. The next time around we're going to increment it, which will be ARR of 1. We're going to store this. So top will be pointing to 1, then top will be pointing to 2, right? So it will be something like this. So we have 5, 10, and 15, and so on, right? This will be 0 to 0, 1, and the top will be here. So let's suppose the size of this array is 4, and next time around when you're pushing, right, when you're pushing this another element in there, let's suppose 20, then it will be 3. So the next time around when you are inserting the element, right, when you are trying to insert this element, that is, let's suppose you are passing in 25 and you're trying to insert, but the occupancy of this array is full. So we check if is full, that if this stack is full or not. Yes it is, then we return from this function. Okay, so we will see how to implement this full method, but right now you can think of it as a pointer which does not allow us to go exceed the limit of this array in terms of storing the elements. Okay, so this is how you implement push using arrays. Okay, so now let's move ahead and try to implement pop. So now you have the stack available, right? Let's suppose you have the stack available, and the first element, that is their top, will be obviously pointing to this. So as if you can observe carefully the pointer that we are just updating, so whole operation, whole of this function is executed in constant amount of time, because we are not traversing anything, we are just updating our top, that's it. Similarly, in pop we have the top that is pointing to the top element of the stack. So we need to keep this thing in mind, that we operate this stack in last in first out manner. So the last element in was 20, right? And this will be the first element that is out. Okay, so top is pointing to this location. Let's suppose, let me name this as 3. Okay, so now what we are going to do, we are going to pick first, we are going to access this top. Okay, so the top will be 3, so ARR of 3, and then we are going to return that ARR of 3. So 20 has been returned. So that is why you see the return type of this pop as int, and we are passing in the array. Okay, as an argument. So 20 is returned, and we'll see what we are going to do with this. Maybe we will print it. Okay. So we're going to see what we are going to do with this 20. For now, let's suppose that we're going to print it. So we are printing this 20 in the main method, and we are then decrementing our top. So this is a post decrement. Okay. So we're going to decrement after this whole thing is O. So it is pointing to this. So this 20 will be still there. We are basically overriding it. Okay. So then top will be here at 2. So again, we are going to remove this. We are going to print 15 in the main. Then top will be pointing to 1. Then we are going to print 10. Then finally, we are going to print, we have top at 0th location, a 0th index. We are going to print 5 in the main method. Then top will be at -1 in the next step. Now, next time around, when we are trying to delete an element, but there is no element, we check if is empty condition. Obviously, we are checking it throughout when we are performing these operations, right? Whenever we are performing pop operation, we're going to check first this condition. So next time around, unless up to this case, we're not what executing this if block, right? But we are simply returning the value with the help of this method, this statement. Okay. Now this time around, we check if this stack is empty. Yes, it is, right? At that time we return -1, and then maybe in the main method we signify if we have returned -1, then we can put a message that okay, we cannot delete any elements, the stack is empty. So this is how you implement your pop method. Now, obviously, there are two things, right? You need to see what how to implement is empty, and in the earlier push method, you need to see how to implement is full. Now let's move ahead and see how to implement is full. So basically, is full is used to keep the track. Okay, if top, whatever is at top, whatever is the current position of top when we are inserting the elements, if it is equal to the size -1, that is the actual size of this array. Obviously, this array will have some size when we are declaring this and initializing this in the structure. Okay. At that time, let's suppose we have defined this array as 100. Now, the size -100 is 99 because we know indexing starts from 0. Now, if our top is at also 99th index and we are storing the element, so this time around, both of these are 99 and 99. This time around, these are equal. So we return true, obviously, right? So if this is full, we will return yes, it is full. So we will return true. Okay, so since both of these are equal, so we return true, and this in this case we return 1. Okay, so because we are returning, the return type is int, so we are returning 1, and later on in the main method we will do something. So this is the condition when 99 is equal to 99. In this case, when we have the array as 100, the size of the array is 100. So this time around we can easily detect or depict and say that okay, our array is full, we cannot insert any more elements. So this is the condition of this is full is condition of overflow. Okay, this is the condition when you check okay, is our array full? Yes, it is. This is the condition, and this condition is known as overflow. Okay, now let's see how to implement is empty. So in this we are simply going to check if top is equal to -1. If top is equal to -1, that means we are not having any elements in the stack, and we are going to delete something from this, it is not possible because there are no elements. So if that is the case, we are going to return 1 and saying that okay, this is the function is empty is returning 1. That means the stack is empty, and we can put a message saying that okay, we cannot delete any elements. And this condition of is empty, and whenever you're trying to delete an element from an empty stack, and this condition is known as underflow. Okay, so now let's try to understand how to implement peak. So obviously, when you talk about peak, we are not going to remove anything, or we are not going to override in this case. When we are talking about implementation using arrays, we are simply we have passed in the array and we are checking if this is empty, then peak is not possible, obviously, right? At that time, we will returning this int min, which is the minimum value of the integer. Okay, so if there is an element in the stack, right? At that time, what we are going to do, we're going to just return the value that is at the top of the stack. So we access the top, that is, let's suppose in this case, let's suppose this is at index 5. So we access ARR of 5, that is with the help of this stack operator, obviously, stack variable. Mm. and we are going to return that value. So the return value is integer, so that is why you see the return type is integer, and we're not going to overwrite it. Still our top will be at this position, because we are just taking a peek at the stack. Okay, we are just looking at which element is at the top of the stack. That's it. Okay, so we are going to return it, and that's it. Okay, so now let's see how to implement these functions in code blocks. So now let's see the implementation of stack using arrays. So you have this structure over here, and in this you have top, that is used to, that's a pointer, and then the unsigned size of the array, and then we are going to have this array inside the structure. Done. And plus we have these libraries so that we don't have to explicitly create everything from the scratch. Okay, so then we are going to create this method which is used to create. We have already seen it in the declaration and initialization part, wherein we are just initializing the stack. We are just initializing our size, top, and the array with the size, and then finally we are returning the stack. So this create method is already covered. So then what happens in full, whenever we are checking if the size is full or not, if the array exceed whenever the size of the array is maximum, that is if the size of the array is 100 and we are at 99th location, the top is at 99th location, and obviously we check it with the size of the array, which is 99, because indexing starts from 0. If 99 is equal to 99, that means this is the full condition, our stack is full. Now if top is at -1, that means our stack is empty, so we can have this message printed. Okay, this empty. Right now we cannot delete anything from our stack because there is no element in the stack. So this is full and is empty are these two methods. Then we have this push method, wherein first we check if can we push an element in the stack or not. We check for the is full condition. If yes, then we insert the value, that is this item. And in pop, we will first check can we remove anything from the stack. We check is empty condition, because if there are no elements in the stack, we cannot delete anything, right? Then finally we have this method, peek method, wherein we are just peeking the first element in the stack, that is top of the stack, and that's it. We are not going to change the top, that is we are not going to change the top of the stack. It will remain as it is. Okay, we're just peeking. And then we have this main method. In this main method, we are having this value, which is used to insert the value in the stack, and then the n, which is our choice. Okay, so we are again going to create a menu, and in this menu, we have push, pop, peek, is empty, exit, and then we are going to enter our choice. So if we picked anything from 1 to 5, then we are going to implement these functions one by one. So we have this scanf statement wherein you ask the user enter your choice. If you pressed 1, we are going to call the push function. If you press 2, we are going to call the pop function. If you pressed 3, we are going to call what is peak of the stack. We will call peak function. If we press 4, we are going to see is our stack empty or not. And finally, if you press 5, we are going to exit out of the program. And if there are no state, if you press something which is not which is not in this range from 1 to 5, right, including 1 and 5, then we have the default case wherein you will get the output as wrong message, and then you will break out of the program. And then it will also prompt you a message wherein it asks you, do you want to continue or not? If you say Y, that means yes. If you press Y from the keyboard, it will still continue. Okay, so this is the menu that we have created. Okay, now let's minimize this also, and now let's try to run this program. So we'll do build and run, and this is our menu. Okay, so now in this we first ask the user to enter his choice. Now let's suppose we pressed 1. Okay, now the user says okay, we are going to push. So now let's suppose we are going to push 10. So this is a stack. Okay, do you want to continue? Press Y in lowercase. Okay, then again we are going to push, press 1. Do you want to, whatever is the value, let's suppose it is 20. So 20 is the top. Okay, we have 10, we have 20. This is a stack. Okay, do you want to continue? Yes. We are going to push into your choice. We are going to again push. Okay, and let's suppose this time around we are going to push 30. Okay, do you want to continue? Yes. Now we have 10, 20 and 30. Do you want to check the peak of the stack? Yes, it should be 30. So let's press your choice 3. you get top element as 30, which is right. Okay. Now we are not removing it, we are just speaking it. Okay. So now if you want to check whether whether your stack is empty or not, what you're going to uh, use, we are going to say yes. First we are going to say continue, and then we will check if our stack is empty or not. So we are going to call is empty function, and we'll say is it is zero, that means it is not, it is false. Okay, that zero represents false. Okay, it is not empty because we have elements in the stack. Okay, so now let's pop the element. Since we have 10, 20, 30, so the element that we should be able to pop should be 30. So let's press 30, we should get well, let's press 2 and we got 30. Again, let's pop the element. And this time around again let's pop. Okay, enter your choice, let's pop. We will get, this time around we will get 20. Yes, correct. Okay, now the last pop, and we press 2, we get 10. Now, yeah, would you want to continue? Yes. Now this time around, let's see, is our stack empty or not? Let's press 4. Yes, we got true. Our stack is empty. Okay. So this is how you play around this. And now if you want to exit, you can press 5, or if you press anything that is there apart from Y, it will just break out of the loop. Okay. This is how break out the switch case. Okay, so that we are done with this implementation. So in this way, we have just implemented all the functions that were there, right? First, we implemented what push, then we implemented pop, then we implemented is empty, then we implemented what is empty and is full, then we saw peak. Okay, with this, we implemented all these functions using C in code blocks. Now let's try to understand the implementation of stack using linked list. Now, before we do that, let's try to understand the declaration and initialization when we are implementing our stack using linked list. So we create a node, obviously, and that node will contain two things. What are those two things? The data and the next. Now this next will be nothing but the pointer which is pointing to the node, that is the next node. Obviously, it will be of the type node. So this is why this is a self-referencing pointer, because it is pointing to something which is of same type as it is. Okay. And plus we have the data part wherein we enter our data. Plus we have this variable which is of type struct, which is of type node. And finally, what we do, we create this temporary node. Let's suppose we are creating this node here in this case, right? Let's name it tmp. And then what we are doing with the help of malloc, we are allocating memory, and we are obviously calculating the size and then locating memory and then typecasting it. And then we are inserting the value as 5. And then the next part of it, which is this, this is the next part, and this is the data part. And then what we are doing, we are locating null to this because there is no node which this particular node is pointing. Okay, so that is why it is null. So this is how you declare and initialize your node while you're implementing stack using linked list. Now let's try to understand push implementation using linked list in stack. So if you can see that this push method, we are passing in the argument as the element that we want to push. Now, before moving into the implementation, one thing should be clear, that whenever we are implementing push, right, in any, either in arrays or in linked list, one thing that we have to keep in mind, that this push operation should take constant amount of time. Now in linked list, we have already seen that if we want to insert at the end, right, we let's suppose we have this set of elements. Let's suppose 10, 20, 30, 40, and 50. Now we want to insert this in a stack. If we insert it in such a way that we are inserting 10, then after that we are inserting 20 in a linked list, right? 30, then 40, then 50. Now to insert this 50, we are taking how many, we are traversing through all these elements and then pushing it at the end, which is nothing but insertion at the end, right? When we talk about when we talk about insertion in a linked list, we have already seen this insertion at the end and insertion at the beginning, right? So if we use this insertion at the end, we are traversing through all the elements and we are implementing this push function in a linear time, that is big O of n, which is not correct. So in order to use the linked list implementation, we need to implement this push in a constant amount of time, which can be done when we use insertion at beginning. Insertion at beginning. Okay, so let's clear the screen and let's see how it's done. So we have this element in place. We have called this push function in the main method, that is our driver method. And then what we have done, we have created a node, right, with the help of malloc. And now what we are doing, we are inserting data in the element. We are inserting element in the data part of the node. So this is tmp, and obviously this will have some address that suppose that is 1000. Okay, so now what we are doing, we are storing the element which is 10. Okay, now again, whenever we are inserting an element at the beginning, two cases are there, right? We have already seen them. First, that we have no element in the linked list, that is our header or head node is at head, that is the pointer that is pointing to the first node is null, or it is having some address. It can be one node or multiple nodes, it doesn't matter. Okay, so in this case, let's suppose that there is no node. At that time, p will be null, that is our head, so it will be null. P is the head and it is null. So then what we will do, we'll just update our p to temp. So p is now this temp, and that's it. Okay, and we are also inserting, we are also initializing this next part to null because there are no such nodes. Okay, so we have inserted, we have implemented this push operation in a constant amount of time. Done. Now what if there are multiple nodes? Okay, let's clear out the screen, and there are multiple nodes. Let's suppose there are two nodes already, and one is containing 10, and this is 20, and this is 1000. The address, this is 2000, and p is pointing to this, that is our head node, and this will contain 2000, and this is null. So this is our linked list that is already present. Now we want to implement push operation. If we insert here, this is not correct because it will take big of n time. Now we want to insert something that is at the beginning. So we will check, okay, we first create the node, that is this. We create it with the help of this malloc function. We allocated its memory, and then we inserted the data. Let's suppose data is 5 and we have address as 5000. Okay, so this is our temp. So what we did, we insert the value. So these two steps are done. Then we checked if p is null. No, is p is not null. This will not be executed. Then what we'll do, we'll check, we'll insert the value in temps next as p. So temps next is this, which is right now empty, and we will insert p in it. So p is 1000. So here you have your link. Okay, so this is insertion at the beginning in a constant amount of time. Okay, so push is implemented in a constant amount of time. Now after that, what we do, we'll just update our p, that is our update our head, and it is pointing to the first node. Done. So this is how you implement push operation using linked list, which is nothing but insertion. Insert your element at the beginning, okay, because it takes constant amount of time, and we need to keep this push operation in constant, or implement this push operation in constant amount of time. Now let's try to understand implementation of pop method in stack using linked list. So we have already seen that when we want to delete an element from, or when we want to delete a node from linked list, we have two operations, right? Insertion, or we can say not insertion, deletion, right? Deletion at beginning and deletion at the end. Now, since we want to perform this operation in a constant amount of time, so deletion at end is out of the picture. Why? Because if we are deleting the node at the end, we need to traverse all these nodes to reach here, which takes big of n time in worst case scenario, right? So this is out of the picture. Now we will be implementing this pop method using the same approach that we did in deletion at beginning. So let's see how to do it. So the scenario remains same. We are not going to change our head node, that will remain as it is. So there are again two cases, null when we cannot delete an element and or the node, and wherein we can delete the node, that is the first node. Okay, and always we will delete the first node. Okay, so when we talk about this first case, when we don't have any elements, right, and there are no nodes in the linked list, that will be the case of underflow, right? We are trying to delete an element in the linked list, when we don't have any element in the linked list or any node in the linked list, that is not possible. So if P is null, that is if our head is null, we can print no element to be deleted. There is no element that we can delete. Now if P is not null, that means head or P is pointing to this node, that means 1000, let's suppose. So at that time, what we are going to do, we are just going to put, or we can just update our P to P's next, which is nothing but this node. That will be, let's suppose, 2000 here. So P will be pointing to this. That's it. We have removed this. Okay. This is how you delete or perform pop operation in stack. Okay. And obviously, if we are changing, or we can use this temp when we have to traverse. Okay. So this is how you implement pop using what linked list. Now let's try to understand is full. So now think about it in this way, right? In arrays, when we implemented this is full method, we were looking at the size of the array, right? If size of the array is 99, if size of the array is 100, and the last element will be stored at 99, right? Because indexing starts from 0. So we were checking if 99 is equal to the wherein the top is also at 99. So this is a condition of overflow. Now when we talk about linked list, this overflow is present only in arrays because of the fixed size, that is the nature of the array. We have to define a size and it is having a fixed size. This overflow condition is possible only in that case, right? Because if we talk about linked list, right, since it is dynamic in nature, we can add as many nodes as we want, as we have, as our application grows, or if we want to insert many elements, right? So is full condition is not applicable when we are implementing stack using linked list. Now what about is empty? Yes, this will be the scenario, right? If our stack is empty, right, that means if there are no nodes available in the linked list, at that time P will be equal to null. So we'll say stack is empty, else we will say our stack is not empty. That's it. Okay, let's move ahead. If we want to peek the element, right, if we want to take a peek at the element that is present at the first, that is present at the head node, or we can say the P node. So we are just peeking at the top of the stack, right, that we just saw in the array implementation as well. So we are just looking at this. So we just print whatever is in the heads data. That is what is P, right? This is the first element. This is the top of the stack, right? This first element, because we are implementing it insertion at beginning, like we did in that, right? So just like we implemented insertion at beginning, we have our top at this location, that is at the first, and again this will be a constant operation, right? So we are just looking at the top of the stack, that is head nodes next or P nodes data. That's it. If there is an element, there will be this is the case wherein the stack is not empty, and if there is no if our stack is empty, that means if P is null, right? If P is null, at that time we will return -1. That's it. Okay. And you can just use this condition, or you can just implement it in a different way, just by returning if P is null, then you return -1 or anything like that. Else you can say that if stack is empty, then you return 0, else return 1, or the vice versa. If you want to say that is stack empty true, you return 1, or else return 0 instead of these printf statements. Okay, it depends on implementation. Okay, so this is your peak operation, and this is also happening in a constant amount of time. Now if you want to display all the elements that are present in the linked list, this is similar to what we have already seen. So you have this temporary variable because you don't want to change the head node, that is P. So you have this temp also pointing to the head. Then you will traverse one by one. You print out the data that is there. So you will be printing out the stack that is there, right? The top of the stack is this 10, then 20, then 30, then 40, then 50. So you will represent this in this manner. So this top is the top of the stack. Okay, so this is how you display your elements. Now let's see the implementation of all these methods in code blocks using C. So now we have a structure that is data and the next, because we are implementing it using linked list, right? So we have these set of temporary variables that we will be using, and we are declaring it globally so that we don't have to pass every time. So we have this method, right? Insert is there and delete is there. Let's just write this again. So let's just save these files. So these are few methods that we will be implementing: insert, display, delete, and is empty. Okay, done. Then we have, let's minimize this as well. So then we have our driver function, that is our main function. We have this menu in place wherein we are going to use push, pop, is empty, display, and exit, and we will enter our choice. We'll ask the user to enter his choice, and we will be storing it in n. So this is why we have declared this n over here. Then the value is for inserting the value. So this is the head node, which is null. Okay, this p. We have in switch place that takes an n as an argument, which is nothing but the choice, and 1 represents, if you press 1, that means you will be entering value inside the stack, and you will just ask the user to enter that value. So we have used that val which we declared earlier over here. Okay, then we pass in this to an insert, which is nothing but insertion at beginning, and the same, that delete function gets called, which is nothing but deletion at beginning, because we want to perform all these operations in a constant amount of time. Then we have case 3, which is for empty, to check if the stack is empty or not. Then we have this display method over here to display all the elements. Then exit, to exit will be exiting from the program, and if we enter anything apart from 1 to 5, that will be wrong choice and we will break out of the program. And we will also prompt the user the message, do you want to continue or not? If he says Y, that means he presses Y in his key on his keyboard, then we will continue. Else if we press anything apart from that Y, we'll get out of the program. Okay, we have this insert function over here, which is nothing but insertion at beginning, wherein we will check both these cases, wherein if p is equal to null, that is if there are no elements in the stack, yes, you can see it in the stack or in the linked list. Else we will traverse and we will update our this head node. Okay, it's because this is insertion at beginning, right? Done. And we also pass the element that we want to insert. Then deletion, again same thing, we will print the data. Else we will print, if the underflow condition is there, we will print that no data is there is no element in the stack. Then is empty, we are just checking if the stack is empty. We are using this implementation where p is equal to null, and if that is equal to null, then we say stack is empty, else stack is not empty. Then display function, we are traversing through the linked list, and that's it. Okay, one by one using this temporary variable temp. Okay, done. So these are few methods, and this is our driver method. Okay, now let's run this program. Let's build and run this. So you see we have our menu in place, and now it is asking for the user to enter his choice. Okay, so let's say we want to push the element. Okay, we pressed 1. Now which element do you want to push? Because this will be the last element in the stack. Let's suppose we are pushing 40. Now he says, do you want to continue? Yes, press Y. Okay, then again we want to push it. Okay, we want to push another element. Let's suppose 30. Okay, and then we want to continue. Yes, then again we want to push, press 1, and then we want to push 20. Do you want to continue? Yes, we want to continue. We are going to push again, and this time around we push 10. Now do you want to continue? Yes. Okay, so now what is happening? 40, then about 30, 20, and 10. So we have a stack in which 10 is the top element. Okay, now if we want to pop, what should be what is the element that we should be able to pop? Is the 10. Now let's see, we press 2, we should get the output as 10. We got the output, element is deleted, that is 10. Okay, now we want to check if the stack is empty, since there are elements, right? 20, 30, and 40 in the stack. 20, 30, 40 in this manner. So we want to check if this is if there is if the stack is empty or not. So let's say 3. Let's enter the choice 3. He says stack is not empty, which is absolutely correct. So let's press Y and say continue, and now let's try to pop again. So 20 is deleted, and now finally let's try to display all the elements. So 10 was earlier there, we popped it. 20 was there, we popped it. So now we are left with 30 and 40. Okay, so 30, 40 should be printed, okay, in the form of stack. Okay, now let's try to display that. Let's see 4, Let's press enter. So 30, 40 is the stack. Do you want to continue? Yes. Now let's press 5 to exit our program. Press 5 and we are out of the program. Press any key to continue so that we are out of this prompt. Okay, done. So now let's go back. So in this way, we implemented push, we implemented for, we implemented is empty, and we implemented push pop was there, is empty was there. We implemented display. Okay, so these are some functions that we implemented in the code blocks using C. Is it possible, once more I will ask you this question, is it possible for us to have is full condition in linked list? No, because of its dynamic nature, that the size is dynamic, so this condition, overflow condition, will never be there, but underflow will still remain. That is nothing but if you want to delete an element but the stack is empty, or you don't have anything in the linked list. Okay, now let's talk about the advantages and disadvantages of stack. If you talk about advantages, it maintains data in a LIFO order, right? The data is maintained in a LIFO order. That means the last element that is there in the stack is readily available for us to use. So one of the readily available, right? So one of the applications of using stack is it can be used to evaluate expressions, right? Therein we require this feature, that is LIFO, right? And all the operations that are performed in stack, like push, pop, and then is empty, and then pick. All these operations take constant amount of time, which is very important while you're playing around with competitive programming or while you're doing competitive programming. At that time, these are very important that you program in the most efficient way. Programming in most efficient way is important and it is very crucial for your selection, right, in competitive programming. So all the since all the operations are performed in a constant amount of time, so these the stack is used oftenly when you are doing competitive programming. Now, what are the disadvantages? Since we are restricted, right? There's a restriction that we can only add and remove elements from top of the stack. So this is one restriction that is there. Thus, it is not very much flexible, right? It is not flexible. If you talk about the flexibility of how we are storing data in the stack, it's not very much flexible. So these are the disadvantages of using stack. Now let's try to understand queue linear data structure. What is queue? Queue is a linear data structure. That means all the elements in the queue are stored in linear fashion. Now, it follows a principle of FIFO. That means there's a restriction that whatever is the first item in is the first item that is to be out. Okay, so now let's try to make a queue. And let's suppose you are in a queue and you're waiting for a movie. You're waiting for a movie ticket to buy. Okay, so there is one person, then there is another person, right? So these are few persons here, right? And you're waiting in a queue. So now the first person who is in the queue will be the first person who will get his ticket, right? Makes sense, right? So he will be the guy who will get his movie ticket first and he will be out of the queue. Then the next person who is in the queue is the next person who will get his tickets, right? And let's suppose a new person comes in, he's not going to go ahead from this person, rather he is going to go behind this person. Then the next person comes, he will go after this person, and in the same way. So this is nothing but a FIFO principle. Okay, the first person in is the first person out. Okay, now insertion will always take place from the rear end. Okay, and if you talk about deletion, it will always take place from the front end. Okay, so this is our front end and this is our rear. Cool. So for examples, buying the tickets from the counter, or it can be a movie ticket, or it can be a bus station. You are in front of a bus station trying to get tickets for your bus, right? These are some examples. Now there are four major operations when you talk about queue. What are those major operations? Let me clear my screen. So NQ. So you are going to insert an element in the queue. This is what you mean by NQ. DQ, you are going to delete an element, okay, from the queue. Then peek first, that you're going to peek the first element that is in the queue. And peek last means that you're going to peek the last element that is in the queue. So you will have two pointers. One is friend and another is where. And with the help of these pointers, you're going to enqueue, dequeue, peek first, peek last. You're going to perform these operations. Now, one major advantage of these operations, these four operations, is that all of these operations are performed in a constant amount of time. That means the time complexity of performing these operations is O of 1. So that is why when you talk about competitive programming, Q is most commonly used data structure because of these things, right? Because of its time complexity, right? You're able to perform your operations in a constant amount of time. Now let's talk about applications of queue. So it is used in scheduling algorithms of the operating system, like first in, first out scheduling algorithm is there, round robin is there, and we have multi-level queue that is there. In all these algorithms, queue is used, okay, for storing the data or the processes. It's also used in maintaining playlists. Like when you have a playlist, let's suppose you have 10 songs in a queue, right? And after one song, the next song which is in the queue will be played, and it goes on for like this, right? So for maintaining a playlist, again, a queue is used. It's also used in interrupt handling. Let me take an example here. You know the process state diagram of operating system. So it is also used at that time. So when you have an interrupt and therein, if your process is being executed at that time, that process is preempted out and it is stored in a queue. Now, the next time when this priority or this interrupt is handled, once it is done, then it starts picking up the process which was in the queue and starts executing that. In the meanwhile, if there are some other processes, that those processes will also be in the queue. So a queue is maintained, and once the interrupt is handled, they will start taking out that process that was being executed earlier and executes it and completes its execution and terminates the process. So it is also used in interrupt handling. Now let's try to implement queue using arrays. So let's first see the declaration and initialization using arrays. So we have defined a structure here and named it queue. And in this structure, we have three data members of type integer. That is, first is friend for keeping the track of the friend and from which we will delete our elements. And there is rear from which, with the help of which we can insert the elements in the queue. Then there is size of the array. Obviously, we are implementing it with the help of array. So we will be having the size. So we have then unsigned actual size of the array, right? This is the actual size of the array, and this is the size wherein we will keep the track of how many elements are there in the array. Then we have the array, okay? And then this is our structure, okay? Then how would we create? We will call this create queue method from our driver method. Driver method means the main method. And therein we will pass the actual size of the array. And then we will allocate size or allocate memory to the queue with the help of malloc function, wherein we calculate first the size of the structure, which is this queue, right? Once we are done with that, then we will typecast it in the same. And then we will assign this to queue. Then what we will do, we'll assign the actual size to the queue. Then we will initialize our friend to the size of the queue, which is equal to 0. Right now, there are no elements in the queue, so the size of the queue is 0. That means the friend will be at the starting, which is 0th index, right? And then what we will do, we will assign the value to the rear side, which is actual size of the array. Let's suppose the size of the array is 100 and we are subtracting 1 because indexing starts from 0. So our rear is initialized, our friend is initialized, our actual size of the queue is also initialized. Then we allocate memory to the array. Again, we will calculate the size with the help of size of operator and then allocate memory and then typecast it to the type integer. And then finally what we do, we'll return this queue. So this is the declaration and initialization when we are implementing queue with the help of array. Now let's try to implement queue using linked list. First, we will understand the declaration and initialization. So obviously we are using linked list, so there should be a structure of the node, right? So we are defining a structure that is of the node, and herein we will have two data members. One is the data part and another is the next. With this next can is used to store the addresses, right? This stores the address of the next node that is connected to it, which will be obviously of type node. So that is why we have this struct node, which is this next is a self-referencing pointer, because this next is also pointing to the node, which is of type node. And plus we have the data part wherein we are going to store our integer values. Plus we have this temporary variable, which is of type node. Plus, what we will do, we will allocate the memory with the help of this malloc function, and we calculate the size of the node, that is the structured node, and then we typecast it, and then this temp will be pointing to something like this. This will be the node, and it is named as temp, and it will have some address, let's suppose 1000, and this will have data part and the next part. Now we are allocating, or we are assigning 5 to the data part, that is this 5, and we are assigning null to the next part. So this is our node, and this is currently temp is pointing to this node. Okay. So in this way, we understood the declaration and initialization of linked list and how we are going to implement queue using linked list. Now let's try to understand the implementation of enqueue operation in a queue using arrays. So this is an enqueue function that we have over here. And in this we have passed in the array and the item that we want to insert. Now before we move on to this enqueue, let's try to understand what this enqueue operation is. It is nothing but if you want to insert an element in the queue, right? And right now we are implementing it using arrays. So we want to insert an element. That operation is known as enqueue, and we need to keep this thing in mind, that we perform this operation in a constant amount of time. Now let's try to understand what is this enqueue operation. So first we are going to check if the queue is full or not. Now why this condition is important? Because this is the condition of overflow. That means we want to check if the array, let's suppose we have this array and the last index is 99. That means it starts from 0 to 99. That means the size of the array is 100. Now we want to check if the queue that we have created is full or not. So we check if the elements that are present in the queue is equal to this 99. That means the actual size of the queue and the actual size of the array, are these equal? At that time we cannot insert any more item in the queue. So this is the condition of overflow. Now let's erase all these things. Now let's see what is the next thing that we are doing. So since both of these front and rear are at -1, as we have seen in the declaration and initialization part, right? So this is the 0th index, and now this is the array, and let's suppose the last index is 99. So now when we are trying to insert an item in this array, the first thing that we are going to do, we are going to, obviously the enqueue will take place from the rear end, so we are going to update the rear. So now rear will be pointing to this index 0, and we inserted this element in the array, that is this item that we inserted in this queue is 5. Let's suppose we passed in 5. So 5 is inserted. Right now these two steps are done, and this condition is false because our queue is right now empty. Then what we are doing, we are now, this helps us to keep the track of the number of items that are there in this queue, because we are removing, and then we also want to keep the track, since this size helps us to keep the track. Let's suppose we are over here and this is the 50th index, so we want to keep the track. Okay, still we can insert elements that are less than, obviously the index is 50. Right now the size is 50, and we can insert elements up to 99 size. Okay, so this helps us to keep the track of that. So this is the actual size, this is the actual size of the queue, and this that actual size of, then that is different. Okay, this size is actual size of queue, and when we pass in the actual size, that is the size of the array. Okay, these two are different things. Then what we are doing now, since when we are inserting the element first time, at that time we want to update the front as well, because front is the guy who is responsible for deletion. So we want to keep him in track that okay, once we have inserted the first element, we want to update him. Okay, this is the first point where this is the point from which you can start deleting the in the queue. Okay, you can start deletion. So at that time, if it is at -1, we'll update it. Okay, the front is also at this position, that is 0th index. So both front and rear are at 0. Okay, when the queue was empty, and then we printed out this item. Okay, we have inserted this item that is 5 in the queue. Now let's suppose we are doing it the second time. Now let's clear all this thing. Now let's suppose we have this 5 inserted and front and rear are both at this 0th index. Now the next time, is our queue empty? No, it is not. Now what we are going to do, we are going to update our rear. Now rear will be pointing to this index, that is 1. And then we insert the item. Let's suppose we are trying to insert 10. We have inserted the item, so these two steps are also done. Then we update our size, that is earlier size was 1 and now size is 2. So obviously the array size will remain the same, that is 99. Okay, not the 99 but 0 plus 9, that means the size, actual size of the array is 100 in this case. Okay, so now q is not -1, so we are not going to, the friend is not equal to -1, because now friend, earlier we updated it and friend was 0, since friend is binding to the 0th index. So we are not going to update our friend, because this only takes place when we are inserting element in the array, in the queue, or you can say the array implementation, right? We are inserting that element in the queue the first time, for the first time. Okay, at that time this condition, this if will be executed. Okay, done. Then we print out the item, that is 10 was enqueued in the queue. Done. So this is the implementation of enqueue. Now let's see the implementation of dequeue. Now dequeue, now one more thing before we shift to dequeue, one more thing that is there. So this is done, this whole operation is done in constant amount of time. Why? Because we have the track of both of these indexes, right? So obviously front is not required right now, but rear is updating all the time, and we have direct access to this memory location. That means we only require a single unit of operation. That is for the same reason the enqueue operation is executed in a constant amount of time. Okay, now let's move ahead and see the dequeue. So dequeue is used for, or this operation is known as deletion in the queue. Okay, now we have already placed our friend. Now let's see what are the things that we are going to implement in this dequeue method. So obviously we are going to pass the array, right? Let's suppose we have this array. We will take care of both the conditions when both front and rear are at this position, and then when front is at this position and rear is somewhere, and also when our array is empty. Okay, then at that time both front and rear are at -1. Okay, done. So now obviously we will be returning the item that we have deleted. Okay, so now let's first check if this condition holds or not. So we are going to check is empty condition. That means if this is the scenario at that time, we are going to return int minimum. That is the minimum value of integer. Okay, or you can return any arbitrary value. Okay, so this condition is checked, right? This case is checked. Now after that, what we are going to do, we are going, now we know for the fact that there is at least one or more than one item in the queue. Okay, so now we can delete, we can perform deletion. So the next thing is that we are going to pick the element with the help of this friend operator and insert it into this item, that is the temporary value we are using. So let's suppose 10 is here and 10 is here. Okay, and then we have 20, then we have 30. Okay, done. So in either of these cases, this case 1, case 2, case 3 is solved, right? So case 1 or case 2, what we are going to do, we are going to pick the element that is present at index 0 or at index that is front. The index that is present in the front is the element we are going to pick and insert it, or store its value in this item. Okay, so that we can return it. Okay, that's the for this purpose. Okay, so now if front and rear are at equal positions, that means in this case is happened, right? That means there is no further item in the queue, because it is obvious, right? Since front and rear are at this position, that means there is only single item in the queue. Done. So what we will do, we'll update our front and rear both to -1. That means this case, okay, when our item or when there were no items in the queue. Done. So we updated it. Done. Now, what if this is not the case? What if this is the case, right? Let's suppose rear is here. Okay, 40. So now if that is the case, what we are going to do? We are just going to update our front to this position. That's it. And also reduce in any of these cases, right, except for this one, we are going to reduce the size because this is if block, this is else block, and this is executed anyways, right? Either this case is executed or this case is executed. This case is entirely different. This is done by this if, right? Now, if in any of these cases, we are going to execute this queue size and queue size -1. That means we will be reducing the size of the queue. Earlier, we had 4 items. In this case, we had 4 items in the size. That means size is 4. Now we have 3 items. So because one item is removed. Okay. In this case, we are also having 1 item in the queue. That means size was 1. Now it is 0. We are decrementing. Okay. This is how you perform dequeue operation. Now, one more thing is that since we have the pointer that is front, which is pointing to the index that or pointing to the element that we want to delete. So again, this operation is performed in a constant amount of time. That is the time complexity in the worst case is big O of 1. That is constant. Now let's see is full condition. That is the overflow condition, right? That we checked while inserting the element. So now if the queue size, that is the size of the queue, which helps us to keep the track of the elements that are present in the queue, if that size is equal to the actual size, right? That 100, the actual size of the array, it is equal to the size that we have, right? That is used to keep the track of the elements that are present there, right? If this is the case, that means we cannot insert any elements any further. We cannot insert any elements, right? Or it should be something like, or it depends upon the implementation. What have you returned? If you have inserted 99, so because indexing starts from 0, so it will be somewhere around 99 is equal to 99 because indexing starts from 0, not 100. Okay, because 0 to 99 is again 100 elements. Okay, so now what we are going to do, if this is the case, that means we cannot insert any value in the queue. This is the overflow condition, and our queue is full. Done. This is the is flow implementation, and obviously we are returning then either 0, that means the stack is not full, or if the stack is full, we will be returning 1. That's it. Okay, since the return type of this method is int. Again, if you see, this operation is performed in a constant amount of time. Now, if you want to see if your queue is empty or not, that is simple. You just check the size of the queue. That is the elements that are present in the queue, not the actual size. If that is 0, that means if size is 0, that means your queue is empty. And what we are going to return, if that is the case, you're going to return 1, else you're going to return 0. Okay, done. This is again performed in a constant amount of time, that is big O of 1. Now, what if you want to get the front element, that is the front element of the queue? This is the front and this is the rear. So it is quite obvious that you have the tracker, or the front is the pointer that is used to keep the track of the front element, and rear is the tracker or pointer that is used to keep the track of the last element. So this is the first element that is there, and this is the last element that is there. So we have these pointers available. So again, these operations will be performed in a constant amount of time, and it is simple, right? If you want to see the front, first you check if your queue is empty. If it's empty, then there will be no front element, else we are going to just return whatever is at this position, that is with the help of this front iterator or pointer. Okay, then we are just returning that value, so it will be integer. Or if the queue is empty, at that time we will return the minimum value of integer. Okay, in any ways, both of these, either this return or this return, are sending the integer value. Okay, again it is performed in a constant amount of time. Similarly, we can execute, or we can have this function that is get rear. Again, we will be having this pointer that is pointing to the last element, and we will be straight away returning that value. Again, it will be an integer, and plus we are going to check if, again, we are going to check the is empty condition to see if there are elements in the queue. Only then we will return the last element. Okay, again, this int minimum is nothing but the minimum value of the integer. Okay, if you observe carefully, again, since we have the access to this rear pointer, that is the last element is available to us, right, with the help of this rear pointer, again, this will be performed in a constant amount of time. Now let's look at the implementation of these methods in the coding blocks. Now let's see its the implementation. We have these libraries in place which are used, okay, and then we define the structure as we have declared, as I have already taught you this thing, that the declaration and initialization part, wherein we have these three pointers, front, rear, and size. This size is the size of the queue, and this is the actual size of the array. Then we have the array. So this is our structure of queue. Then we have this method create queue, wherein we are passing the actual size of the array. Okay, and then we initialize our queue with the help of this malloc function. We allocate memory, then we update our actual size of the queue, that is the actual size of the array, and we are updating our actual size. Okay, then our elements that are present in the queue are right now 0 because there are no elements in the queue. We update our rear and front pointer, we initialize our array and allocate memory according to the size that we have received in the actual size, and with the help of size of operator, we calculate the size of each byte or each integer that we have in this queue, and then we typecast it to the integer. So this is the create method, create queue method, and then we return the queue. Done. So is full is simple, that we check the size of the queue and the actual size of the array. Done. This is our is full, and we will return 0 or 1. This is done. This is also done. Okay, now let's see our enqueue, which means we will be inserting value. So we need to have one item here. Obviously we'll be checking first the overflow condition, and then we update our rear, because rear is the guy who helps us to insert the values, right? So we'll be inserting from the rear end. Then we insert the item, right? And then we check, then we update our size, because we want to keep the track of the elements that are present in the queue. Obviously the actual size will remain the same. Okay, and then if it is the first element in the queue, then we also update, at that time we update the front pointer as well, and then we prompt a message that enqueue to queue is this item, let's suppose 5. Okay, done. Then we check is empty condition, which is this size is helping us to keep the track of the items that are present in the queue. So if that is 0, that means there are no elements in the queue, right? And we return either 0 or 1 depending on that. Then we have the dequeue method, and in this we return the value. So first we check the underflow condition. That means if there are no items in the queue, at that time we cannot delete anything from the queue. Then what we do, we with the help of front, because that is the guy who helps us, or that this is the pointer which helps us to remove an element. So we pick up the element and put it in a variable that is item, and then what we do, we check if this is the only element that is present in the queue, right? If that is the case, then we update both front and rear to -1. Else what we do, we will see, okay, there are multiple elements in the queue, so at that time we will only update our front. In either of these cases, the size is reduced, so we at the end we reduce the elements that are present in the queue, that is size -1. We decrement it by 1, and then we return the item which we have stored in over here, right? The item. Done. And then we have get rear and get front. So basically we will be returning the values that are present, the first element that is with the help of this front, and the last element that is present with the help of this rear methods. Okay, front and rear. Then we have this driver function, wherein we have this value that we want to insert in the queue, and the n is the choice. Okay, then we call this create queue, and the size of the array is 1000. Then we define this menu, okay, over here, that is our menu, and in this if we press 1, 2 and 3, 4, 5, 6 and 7, if we press any of these, what we are going to do, if 1 is pressed, enqueue, dequeue is pressed when dequeue is called when 2 is pressed, 3 is for is empty, 4 is for is full, When we want to check the first element in the array, that is 5, the last is 6, and then if we want to exit, we need to press 7. Else, if any of these values, that is from 1 to 7, is not pressed, we will prompt a message that this is the wrong choice, please re-enter. Okay, so now what we also prompt the user that please enter your choice, right, from 1 to 7. He enters something that is stored in the end, and then we have the switch case, wherein depending on 1, if 1 is pressed, we call what, enqueue. If 2 is pressed, we call dequeue. If 3 is pressed, we call is empty. 4 is pressed, we call is full method. 5 is pressed, we call friend. 6 is pressed, we call rare. And finally, if 7 is pressed, we will exit out, or we will break out of the program. And if any of these values are not pressed, we'll prompt a message that is wrong choice. And then we also prompt a message, do you want to continue? If Y is pressed, that means yes, that means we will continue, else we will break out of the program. Now let's try to run this code and at the same time build it also. So we have this menu in place. Now let's try to enter some values. So he's saying that enter your choice. Let's suppose we want to enqueue. We press 1. Then we enter the value, that is 10 in the queue. So it gets the message is prompted 10 enqueued in the queue. Do you want to continue? Press Y. Yes, we want to continue. Press again 1 because we want to again enter value. So we enter 20. Okay, 20 is enqueued. We press Y. We again want to enqueue and we press 30. Okay, now do you want to continue? Yes. So if you think of how many elements are there, there are 10, 20 and 30 in the queue. Now let's see if our queue is empty or not. Let's call these functions. Let's see, if queue is empty, it will return 0, right? So we'll press 3 to check it. It gives the output as is empty 0. That means there are elements in the queue. Do you want to continue? Yes. Again, we press is full. We check is our queue full. Obviously, the size of the array is 1000, so we haven't entered those many values, right? So is full will also return 0. Do you want to continue? Yes. Now let's see. First, try to dequeue. So we press 2. So now earlier it was 10, 20, and 30. So we dequeued 10. So 10 will not be the first element anymore. So let's try to enter 2. So element is dequeued. Okay. Now let's continue again. Now let's see the first element. It should not be 10 because 10 has been already removed. It should be 20. So we press 5. We have 20. That is the first element. Now let's check the last element that is there, which is 6. Our choice should be 6. So the last element is obviously 30. So earlier it was 10, 20, 30. We removed 10. Then 20 is our first element. 30 is our last element. Do you want to continue? I will press any other key apart from Y. So I pressed U. So then I pressed enter. So we are out of the program. Done. So in this way, we implemented all of these operations, and all of these operations which were in queue, that is insert in the queue. Then we pressed dequeue. We implemented dequeue. Then there was get rare, get friend. That is for the first and the last element. This is for the first to check the last element in the array, and this is for checking the first element in the array. We also went through some other functions as well. Those were, if we want to see is full condition, that is the overflow condition. This was the overflow condition to check is full, and also is empty. This is used when we were trying to remove and there were no elements in there in the queue, right? This is the underflow condition. So we implemented all of these methods, and all of these methods were implemented in a constant amount of time. That is the beauty of queue. Now let's try to implement queue using linked list. First, we will understand the declaration and initialization. So obviously we are using linked list, so there should be a structure of the node, right? So we are defining a structure that is of the node, and herein we will have two data members. One is the data part and another is the next. With this next is used to store the addresses, right? This stores the address of the next node that is connected to it, which will be obviously of type node. So that is why we have this struct node, which is this next is a self-referencing pointer, because this next is also pointing to the node, which is of type node. And plus we have the data part wherein we are going to store our integer values. Plus we have this temporary variable which is of type node. Plus what we will do, we will allocate the memory with the help of this malloc function, and we calculate the size of the node, that is the structured node, and then we typecast it, and then this temp will be pointing to something like this. This will be the node and it is named as temp, and it will have some address, let's suppose 1000, and this will have data part and the next part. Now we are allocating, or we are assigning 5 to the data part, that is this 5, and we are assigning null to the next part. So this is our node, and this is currently temp is pointing to this node. Okay. So in this way, we understood the declaration and initialization of linked list and how we are going to implement queue using linked list. Now let's try to understand the implementation of enqueue operation using linked list. So again, I'll reiterate what I said when we did the array implementation of enqueue. Again, we are going to implement the enqueue operation, but this time around, we are going to use linked list. Now, keeping this thing in mind that this operation should be executed in a constant amount of time. Now, as we have already seen in the linked list part, right, wherein we did something that is known as insertion at the end. So you have this linked list, and in this linked list, you have 10, 20, 30, and 40. Now, keeping this thing in mind that queue operates in this fashion, let's suppose you have 10, 20, 30, and 40. Now, if next item arrives, it should arrive at this position, right? We are inserting from the rear end and we are deleting from the front end. Now, deletion from front end is possible in a constant amount of time because we know the head, right? Now, if you want to implement it, now let's suppose we want to implement the enqueue operation, right? And that too in a constant amount of time. But if we are implementing it using a linked list, now the next element, if we want to insert, is 40 and it should be here. Now we don't have anything with which we can keep track of this thing, right? The tail. Now what we have to do, we have to traverse one by one. We have to traverse to when we are at the position where the next part is null. Unless and until we find that next which is null, we need to traverse. So it will take a big O of n time. That means this operation is done in a linear time, big O of n. Okay. Now, obviously, we can modify it, and we can use or insert items in such a way that we are keeping the track of the tail, with which we have, if we have this tail in place, then we can easily perform this operation in a constant amount of time. But let's not go into that, and let's try to implement it in a linear way. And maybe on your own, you can try this. You can keep the track of the tail, and with which you can insert directly at the end, thus making this enqueue operation to work in a constant amount of time. Now, we are not going into that constant implementation. We are going to see the linear implementation. So it will be similar to what we have already seen, insertion at the end. The operation that we performed on linked list, that insertion at the end, we are going to do the same thing. So you have this element which you want to insert, right? And then you have created a temporary variable which is also pointing to p, that is the head node, right? This is your head, and temp is also pointing to this. We have already seen how we have defined this structure node, and in this what we are going to create a node in that we have data part and the next part. And in our data part, that is, this is also the mp1 is pointing to this new node that we just created. The data part is the element, let's suppose 5, we want to insert a 5, and the next part is null, and it will always be null because we are inserting at the end. Now there will be again two scenarios which we have already seen. One, when your head is null, and the second, when you have some items or some nodes in the linked list. It can be one, it can be many. Now, if this is the scenario where your head is null, and that time directly you go ahead and put this head node, you can point this head node to this TMP1. Thus, you are inserting at the end because in this case, you're performing it in a constant amount of time. because this is a scenario wherein your linked list was empty and this is performed in a constant amount of time. But when this is not the scenario, right, when you have 2 3 nodes, let's suppose, let me just clear it out and let me show it again how it works. So you have these nodes and this has 100 as the address, 200 and 300. This is obviously null. This, let's suppose this is 10, this is 20, this is 30, and let's suppose this is 200 and this is 300. Okay, done. This is your P. Now we are taking into consideration the second else part. Let me just change the color as well. So we are pointing this TMP because we don't want to lose the head. So we have this temporary variable of type node also pointing to this head node. Okay, then we created a new node. Let's suppose this is our new node and we want to insert 40. This might be having some address. Obviously this will be having some address, that is 400, and this is tmp1 is pointing to this, and this part is null. So these 4 steps are done. Now our P is not null, it is pointing to this node, the first node. Okay, now this part will be executed. So what we are going to do, obviously we are performing it in a linear time, so we'll be traversing to the end, right? So we are checking if tmp's next is null. What is tmp is this, is its next null? No, it is not null, it's 200. So update it, put tmp equal to tmp's next. So tmp will not be pointing to this node, now it will be pointing to this node. Again we will check, is tmp's next null? No, it is 300. Then what we are going to do, again we are going to put TMP is next into TMP. Again, now this is pointing to 30 or this node, right? So is TMP is next null? Yes, it is. So condition is true. We are out of this while loop. Now what we are going to do, we are telling him whatever is in the temp or whatever is in this temp one. So it is 400. Please go ahead and put it in temps next. Temps next is null. So 400 is inserted here. Now what is happening? This node comes in here and this is obviously null, so this will be 400. Done. So this is how you perform NQ operation. Obviously we are not implementing it the way we should, because this operation, NQ operation, is done in a linear amount of time. Since we haven't seen the implementation of linked list wherein we are keeping the track of the tail node or the last node, if you keep, while you are inserting elements in the linked list, if you keep the track of the tail, then easily you can perform this operation in a constant amount of time. Here it is done in a linear amount of time. Okay, so that is something that you can do on your own. Okay, done. So this is NQ. Now what about DQ? Obviously now dequeuing is simpler in linked list, right? Now if you want to dequeue, so obviously these will be the elements 10 20 30. If you see in this in the form of queue, so these are the elements, right? Now if you want to dequeue, you have to dequeue this because this is a friend, right? So easily you can remove this directly, and that can be also performed in a constant amount of time. Why? Because we know some operation that is there, that is deletion at beginning. So you're deleting always from the beginning, so always you have the head node that is pointing to this node, so or P in this case is pointing to this node. You can easily delete this or remove this element, right? You can perform dequeue in a constant amount of time. Now let's clear this out and let's see how it is done. So let's suppose you have again 2 scenarios, right? You have 100 over here, you have 200, you have 300, and then let me change the color. You have data part 10, this is 200, you have 20, this is 300, you have 30, and this is null. Now this is one scenario. The second scenario is, this is obviously P is pointing to this. The second scenario is, this is null and P is pointing to this. Done. Now what is happening? Since this TMP is, I think this is not required in this. Okay, so is P equal to null? In this case, yes. Then you cannot delete any elements. This is the condition for underflow. Okay, obviously you can use something like is empty, and you're checking is empty, is RQ empty or not. You can use that also. Okay, since there are no elements, so no element to be deleted. Done. But what if this is the scenario? Now here what you are going to do, first you will print whatever is in the P's data. So P's data is 10, So you are printing out, this is the element that has been deleted. Okay, you have printed it out. Then the next thing what you're doing, you are updating your head node. So it will be nothing but p is next. So p is next is 200. So this is your new node. Done. Also, you can just remove this link, right? Or therein you have to just keep a track of this, right? If you have used this, let me just clear it out. So how to remove this link as well, because obviously you might be thinking this link is still there, so you can remove it easily. So what you're going to do, just remove this. So you have this temp still pointing to this, right? You have this temp still pointing to this node. Then what you will do, temps next equal to null. Okay, so this will be null. And now this has been removed. Okay, this link is removed. Done. So this is how you perform the queue operation, and that too in a constant amount of time. Now let's move ahead. Now, is full, the function or the method that is there is full. Is this possible in a linked list? Right? In arrays we have seen, okay, if array is full, that means if the size of the array is equal to the actual size of the queue, then we say we cannot insert any element in the queue. That is, the overflow condition is always there when we implement it using arrays. But is it possible in linked list? No. Why? Because there is no such thing as static size in linked list. Linked list is a dynamic size, is of dynamic size. That means we don't specify the size. So that is why there is no overflow in the queue while we are implementing it in a linked list. Okay, so this is not possible. Is this possible? No. Okay, done. So is empty, obviously we are going to check if our queue is empty or not. So what we are going to do, if p is equal to null, that means queue is empty. Else we can say that queue is not empty, because then obviously it will be pointing to something, right? The first node in our case, this is our head, right? Done. This is empty. Now the final method that is there, we want to display whatever is in the linked list. So it is similar to what we have already seen. So we have this temporary variable. Let me just quickly draw a linked list. So we have this p and we have this temp also pointing to this. So you have 10, 20, 30 and 40. Obviously these will be having addresses that will, let me just quickly change the color and just show you. So let's suppose this is 100, this is 200, the addresses, this is 300, this is 400, and this is 100. Okay, this is 200, this is 300, and this is 400. Okay, and this is null, obviously, right? So this is your linked list. So you have tmp that is pointing to this. You will check, is tmp null? No, it is not. Print data, tmp is data, that is 10. Then put your temp pointer ahead. So temp is pointing to this now. Temp's next, right? So is temp null? No, it is 200. Print temp's data, that is 20. Move temp ahead. So temp is pointing to this. Is temp null? No, it is 300. Print temp's data, that is 30. Now next step is that put temp equal to temp's next, that is 400. Is 400 equal to null? No, it is. Is temp equal to null? No, it is 400, right? So then we print the data and then we move it ahead and put it to temps next, which is null. Then we check, is temp null? Yes, it is. We get out of the loop and we have all the elements printed. So the time complexity associated with this display method is big of n. Now let's try to implement this using code blocks, and the language we are going to implement it in is C. So now if you can see that we have these library functions over here which we have used. Then we define the structure of the node, that is data part, and the next part, which is obviously self-referencing pointer. We have also defined these variables which are of type node, so that we don't have to pass them to every function. Done. Then we have this insert, end, in, delete, from beginning, display, and is empty methods that we are going to implement. Then we have this driver method, that is our main method. Then we have this value, which is the value that we want to insert, and the n, that is the choice. Okay, so from at the start of the linked list, p is null, that is our head, and then we are creating this menu wherein we are, if we press 1 we are going to enqueue, if we press 2 we are going to dequeue, 3 is empty, 4 for displaying it, and 5 to exit. Then we enter the choice and we insert a value and we store it in n, and then we pass that n to the switch case. If we have pressed 1 and we are going to call insert at end, that is our enqueue operation, and then we are going to break out of it. If we have case 2, we are going to delete. If 3 we have entered, we are going to check is empty, 4 for display, 5 for exiting, and then we also prompt a user a message, do you want to continue? If he or she presses Y, that means yes, we want to continue. Then we are going to start this menu and start this whole process again. Now we have already seen the insert function. That means we are inserting at the end, and this is obviously taking big of end time. I also told you what is an alternative and how you can solve this problem, and so that this insertion or enqueue operation takes constant amount of time by keeping a track of what the tail node or the last node. So what we are going to do, we are creating this stem one and we are setting its data and next part. Then if it is null, then that is our head node, that is our new node. We have inserted it. And if it is if we have some elements or some nodes available, we are going to traverse, and then we are going to insert at the end. So this is insertion at the end, which is our enqueue operation, and our dequeue is obviously performing well than the insertion at end, that is our enqueue, because we are performing it in a constant amount of time, because we have an operation where we are going to delete from beginning. Okay, we are just going to delete from beginning. Then we have this is empty condition or is empty method, wherein we are going to check if our queue is empty or not. If p is equal to null, that is our head node. If it is null, we are going to say queue is empty, else we say our queue is not empty. This is our is empty condition. Then our dequeue operation, wherein we are going to delete from beginning. That is, we are going to first check if there is any element or any node available. If yes, then p will never be equal to null, right? And also I showed you that this can be removed. This is used for removing that link that we have already seen, right? So we check if p is null, if head is null, then we say this is an underflow condition, we cannot delete anything, else we will delete and print that element. Done. This is deletion, or you can say this is our dequeue operation. Then finally we will print with the help of this display method. Right over here we will print all the elements that are present in our queue. So now let's run this thing. So here we have our menu in place, and you see if we press 1 we can enqueue, if we press 2 we can dequeue, 3 to check if our queue is empty or not, 4 to display, 5 to exit. So let's press 1 and let's enqueue. So let's enqueue 10. Do you want to continue? Yes, press Y. Again we want to insert a value, that is 20. We press enter, we press Y. 3 we want to enqueue again. Yes, we press 30, insert a value 30. We press enter. Do you want to continue? Yes. Now let's try to display all the elements that are present in the queue. So there will be 10, 20 and 30. So we press 4 and we have 10, 20, 30. This is the queue. Do you want to continue? Yes. Now let's try to dequeue. So dequeue works in such a way that 10 should be removed because that is the friend, right? So we press 2 and we should get the output as 10. So 10 is element deleted is 10. Done. We want to continue? Yes. Let's try to see if the queue is empty or not. Right now it should not, it should say that queue is not empty. So we check, we press 3. So queue is not empty, correct. Now let's continue again. Now let's press display. The queue is done, display is done. Now let's try to display again and let's see what are the elements. So 20 and 30, which is correct. Do you want to continue? No. You press any other letter or any other character apart from Y. So I press N, so I don't want to continue. Press enter. That's it. Done. So in this way, we have implemented queue using linked list. And what we have seen dequeue operation, that is nothing but deletion from beginning. We have seen enqueue operation. Obviously that is not efficient, but it will work. And obviously I have shown you, I have told you that how you can implement it in a constant amount of time. This is constant amount of time, right? Dequeue is done in constant amount of time. Here we have done insertion at the end. right, which is obviously performing in a linear amount of time. So if you somehow keep the track of the tail, you can obviously perform it in a constant amount of time. We have also seen is empty. We have also implemented is empty to check if our queue is empty or not. And finally, we also check the display method, which is used to display all the elements in the queue. Now, one more thing is there. This is also done in constant amount of time, is empty. Now, one more thing is there, that is full method. We cannot implement it because queue is never full, or you can say that only the case where when you have exhausted all the memory in your system, right, that will be the case. So in this linked list we don't implement is full because there will be no overflow condition, and this is to check if we want to delete, and is empty is used to save us from the underflow condition, because if we have is empty condition and then we want to dequeue, that is not possible. So this will help at that time. Okay, now let's talk about advantages and disadvantages of queue. First, we are talking about advantages. So it follows a principle of FIFO, or the elements are stored in a FIFO manner. That means, let's suppose this is a queue, and in this queue you have elements. So the deletion will take place from the front, right? And the insertion will take place from the rear side. So this is known as dequeue, the deletion, and insertion is known as enqueue operation. And both these operations are performed in a constant amount of time. So that is one of the advantages, right? And the insertion from beginning and deletion from end takes a constant amount of time. Plus, if we want to do peak first, peak last, all these operations are performed in a constant amount of time. And this is most widely used data structure when we talk about CP, that is competitive programming. When we talk about competitive programming, this data structure is most commonly used because of these features, that all the operations that are performed like insertion, deletion, peak first, peak last, enqueue, dequeue, all these operations are performed in a constant amount of time. Now let's talk about disadvantages. Since we are only able to delete or insert from the front and the rear, that means deletion from front and insertion from the rear. So the restriction of insertion or any manipulation, right? We have a restriction over these, right? What? These operations, insertion and deletion. So this restriction is always there, and so this data structure, that is the queue, is not much flexible, right? We are fixed. We can delete and insert element in a fixed pattern or in the FIFO manner. Thus, it's not much flexible. Binary tree. Now let's talk about what is binary tree. So it is a hierarchical data structure. As we have seen in earlier data structures like arrays, linked lists, stacks, and queues. All of these data structures were linear data structures. But when you talk about tree, is a hierarchical data structure. That means it can have one or more than one children. Doesn't have to be explicitly two children. But when you talk about binary tree, therein you can have at most two children. That means if this is the node, and then it can have at most two children, or if this is a node, it can have either left child or the right child, or it can have no children at all. Okay, so this is a binary tree, and now this is known as the root of the tree. That means the first node is known as the root of the tree, and you cannot access elements or these nodes directly. Okay, so now this is the whole structure of a binary tree. Now there are some common traversals, right? How we can traverse through all these nodes. So one of the common traversal is pre-order, wherein you always, whenever you are on this node, you always print this node first. What is the value of this node? Then you go on to the left side and do the same. Then again you go on to the left side, then do the same. Print, go on the left side, print, go on the left side, and so on. Unless and until there is no left, then what you do is print that thing. Okay. Then after that, you will go on the right side. So pre-order follows print first, then go on to the left, then go on to the right. Similarly, post is saying that whatever is you have, print it at the last. So go on the left, go on the right, print at last.
And in order says left, print, and right. So these are all traversals. We will also see one by one how we can implement it, and how we will also see examples based on these traversals. Now let's talk about the applications. If you have seen the file hierarchy system, wherein we have the root folder, and inside that root folder we have subfolders like music, and we have bin, we have files, we have program files, and all those things, right? So it is a kind of a hierarchical data structures, right? And explicitly here we are not talking about binary tree but generalized tree. Now, if you have binary tree, it has multiple variations, right? If you talk about this binary tree, so here you always have either or the left child or the right child. When you talk about BST, the childs are inserted in the tree in such a way that on the left side it will be always less than the root, and on the right side it will be always greater than the root. So this is a variation. It is known as BST. So you have aerial tree wherein you don't exceed the height more than 2. So that is one more variation. Then we have red black trees. So these are all variations of binary tree.
Now let's talk about implementation of binary tree. So first let's talk about declaration and initialization of binary tree. So we have a structure over here, and in that structure we have three data members. One is data part, another is self-referencing pointer, that is left, and similarly the right. So our structure will look like something this. So this will be our data part, this will be our left, and this will be our. So this is the structure. Now let's see how to insert values in a binary tree. So we have this insert function over here, and in that function we are passing in the head, or also known as the root node. We are passing in the value and the direction. Would you want it to be on the left side, or do you want to be on it on the right side? So this direction is over here. Now we have created a structure, a temporary structure over here, that is temp tmp, and then we are allocating memory with the help of malloc function, and we are also calculating the size with the help of size of operator, and then finally we are typecasting it to the structure, that is pt. Then what we are doing, we are inserting the values in this temporary variable, that is tmp, and we are inserting the value. Let's suppose the value is 5, so value 5 is inserted. Then what we are doing, we are updating our left all as well as our right pointer to null. This is null, and this is null. Done. Now what we are doing, we are checking if the direction is left. That means if the direction is left, if we want to insert it on the left hand side, then what we will do, we'll say, okay, whatever is in the queue, let's suppose this was our root, and in that root we had 10, and this is null, and this is null. Okay, this is our queue, as also known as the root. Now if we are saying that whatever is, obviously these will be having some addresses. Let's suppose this is 1000 and this is 2000. Now what we are saying that queues left, that means we are talking about this position because the direction is left, so we are inserting this on the left hand side. We are saying if direction is left, then whatever is in the temp, put that in that left side. Okay, so that 2000 goes into here. That means this is linked, and this is how it looks now. Okay, now next time, let's suppose another time we call this function again. We called it again. Let me just erase all these things. Okay, now we don't have this as temp. This is 2000 and done. So we are calling it again. Now this time around, what we are doing, we are checking, okay, if root is there, this root should be there, and this is 2000, right? So value is, let's suppose we are right now trying to insert 50, and then the direction is right this time. Okay, so we are creating a structure. Let's suppose this is our structure, and in that data part, obviously with the help of malloc, we are having this null, we'll be having this null, and this is null. And then what we are doing, we are inserting the value in this temp data part of temp, that is right now this is temp. Okay, and the data part, let's suppose we are inserting 50, which is the past, and we are checking if direction is left. No, it is not. Else whatever is in the queues right, that means whatever is in the queues right, please insert temp in that temp. Let's suppose this is 3000. Okay, so this will be 3000, and these are linked. Okay,
So this is what happens over in this slide. So in the next slide, what we are doing, we are just creating another thing, right? We are creating a root over here, and then what we are saying that, okay, allocate memory to this root. So that means that root function that was earlier here, the root node that was earlier here, this root node. Okay, we are having this root node, and what we created this, and we allocated -1 in the data part. Okay, and then in the left and the right it will be null. Okay, so then we are inserting this. Okay, and we are saying that, okay, insert the value on this side, insert the value on this side. Then we are again calling it, but this time on the roots left. That means whatever was in the roots left, this time this becomes the root. Okay, this becomes the root. And then what we are doing, what we are inserting on the left hand side, we are inserting 5. In this case, it was here -1, then it was the roots left was 3. And then this became the root, and in this roots left, we are inserting 5. Okay, because it's on the left hand side. Similarly, what we are doing in roots right, please insert 7. So this is 7. We are inserting the 7. And also this statement is there. That means roots right, please insert 2. So our tree will look like something this. 3, 5, 7, 2. Okay, let's clear out the screen. So we have this -1. Then we have 3 over here. The left hand side, 2 over here. Then we have 5 over here and 7 over here. This is how our tree looks like. Now let's try to traverse through this tree. So we are having this function over here, and we are using recursion, and we are trying to calculate pre-order. And pre-order means first try to print the data, whatever is in there, then move to the left hand side, and then if there is no left, then move on to the right hand side. And this goes for same for each and every node that is there. So let's suppose we have the same node that we earlier discussed about, the same tree, that is -1. One second. -1, 3, 5, 7, and 2. -1, 3, 5, 7, and 2. So this is our tree. Now we are trying to find out the pre-order. Pre-order means let's name these as 1, 2, and 3. Okay, or P, L, and F. Okay, P, L, and R. Okay, so P, L, and R. Okay. So now, is our Q null? No, absolutely not, because Q will be having some address, right? And that is not null. So pre-order means print first. So -1 will be printed. So this statement is done. Then what we will do, we'll traverse to the left hand side, and this time this will be the root, and we are calling this function pre-order recursively again. So now this left part is also done, but this time around we are here. Now this is P, L, and R. Okay. Now again, we are over here, and the first statement is to print the data. Now data is 3. So this is printed. This statement is done. Now we go on to the left hand side and recursively call it. So this side is also done, but this time around, this will be the root. This will be P, L, and R. Is our Q null? This time this is the Q. No, it is not. Print the data. That is 5. This statement is done. Now move on to the left side. Now again, recursively we call this pre-order again. But this time around, roots left, that is there, it is null. Now this is our root right now. So is Q null? Yes. Return. So it returned. So because we are not doing anything, so it will return automatically. Okay. Now what is left? The roots right. Again, it will be null. So is Q null? Yes, it is. Again, we are returning. Now all of these statements are done. Now where will we? We'll traverse back, because everything is executed. We will return to the function which called it. So this time around, the left side is entire left side of this is done. Now we will traverse on the right hand side. So in the right hand side, if you can see, we have the 7 left. So we'll move on to the right hand side. So this will be called. And now this will be having the same thing, P, L, and R. So in this, we will first print the data, that is 7. Then we will check for left. Left is null. It will come back. Right is null. It will come back. Done. Then what we will do, we'll traverse back to this portion. Now right is also done. Now this is left. So what are the things that are there? P, L, and R. So print your data. That is this. Go on to the left. This is null. Go on to the right. This is null. Everything is done. Return to this and return. Then finally return to the main function, because that is the driver function. Done. This is how your pre-order looks like. Okay. So for this particular tree, -1, 3, 7, and 2, we will get the output as -1, 3, 5, 7, and 2. This is your pre-order traversal. Now, what about the post-order? Post-order is similar to what we have already seen, but this time we will be first traversing to the left, then right, then finally printing it. Post means
we will postpone the printing statement. Pre means we are printing the first statement. The statement that is first is the printing statement. Okay. Now let's see how it will look like for the same tree. So 3 was here, 5 was over here, 7 was over here, and it was 2, I guess. Yes. So this time around root is this. So we have passed in the root, and is root null? No, absolutely not. So what are the statements left? That are L, R, and P. So now we are not printing over here, right? Go to the left hand side. We are going to the left hand side. The statement is executed. Again, L, R, and P. L, R, and P. Okay. So again, we've checked. Is our root null? No, absolutely not. So we'll go on to the left hand side. Again, left is there. Left, we call this left. Is root null? Oh, obviously, there's 3 statements will be there. Is our root null? No, absolutely not. Go on to the left. Left, it has gone to the left. Now it returned because this is null. So Q is null, we return back. Go on to the right. It is null, we return back. Now finally print. So we are printing. The first element that will be printed is 5. Done. Now, after that, we are done with the printing statement. It will return. So it will go on to the right hand side. Now right hand side is this. Now again, what will happen? L, right, left, right, and print. So left, there's nothing, return. Right, there's nothing, return. And then finally print. Printing 7. So left, right is done for this root node, but the printing statement is left. So we'll directly go ahead and print it. Done. We'll return back. Now entire left portion of this root -1 is done, but still the right portion is left. So we move on to the right. We'll write L, R, and P. So there is no left, return. There is no right, return. So both of these are done. And then finally print. Printing 2, and we are done. So we have done, and we will return. Then finally, the last statement that is left is print. So we'll print -1, and then we will return to the main function. Done. This is how your post order looks like. So we will get the output as 5, 7, 3, 2, -1. Done. Now let's look at the in order. So in order is that go on to the left, print the data, go on to the right. So printing statement will be in between. So left, print, and right. Okay, same tree. -1, 3, 5, 7, and 2. Okay, so now how will we do it? So same stuff, right? So this time around we have said that if Q is null, then return. Else we were putting if Q is not equal to null. Okay. Now we have L, P, and R. So is Q null? Absolutely not. Go on to the right. Go on to the left. We went to the left, right? And we again called this function L, P, and R. So is Q null? No, absolutely not. Go on to the left. We went on to the left. Left, P, and R. Go on to the left. Again, is Q null? No. Go on to the left. We went on to the left. So left is null. We will return. We return from here. So left is done. Then we will print it. Then we'll move on to the right. So right is null, we'll return. So both of these statements are done. We went here. So print 3. Then move on to the right. Right, we went to right, left, print, and right. So again, we went on to the right. So this statement is also done. So now we check for this. So left is null, we print it. Right is null, we return again. So left, right, print is done. So we return to this function. No statement is left because right is already covered. Now we go back to the main calling function. That was this, wherein -1 was the root. Again, now we are here. So we'll print it. -1 is printed. Then we move on to the right hand side. So L, P, and R. There is no left, return, print it. And then there is no right, return, nothing will happen. So entire right is done. So this is done. Then finally, we are returning back to our main function. So this will be the output as 5, 3, 7, -1, and 2. Now let's see the implementation of the same in order traversal, pre-order, and post-order in code blocks, along with the insertion, how we insert the elements. Now let's try to understand the implementation of these methods in code blocks using C. So now if you can see that we have these header files over here, and then we have the structure, that is binary tree, wherein we have the left and the right and the data part. These are all the 3 data members. Then we have this insert function over here, which expects the arguments, 3 arguments. One is the root, then the value, then the character. That is either the left direction or on the right hand side. We want to insert the value. Then we have defined the structure, that is the temporary structure, wherein we allocate the memory with the help of malloc and calculate the size and then typecast it. Then we insert the value in the data part, and then we update our both left as well as right pointers to null. This is the insert function. And then based on either the character, if the character is or the direction is L, we'll go on to the left side. If it is right, we will move on to the right hand side. So this is your insert function. Now if you look at the in order function which is there, we have this q, that is our root. If it is null, then we will return, else we will print, which is the order. That in order, what will happen, first we go on to the left, then print, and then right. So that is there, we are recursively calling in order left on the left hand side and on the right hand side. Same thing happens on the pre-order. If q is not equal to null, then we'll go and print the data, because we are talking about pre-order. So print the data, move on to the left, move on to the right, recursively calling pre-order on left and right hand side. Similarly, post order will prepone our print statement, that it will be the last statement that is there. We'll check if q is not equal to null, move on to the left, move on to the right, and then finally print the data. And then our main function, in this main function, we have defined the root node with the help of malloc function, and we are allocating memory and size of, we are calculating the size of bt, then typecasting it to the structure, that is bt. Then roots data is -1. Then we declare or initialize our tree, that is the -1 being the root. On the left hand side, it will be 3. On the right hand side, it will be 2. Then on the left hand side's left, it will be 5, which we have already seen in the implementation. And on the right hand side, it will be 7. Now we'll be calculating the in order and printing out the elements, and then calculating the pre-order, in order, and finally the post order, and printing out all those orders. Okay, because if you observe carefully, in all these pre-order, post order functions, we have the print statement associated, so we don't need to worry about printing out the elements or having a separate function for printing out those elements. Now let's save this file, and let's now try to run and build and run this code. As you can see that this is our in order. You can check it with the earlier implementations that we showed. So this is the output that is here, which is 5, 3, -1, 7, and 2 for in order. For pre-order, it is -1, 3, 5, and 2, and 7, because in pre-order you're printing the first. So -1 is the root, so that is why you're printing it. In order, you will go on to the left, then print. 5 is the left hand side's first element. The entire left, when entire left tree is traversed, the left part portion, therein you have the 5 at the end. Similarly, we postpone our print statement, so we move on to the left, and then on the right. So right, there is no element in the right, so we'll be printing the 5. So these are all in order, pre-order, and post order traversals for the binary tree. So in this way, we understood how to declare and initialize our structure when we talk about binary tree. Then we defined what the insertion function, wherein we were inserting all the elements that is on the left hand side as well as on the right hand side. Then we used 3 traversal methods, right? And we implemented them as well. Those were pre-order, in order, and post order. Now let's talk about advantages and disadvantages of binary tree. If you talk about advantages, we can represent data with some relationship, right? So this is the root node, or this is the parent node, and this is the child node. So that relationship, parent-child relationship, is always there. And while you are inserting or searching an element or a node in a binary tree, it is much more efficient as compared to other data structures which we have seen. Now, if you talk about disadvantages, if you want to sort this binary tree, it is much more difficult, right? Because we can either go on the left side. This can be a tree. That means this is a left skew tree, or this can be the scenario wherein we have all the elements on the right side of the node. So this can be another scenario wherein we have this right skewed binary tree. So sorting is difficult, and it is not much flexible, right? If you talk about this binary tree, we always have either the 2 children or 1 children or no children. There is no flexibility in terms of how you want to store it. Can we store another node on the with this root node? No, that is not the case, right? And we don't follow any restrictions like, okay, we always find this node. That is, if this is in root node, we always find an element which is less than this node on the left side or on the right side. That is of the greater element. So that flexibility is not there. Binary search tree.
Now, what is binary search tree? So binary tree is an additional restriction, right? This BST is nothing but the additional restriction on binary tree. Like we have already seen the binary tree wherein at most we can have two children, right? So it can be on the left side or it can be on the right side. Now, what are the restrictions on this tree? So the restrictions are that the data, that is, let's suppose this is 5 and these are another two nodes. Now, the restriction is that if this is a root node, then you always will have the element that is less than your root node. So you can have 4, 3, 2, 1 on these sides, but you cannot have 6 on the left side. Similarly, you can have 6, 7, 8, 9, and so on. On the right hand side, you cannot have 1, 2, 3 on the right hand side. So these are the two restrictions that are there in binary search tree. Now, if you talk about insertion, deletion, and while you are searching the element in the binary search tree, it is much more efficient as compared to binary tree, because we can obviously, when we are trying to search for an element, we can obviously, if let's suppose we are searching for 8, so will it make sense to go on the left hand side? No, we can easily neglect this part. Similarly, we can do it on the rest of the elements. This is one scenario wherein searching is much more efficient than binary tree, because in binary tree we cannot neglect any elements, or we cannot say, okay, now we cannot find an element on this portion, on that portion. Similarly, when we are inserting, now, if the element is greater than 8, so we can easily, in this scenario, right, we can easily go on the right hand side rather than searching where we want to insert it. And similarly, when we are deleting, a little bit of ordering is done in order to get the exact same situation, wherein your root is less than the right hand side elements and wherein your root is greater than the left hand side elements. So that scenario is there in the binary search tree. Now let's talk about the application. It is suitable for applications which require sorted hierarchical data. Let's suppose you have some data and you want to store them in such a way that always you want your elements that are greater than the root on the right hand side, right? You want them on the right hand side, and for the elements which are less than this root, you want them on the right hand side. Okay, so that you can easily neglect. Okay, you can now, let's suppose, not, if you don't want this scenario wherein you are just dealing with the greater than or the less than, you can have a similar kind of a situation wherein you are saying that, okay, on this side I will always have some files that are related to coding. Okay, let's say an example, and in this I will always have files which are related to entertainment. So you can do that so that you can easily neglect these files, because these are always going to be your coding files, and these are always going to be your your entertainment files. So wherever you require sorting, right, or you want your data to be in such a manner that it is easy for you to find, insert, and delete. So therein your binary search tree comes into picture.
Let's see the implementation of binary search tree. Now, before we start that, let's see the structure of BST. So again, it will be similar to what we have seen already in the binary tree. So in binary tree, we already seen the data part, the left part, and the right part. Similarly, in BST, we'll have the same. We'll have the data part, we'll have the left subtree, and we have the right subtree. And we'll start inserting our values in this structure. Now let's try to understand the insertion in BST. If we talk about insert function, we pass in the argument as the first argument is the root and then the value that we want to insert. So we know how BST operates. Let's suppose if this is the root is 10, then on the left hand side there will be all the elements that are less than 10, and on the right hand side they will be greater than 10. This is how BST operates, right? Let me just clear out my screen and let's see how it is done. So first of all, we create this temporary variable that is tmp. So it is initialized to null, and then we check if our queue is null. So there will be two scenarios wherein our root is null, right? There are no elements in the root. So when root is null, whatever we have passed in, it will be null, right? Then what happens? We will just check if q is equal to null. Yes, it is. Then what we will do, inside this temp, what we will do, will create a temporary structure like this that we have already seen in the declaration part. We allocate memory and we pass in, we insert the values, data, and the left and the right. Okay, so data, let's suppose the value that we wanted to insert is 10, so 10 is there. Then we have the null, and then we have, this is also null, the left and the right, and this is our data part. And then finally we update our queue. So this is our new queue, that means this is our root. Done. So this is what happens when our root is null. Now what if our root is not null? So this time around, let's call this function again, right? This time around our root is not null, our queue is 10. That means this will be having some address. Let's suppose this is 1000. Okay, so this is data part, this is left, and this is right. Okay, done. Now we check if queue is null. No, it is not. We have this temporary still in place because we are creating, every time we'll be creating a new node because we are talking about insert function. Now we move ahead into the else part. Now in else part, what we will check? We'll check if the value of whatever we have passed in this, right? If the value is, let's suppose 20, we'll get back to this. So let's suppose this is 10, data part, this is left. Or let me just clear it out. This is null, this is left, this is right, this is data, and this is 1000, and this is our root, that is q. Now we are checking whatever is the value is 20 right now. Okay, we check if q, that is if value is less than the q's data. Whatever is the q's data, is value less than? No, it is not. That means we'll not go on to the left hand side because it will be part of the right hand side, because this is BST. We went on to the right hand side, and then what we will do, we will pass in this roots right, and we will store the value in this. Okay, and we will call this insert function on q's right. So this time around this will be the root, and on q's right we will pass the value. We'll call this insert function again, and this time around what we will do, we'll call this function with the new value, that is 20, and we'll try to insert it over here. So new, this will be created again, this will be called. So this time around this q is null. So this q is null, and so this is null, and that will be inserting 20 here. This is null, this is null, this is 20, and this will be on the right hand side. Had it been, we are trying to insert 9. Now again 9, this time around this q will be null, right? Because we are passing in the q's left, which is null, and the value which is 9. So again insert function will be called. Okay, this will be called. So again it will check if this q is null. Yes, it is. And then what we will do, we'll create a structure like this, and this time it is 9, this is null, this is null, this will have some address, let's suppose it is 2000, and this is our tmp, and then this is what we did, the data value and all these updated, and this is our root q, this is our root for this particular left hand side. Now when we return the q, and that q will be stored here, that is this 2000. Similarly, this will be 3000, and this will be stored over here. This is 9, because 9 is less than 10. So if I clear my screen and clear out everything, so it will be something like this: 10, 9, and this will be 20. So this is our BST, and this is how you insert a node in a BST. And then finally we'll return Q in any of these cases. Okay. Now let's talk about the in order function. Obviously, all the three traversals are applicable: in order, pre-order, and post order. Now same thing happens, right? If this is a pre-order, that means we are printing out first the element and then moving on to the left hand side and on the right hand side. Similarly, if this is a post order, we will do left, right, and then print it out. If it is an in order, what we will do, we'll go on to the left, we print it, we move on to the right. Done. So this is how we traverse. Now, if we talk about explicitly the in order function, why I have written it over here, because whenever you apply, let's suppose this is our PST. So this will be 9, this will be 20. So obviously this will be less than 20, but greater than 10. Next element, let's suppose it's 15. This will be 21. And let's suppose this should be less than, that is 8. But this side should be greater than, but obviously less than 10, which will be 9.5, or let me change it to 7. And this will be 9. And let me change it to 6. Okay. Let me just clear it out. Yeah. So this is 6. So now whenever you apply in order traversal on a BST, so this is our BST. This is our root. Whenever you apply in order traversal, I will show you what will happen. So we'll do the same thing that we did earlier. So this is left, this is print, this is right. So go on to the left hand side. So it will traverse. This statement is done. Left, print, and right. Go on to the left hand side. This is done. Is Q null? It is not. Right now it is not. Go on to the left hand side, print L and R. So now again, go on to the left hand side. Is this null? Yes, it is. It will return L is done. Print 6 is printed. Print is done. Go on to the right hand side. Nothing is there. Return. This is done. This entire node is traversed. Will return. Will return and print this out. 7 is printed. We move on to the right hand side. We again do the same thing. Left, print, and right. So left is nothing. Print it out. Right is nothing. Return. Now return from here. Right is done. Go back to the main function. That is our root node. That is 10. Print it out. 10 is printed. Then go on to the right hand side. Do the same stuff. L, P, and R. So move on to the left hand side. Left hand side, do the same stuff. L, P, and R. Move on to the left side. Do the same stuff. L, P, and R. Left is traverse. Will return. Print this out. 15 is printed. Now go on to the right hand side. Nothing is there. Return. Go back to the caller. That is 20. Print it out. Go on to the right hand side. Left, P, and R. Go on to the left hand side. Nothing is there. Return. Print it out. 21 is printed. And go on to the right hand side. Nothing is there. Return. Returned. When returned, right is covered. Return. Right is covered. Return. Return to the main function. Now, what happened over here? If you observe carefully, 6, 7, 8, 9, 10, 15, 20, and 21. Whenever you want to check if the tree that is given to you, BT obviously, binary tree that is given to you, you want to check if this is a BST or not. Apply or traverse in order, apply in order traversal on that. Okay. Whenever you apply in order traversal on a BST, the result will be always in a sorted manner if and only if it is a BST. Now, since this was a BST, right? Everything was according to what we have, all the restrictions that we had on BST. So that is for the same reason we got this output as 6, 7, 9, 10, 15, and 20 and 21, which is obviously sorted. So this is the main objective of having the in-order traversal and traversing in orderly in the BST, because it will always result in a sorted, it will give the output in sorted manner. Now let's try to search an element in the BST. Let's suppose this is the BST, the same BST. It is 10, 7, 6, 9. Okay, let's put it 10, 7, 6, and this is 8, this is 20, this is 15, and this is what, 22, anything, right? So this is the BST. This is our root node, right? This is our P. The key that we want to search is, let's suppose we want to search for 20, and then we passed in the BST. Now what we are doing, we have this temporary variable, and then we are checking if P is null. Then there is no point of checking it, and we'll return. If it is not, we'll keep this P, that is the root node, in a temporary variable. Okay. So now this temp is also pointing to this root node. Done. Let me just erase it out. This P is also done. Now what we are doing, we are updating this pointer that is there, and we are updating it to null. Yeah, we are updating it to null. Then we check if temp not equal to null. If temp is not equal to null, is temp equal to null? No, it is not. Then what you do, you check the temp's data. Is it equal to key? Is temp's data equal to key? No, it is not. Then return temp. So we will be returning temp. Done. But since it is not, because obviously we are checking for 20 and this is 10. Since it is not, so we will move on to the else part. So in else part, what we are doing, this is the pointer that is used to store the root. So we are storing the root, that is temp, and then what we are checking, if temp's data is greater than key. Is temp's data, that is 10, is it greater than key? No, it is not. Then that means if it would have been greater than, then we will find out on the left, in the left subtree. But since it is greater, we will look for the right subtree. Then what we are doing, we are updating our temp to temp's right. That means now this temp will be pointing to this temp's next, that is temp's right, that is this. Okay. Then finally what we will do, we will go back and check again.
If you observe carefully, this is while temp is not equal to null. So is temp null? No, it is not. Is temp's data equal to key? Yes, temp's data is equal to key. Return temp, return the temp node, that is this BST, that is this temporary variable that we created, which is also of type structure, that is BST structure. We return this temp, and then we finally can say that, okay, in the main function, we can say that, okay, we have found this element, that is, it is present in the BST. Okay. Else, if we were not able to, and we have traversed the entire BST and we were not able to find this temp or this key, we would have returned the null. That means this root is not present. This key is not present in the BST. Now let's try to implement whatever we have learned so far in the code blocks. Now we have these these libraries present over here, and we have including them. Then we have the structure BST over here, which is the left and the right. Then we have implemented the insert function, wherein we are passing two arguments. That is, first is the root, and the second is the value that we want to insert. Then we have this temporary variable, and then we are checking if q is null. Remember the two scenarios which we talked about, right? The first wherein our root is null at that time. This will be our new root. That means we are updating, we just allocate memory first to this temporary variable, right? With the help of malloc, size of, we calculate the size and then typecast it to BST. Then we'll update data part, left and right pointers. And then finally, what we will do, we'll make this temporary variable of type BST as the root node, and then we will return Q. That's it. Okay. But what if there are elements, and then what we will do? Then what? Let's suppose there is a 10 and this is the root. Now, if we want to insert an data which is greater than 10, then what we will do? Obviously, we'll check if the value is greater than data. If it is less than, that means we'll move on to the left hand side. If it is not, we'll move on to the right hand side. So we are trying to insert the 11, and so we will go on to the else part and we will insert this value, and then again recursively call this insert function again and go through the whole stuff, because now this queue's right, that means this root's right is null, and now this time around this queue will be null. This queue will be null, and then same stuff will happen. We will allocate this memory to the right hand on the right hand side to the node that is having the value as 12, and then we will finally assign that to the queue's right. And now there's a link between the 10 and the 11, okay, or the 12. So this is our insert function. Let's minimize it. Then we have the in order, which we have already covered. So in order is used to check whether we have a valid BST or not, because we know the property that is there. Whenever we have a BST and we want to check if this BST is a valid BST, apply in order traversal on that. If the result is in order, right? If the result is in sorted manner, then it is a valid BST. So we know how in order traversal works. First, we call the in order on the left and then print out, then call the in order on the right hand side. Done. Then finally, we have this search function that is there, that is structure BST, which is a temporary variable. If we want to search an element in the entire BST, we first have this temporary variable, and then we check if it is null, then there is no point of going into and searching our value. Then we return, and then we have this temp updated. Then we check whether the temp is null. Then we check the data part of the roots, right? If the data is greater than the value where we want to find, we will look in the right subtree. If it is less than, we will look on the right subtree, on the left subtree. If it is less than. Now, if we have exhausted the entire tree, that means there is no point that it will be on the left hand side. It is greater than the root. That means it is on the right hand side. We'll check one by one, we'll check, and we keep on updating our temporary variable. And once the entire left sub or right subtree is done, we will return null if we were not able to find it. Now, if we were able to find that temp's data is equal to the key, we return the temp. Now, if we talk about the main function, we have this root over here, and this is at the starting of this program, it is null. Then we have these variables which are used to insert the values, and we print on the term where we want to insert it. Then we check if this is not equal to null. Then we insert the value and call the insert function. Then call the
insert function and store the value in the root, and we call it as many times as we have entered, right? Let's suppose if we have entered, okay, we want to insert 5 elements, we scan the we enter 5, and then one by one we'll insert the values, and the insertion will take place in this manner that the root will be always less than the root. If the root is 10, all the elements on the left hand side will be less than this root, and all the elements that are greater than this root will be on the right side. So that has been taken care of, and we will insert all the values, and then finally we will display all the elements that are there, and the result, we want to check if this is a valid BST, we'll call this in order function and check, okay, this, if we get the output in sorted manner, that means this is the correct BST. Now let's try to run this. First build this and then run this, okay? So enter the number of terms. So let's suppose we say 5 terms are there. So the first element is 10. Let's suppose 10 is there. Then we had what, 7. 7 was there. It will be on the left. And then we had what? Let's suppose we want to insert a number that's greater than. We have 15. So 3 elements are done. Now I want to insert on 7's, that is the 7 root. On the 7's right hand side, let's insert 9. And on the, okay, on 15's left hand side, let's put a 14. Okay, now we want to check if it's a valid BST or not. So we are displaying the elements in the sorted manner, that is 7, 9, 10, 14, and 15. Since it is the result is in sorted format, so we'll get, we are having a valid BST. Press enter. So in this way, we implemented the insert function. We also looked into declaration and initialization part of the BST. We also talk about insertion of the BST. We also talked about in order traversal and the significance of it. We also have implemented searching an element in the BST. Now let's talk about advantages and disadvantages of binary tree. If you talk about advantages, we can represent data with some relationship, right? So this is the root node, or this is the parent node, and this is the child node. So that relationship, parent-child relationship, is always there. And while you are inserting or searching an element or a node in a binary tree, it is much more efficient as compared to other data structures which we have seen. Now, if you talk about disadvantages, if you want to sort this binary tree, it is much more difficult, right? Because we can, obviously, we can either go on the left side. This can be a tree. That means this is a left skew tree, or this can be the scenario wherein we have all the elements on the right side of the node. So this can be another scenario wherein we have this right skewed binary tree. So sorting is difficult, and it is not much flexible, right? If you talk about this binary tree, we always have either the 2 children or 1 children or no children. There is no flexibility in terms of how you want to store it. Can we store another node on the with this root node? No, that is not the case, right? And we don't follow any restrictions like, okay, we always find this node, that is, if this is in root node, we always find an element which is less than this node on the left side or on the right side, that is of the greater element. So that flexibility is not there. Algorithms. Let's try to understand what is an algorithm. It is a step-by-step approach to solve a particular problem. If there is a problem, what is the things that you are going to take care of? So the solution that you give should be crisp, right? It should be exactly what is required, right? If a problem is about swapping 2 numbers, you should be able to swap 2 numbers and with the most efficient approach. And when you define an algorithm, or when you're writing an algorithm, it should be understood by a non-technical person, right? There should be no such language dependency in your algorithm, right? So this is what an algorithm is: a step-by-step approach to solve a particular problem. Your problem can be complex or it can be an easy problem. It is free from programming language. There are multiple possible algorithms to solve a given problem. Let's suppose I told you to swap 2 numbers, right? Now, one algorithm is wherein you can go ahead and create one temporary variable and then swap them.
The another approach is that you're going to use addition and subtraction operators to solve the same. You're going to use these operators and you can solve this problem of swapping two numbers, right? Which one do you think is the efficient approach? Obviously, here you're using an extra variable and here you're not using any extra variable. So this seems to be a better approach. And obviously, it should be understood by a non-technical person. You should not be using language dependency code, like you should not use any language agnostic code, right? So it should be language independent. So let's see what is an algorithm analysis. This is again a step-by-step approach to solve a particular problem. It helps us identify which algorithm is optimal. Okay, this is the analysis part of algorithm, right? Herein, let's suppose I told you to swap. It helps us to understand the trade-off between time and space complexity, right? So there should be always, you should be able to understand the difference between time complexity and space complexity. And depending on that, you should be able to do a trade-off as well. Now, when I mean trade-off, you should be able to depict that are you going to keep your time complexity efficient, or are you going to use your time efficiently, or are you going to save your space? So let's suppose you are given an example, right? Let me give you an example. So you are given an example, you are given an array, and in that array you want to search an element. Now the first approach is that you will go and search one by one, right? You will go here, you will iterate through here and here and here. You try to search an element, right? Let's suppose you are searching for 4. In the worst case, you are traversing big O of n time, right? And in the best case, you are traversing big O of 1 time. This is the best case and this is the worst case, right? So these are the two cases. But this code in itself, whenever you are traversing in a linear fashion, is inefficient, right? And if you're trying to search for an element using different approach, let's suppose you are using a binary search and then you are trying to search an element, obviously your time complexity will reduce. The best case will again remain big O of 1, but it will reduce to big O of log n. Now there are certain parameters, or depending on these parameters, you can define the best, worst, and average case of a given problem. So now there are different types of algorithmic analysis, that those are best case, average case, and worst case. Okay, so the best case is obviously when you are searching for an element in an array of, let's suppose, 100 size, right, or 1000 size. The best case is that the first element that you look, if you're talking about what, linear search, okay, best case scenario is that the element that you're trying to search is the first element, right? Done. This is your best case and it requires constant amount of time. Now if you talk about average case, it will be somewhere around the middle, right? About 1000 divided by 2, or you can say big O of n divided by 2. Since we are neglecting, we do not take care of these constant terms, or we can negotiate, or we can neglect these constant terms, because as soon as our input is increased, right, let's suppose right now we are talking about million, thousand elements, we are talking about 10 billion elements. At that time, dividing it by 2 still is same, okay, not same, but it can be ignored, because as soon as we are increasing our n, let's suppose, to 10 crore or more than 10 billion, okay, 10 100 billion is the input size, right? At that time, dividing by 2, still it is greater than what we can do if we have something around log n, okay? So obviously the average case is still big O of n. Now when you talk about worst case, the element is found at the end, or it is not even found in the array. You're traversing each and every element in the array and still you were not able to find the element. So this is the worst case, okay? Now the worst case is always taken into consideration because this is the maximum resource that you require, okay? When you talk about time complexity or space complexity, right? So time and space, right? So you always talk about worst case scenario, right? And you always deduce your time and space complexities based on worst case. It is computed because the analysis as it dictates the maximum resource requirements. So worst case helps us to find what are the maximum resources that this is going to take. Okay, so we keep track of those things and we allocate resources in such manner. So we always talk about worst case. Now let me give you an example of linear and binary search. So in linear search, right, we always talk about it, and in binary search the space complexity of both these algorithms is constant in worst case, right? And if you talk about the best cases of linear and binary search, it is again constant, right? And it is again same. Okay, now when you talk about, we go off on, now when you talk about the worst case scenario, right, and this is what helps us to differentiate between binary and linear search, the worst case scenario. The worst case scenario for linear search is big O of n, wherein for binary search it is big O of log n. Now let's suppose there are 8 inputs, you're going to traverse 8 times in it in this linear search. But if you have this log 8 to the base 2 value, it reduces, or you can reduce it to 3 into log 2 to the base 2, which is 3 times. So in this, you are only iterating 3 times. In this, you are iterating 8 times. Now, as you can see, that input is very low or very less. That means there are only 8 elements. As soon as what our input, our n, or the number of elements in the array grows, this size of these iterations become substantial, and that is for the same reason we always talk about worst case scenario. Okay, now let's talk about time complexity. It determines the total number of unit operations to be undertaken to solve a particular problem. Right? Let's suppose, let me take an example of number of iterations. Like, so if you are able to search an element in a single unit of operation, then it is termed to be a constant operation. And if you're doing same for number of inputs, that let's suppose there are n elements and you're traversing to find a particular element, you're traversing n times, so it's termed to be a big O of n. So to solve a particular problem, you determine the number of unit operations. Now, unit operation is an operation that is independent and it can be broken down into simpler operations. It is independent of architecture. It is computed on the basis of algorithm itself. You have an algorithm in place, and based on that, you compute the time complexity of each and every step, right? If there is a loop, what will happen? If there's a if condition, what will happen? If there's a while loop, what will happen? It's high priority critical in optimal algorithm selection. Now, depending on this time complexity, you can determine whether you want to go with a particular algorithm or not. Because let's suppose you're trying to search an algorithm, right? You can have two options, right? You can use a binary search or you can use a linear search. Now, depending upon the time complexity, binary search works much more faster as compared to linear search. It works in order n and it works in big O of n. So time complexity plays a major role, and there is always a trade-off between the time and space. And in this session, we will be covering both of these things. Okay. So now let's take an example and let's try to determine the time complexity of that particular example. Now let's suppose you are given a for loop, and in that for loop, you are iterating from 0 to n, right? Where n is I is less than n, and then you're doing the plus plus. Now you're doing some work in it, okay? Now since you're traversing from 0 to n, now this is a scenario wherein this will be operated or this will work. The number of unit operations that are present in this for loop is big O of n. Now similarly, there is another for loop in the same program which is operating from 0 to n, okay? And then the same thing, there's a nested for loop in it, and therein what you are doing, you are traversing from 0 to what, let's suppose this is traversed, n is 8, right? N is equal to 8, and in this for loop you are traversing 8 times, and in this while loop you are traversing 3 times, right? Let's suppose you are multiplying every time by 2. Okay, so now in this for loop, the nested for loop, the time complexity of the same is n log n. Now why it is n log n? Because if you observe carefully, number of operations that I told you is 8. So outer loop is working 8 times and the inner loop is working log 2 to the base 8, that is 3 times. So now what is the scenario? What will be the total time complexity? It will be big O of n plus big O of n log n. Okay, this will be the time complexity. Now what is happening over here? This is the scenario wherein what is happening? It is happening m into n. That means you are multiplying big O of n, that is the nest for the nested one. Okay, into big O of log n. So you're multiplying it. Whenever you have a situation wherein you have a for loop inside a for loop, therein you will multiply the time complexities. Now you have a for loop outside and then you have this nested for loop. For this nested for loop, you have n into log n, right? And for this, you have what? Big O of n. Now this is a scenario wherein what happens? M plus n. And in this, you will always take into the consideration the maximum number of resources that are there, so that one for loop will take. So in this you're taking only n resources, or this is the time complexity of this is n, and in this you're taking n log n. So obviously this is greater, right? So you always say that the time complexity of that particular problem will be n log n, because you're neglecting these smaller terms. As soon as our input is increased, these terms will be neglected and they will not be that much significant while you're allocating resources. Now, what about the space complexity? It determines the total space to be allocated in order to solve a particular problem. Now, whenever you're using any extra space in the algorithm, while you are implementing it, that is termed to be as space complexity. It can be in the form of arrays, that extra array that you have used to solve a problem, or an extra linked list that you have used to solve a problem, or a stack or a queue, right? It involves memory of the computer, right? You're involving memory, right? You're taking something extra, right, to solve a particular problem. Let's talk about merge sort. Therein you take extra memory, and in worst case you can take big O of n extra memory. That means the number of elements that are present in the array, you're taking the same array as an auxiliary memory, that extra memory, right? It's low priority critical in optimal algorithm selection. When you talk about space complexity, we try to avoid any extra space. We try to solve it with minimal space, right? So that we don't use any of these auxiliary memories. Okay. Now let me take an example of a merge sort, wherein in that merge sort, every time you create a left array for the left side and the right side, every time you create these subarrays and then you calculate them, then you divide them into further and further unless there is no possible division, and then you start merging them. So again, this is a condition, or this is a scenario wherein you are using extra memory of big O of n. Now if you talk about simpler examples, let's suppose you are trying to uh, change the positions of even and odd numbers, right? So let's suppose you have these indexes, right, in the array, and you have some values. Let's suppose 10, 20, 15, 20, 15, and 10. Let's suppose these are the values, right? Now you want to use, or you want to find out the frequency of these numbers. So you will be using another array, and in that array what you will be doing, let's suppose you are picking up this 10 and you are storing it in this. Now you'll be checking, okay, if this is already present, pick up the counter and keep track of how many times this 10 occurred. Now this will work only for when you're trying to search 10 throughout the array. I'm taking a naive example, right? So I'm taking this example and I'm trying to search 10 and I'm trying to calculate how many times it has occurred. So you place a 10 in this array, and then what you're doing, you will just iterate through the array and then keep a track of this, how many times this has occurred, and keep incrementing your counter, right? So now you're using an extra space, right? Now even if this example is not understood, let me take another example. Let's suppose you're using a recursion, right? Now you might be thinking, okay, internally, you are not using any extra space, but what happens in recursion? Every time a recursion is there, that means function calling itself, an activation record is created and a stack is used internally, wherein your main function will be there, and the number of function calls, right? The function calling itself, function calling itself, function calling itself will be we will be pushing it on the stack, and once you have returned, then we will be popping it out, right? So internally you are using an extra memory, and it depends on from program to program. Are you using big O of n, or are you using log n space? But internally, recursion uses extra memory. So an auxiliary memory, or you can say that extra memory, is used while you are using recursion. So that is why we try to avoid recursive problems, and we try to solve our problems using iteration. So which is obviously that we are not using any auxiliary memory, although it is internally, but still recursion uses extra memory, and that thing is taken into consideration. Now you might be thinking, okay, now should we use, or should we save space, or should we use less time? Should we go for time efficient algorithm or space efficient algorithm? Now, there is always a trade off between space and time. So, in some problems, they might ask you to save or to write an efficient algorithm, keeping the time into consideration, that you don't have to use extra time. But in some, they might say, okay, you can use extra space, but time should be efficient. Or in some cases, they say you use as much time as you want, but space should be less. So that is also there. So there's always a trade-off between both of these things. Recursion. Now let's talk about what is recursion. Recursion is nothing but a function calling itself. So let's suppose if you have in this program, for example, you have a function named fun, and in this function, you're calling this function again. Now this is what a recursion is. It is nothing but a function which keeps on calling itself. It comes intuitive when a function is breakable into subproblems. Now, when your problem you can break it into subproblems, then recursion is very much intuitive as compared to iterative. There are many data structures which are recursive in nature. Let's if you talk about data structures, right? When you talk about binary trees and BSTs, right? Therein, if you solve the problem using iterative approach, it is very much difficult to solve those problems. Wherein, if you talk about recursion, therein recursion is much more intuitive, and you can solve those problems in BSTs and binary trees with much more ease. If you talk about binary trees like traversals, you can do it very easily when you use recursion, and when you use iteration it can be much more difficult. Even if you talk about some examples like Tower of Hanoi, therein also recursion is very much intuitive. Now let's talk about what are the steps involved in a recursion. There should be a base case. We'll talk about these one by one. So there should be a base case, which means that, let's suppose you're calling your function again and again and again. There should be something that should know, okay, now don't call it further, right? There should be some base condition which stops our recursion. This helps us to stop our recursion, which stops our recursion. Okay, there should be some mechanism, right? So base condition is that. Now there should be some logic, or it's also known as self work. Okay, it should be some self work. That means what are you doing in this recursive function, or what are the things that you should do. Let's suppose you are printing out anything, right? Let's suppose you are printing out, that's it. So there should be some mechanism or some logic or your self work that you are doing in that recursion. Let's suppose a simple program can be, you can print all the numbers from 1 to n. Then you can use recursion and print out all the numbers from n to n. So printing out those numbers is your logic or is your self work. Okay, then the recursive call, how you are calling it again and again. So you must be having function, and then you keep on calling it after you're printing it or before you're printing it. Okay, so this function call is known as, whatever is the function call is your recursive call. Okay, so now let's take an example and things will be much clearer. So let's suppose you want to print the numbers from 1 to n. In our case, let's print from 1 to 5. Now if we want to write a recursive program for it, how would you do it? So basically what you will be doing, if you have this function call, let's name it fun, or even if you can name it print, let's name it print. Okay, and it takes an argument as int, and it takes an argument as 9. So 9 is currently what, 5, or let's name it 1. Okay, and it doesn't return anything, so it's void. Okay, so now what we are doing, we are checking if n is equal to 5. That means if we have reached the 5, or less we want, if we want to have this 5 inclusive, so then what we will do, we'll just erase this and we'll make it 6. Okay, simple. And then what you will do, you will say return. Now if this is not the case, what you will be doing, you will be printing printf, then %d, and what, your n. And then what you will be doing, you will be calling this print function, that is your print. You'll be calling it again, but this time around you are adding something to it. Obviously you will be having 1. Now we want to have a print 2, so what you will be sending the arguments as n plus 1, and that's it. Now let's try to break this. So basically what will you be having, you'll be having, this is your base condition, right? This is your recursive, or you can say the self work or the logic, and this is your recursive call. Okay, so now you will be doing these things. So let's name these steps as this is step 1, and this is step 2, and this is step 3. Okay, so now let's see how it works. So let me take an example here. So whenever this recursion is done, a stack is created internally. So there's always a space associated with stack. Whenever you are calling functions that are calling itself, you are internally using a stack. So a call stack is maintained. Let's, and those call stacks are names as activation records. So an activation record is maintained here. Obviously this function will be called from our driver function, that is our main, right? Now what is happening, a main calls this function and we pass in the arguments, that is n, and then what is happening, step 1, step 2, and step 3. These are the steps that need to be executed, right? So now we will check if n is equal to 6. No, n is not equal to 6 because n here is equal to 1, right? Now this is done. Then what happens, we are printing out n. So we print out n. So what will be printed, n will be printed, and it is 1. Then our function call, that is this statement is called, that is we are again calling this function, but this time around for n equal to 2. So again this recursive call is called, function is called, that is print, and we are passing in the arguments as n. So another function is pushed on the stack, and the activation record will look like for this is n equal to 2 because we are passing in the argument. So we check if n is equal to 6. No, we print out what n, which is nothing but 2. Then again this function call is called, that is print is called, but this time with the updated, that is n plus 1 argument. So let's suppose we are just printing out to 4. Okay, now we are just printing out from 1 to 3, so we want 1, 2, and 3 numbers to be printed. So now next time another activation is record is called, right? Another activation record is pushed on the stack. So we check the condition. No, it is not 3 for n is equal to 3. Okay, so it's not 4. We're checking for 4. Nothing has been done. We print the 3, and then we call it for n plus 1. Now this time around another activation record is created, this time around for 4. So we will check if n is equal to 4. Yes, we will return. Now we have returned to this point wherein we call this function call. So there is no statement after this, right? This is the end of the statement. So what we will do, so there in recursion what is happening, a stack is maintained. So on that stack First there was the main function, which is our driver function. Then these many function calls were called. So print will be there. Again print will be called. Print will be there. Again print will be called. So print will be there. So this time the stack keeps on pushing these function calls, and once they return, they keep on popping up. Okay. So now in this case, what is happening? Now we either return when there is a returning condition, right? When we have met the base condition, which was in his case, right? So in this case, we met the base condition was met, and we returned. And the next thing, this is the first case, and the next case is that when we don't have any more further statements, so there are no statements, right? No statements to be executed. We again return at that time. So here we are returning again, okay, to this function call. So again no statements, we return. Again no statements, we return. And one by one, these function calls are popped out of the stack. Okay. And then we are up on our main function, that is our driver function. So this way you printed out 1, 2, and 3. Now let's change a question a little bit. Okay. Now I'm saying that I want to print the number from 1 to n. But this time around, I want them to be printed in a reverse order. Again, 1 is an argument, and that is 1 is your argument, right? That is passed, n is equal to 1. But this time around, and I want to print from 1 to, let's suppose 4, okay? And this time around, I want to print them 4, 3, 2, 1 in the reverse fashion. Can you do it using recursion? Yes. So how will you do it? So let's name this as print, and let's name this as print, and we have this argument as n. So our base condition will change now. So we check if our base condition will keep it same. Okay, if n is equal to 4, we will stop. Okay, if we want to print 4 as well, what you will, okay, let's keep it simple because we won't have to create the actuation record as well. So let's print from 1 to 3, and yeah, well, let's print 1 to 3. Okay, so if n is equal to 4, return. Else what you will be doing, you will be calling this print function again, and this time on n plus 1. Okay, and then finally you will be printing out printf %d, and then your value, that is n. This is your function. Now let's try to see what happens over here. Again we'll do the same what we did. Always these three will be there. This is your base condition, this is your recursive call, and this is your self work or logic, what you're doing. Okay, let's clear this out now. These three things will be always there. That's what we talked about in the earlier slides. If I switch to the slide that was earlier there, you will see the base condition, the logic, and the recursive call. So now let's see how stack is maintained. So now actuation record will be there for n equal to 1. This is the actuation record. So let's name these statements as 1, 2, and 3. So we want to print them in reverse order, and the argument that is sent to us is 1. So n is equal to 1 here, and now we'll check, is this statement, if n is equal to 4, no, this is executed, right? And we didn't return from the function. Then what we did, we call this print function again, but this time around on n equal to 2. Print is called. Now this statement is left behind, so 3 is not executed, right? So this is executed, this is executed. Now we will call again, but this time around it is called for n equal to 2. Okay, done. Now again we will check if n is equal to 4. No, it is not. Then we will not return, and then second statement is called. Then we will call again n plus 1, and this 3 is still left. Now again this is calling in this self on this position. So on 3 it is called, is this equal to 4? No. Again call this print function, but this time around on n equal to 4, n plus 1, right? Now this is 3, again this is left. Again we are calling here, and this time on n equal to 4. So these are all your actuation records. That means the function will be piled up. Again, function called on the stack. And finally, when we reach here at this particular point, we check if n is equal to 4. Yes, we return. Now we are returning. Now we returned over here. Now there is a statement that needs to be executed. What is that? That is printf, and we are printing out n. Now what is the value of n here? If you see on this actuation record, the value of n is 3. So 3 is printed, right? Then what is happening? Now there is no further statement to be executed. Now it will be returning to the function call that obviously called it earlier. Now again, this is the statement where it called, and now again this statement was left to be executed. What is that? Printf. So it will be printing n equal to 2 here, because the value of n is 2 in this case. So 2 will be printed. Again, now no statements are left. It will go to the function call that was earlier there. Now here also it will be printing and then returning to the main function, and one by one these function calls will be popped out as soon as there is no statement or you are returning from a particular position. Here you are returning, it will be popped out. Here no statement left, popped out, function call. Here no statement ref, here no statement left, and then finally will be on the main function, that is our drive function. Now this is what you got printed, that is 3, 2, 1. Now if you observe carefully, only by changing in that earlier case wherein we printed, we were printing before and then calling the function, right? And in this we'll be calling the print, that is print function. Let's name print function. Okay. In this print function, what you will be doing, you were just calling this print function again over here. Okay, print function, and then printing out the statement. Okay, like in this case. So you see the difference in the code is not that much, but only the statement where you are calling this function. It was called later and it was called earlier. And you see we were able to print 1, 2, 3 in this case and 3, 2, 1 in this case just by changing one single statement. Now let's see what is the difference between an iteration and recursion. So recursion, when you talk about recursion, it's always about function calling itself, wherein in iteration, it cannot call itself, right? The function cannot call itself, obviously. Now in recursion, there is always a space associated with it, space complexity, right? We always saw that we are creating a stack whenever we're calling a function, which is not the case in iteration. And whenever we are implementing recursion, right, whenever we're solving our problems using recursion, a stack data structure is obviously, it is implicitly, not you are creating it, but a stack is created. Stack data structure that we already have studied is created internally. There is no such requirement in iteration. Obviously we don't have to create a stack. Now any program that you can write in recursion can be written in iteration, and similarly any program that is written in iterative manner can be written in a recursive manner. So there is no such case that there is only programs that you can write recursively or you can write only iteratively. Now obviously recursion is much more slower as compared to iteration, so it's better when you have a time constraint. That means you want to save the time, obviously space also, because then recursion stack is maintained. You should go for iteration rather than going for something that is recursion and which is much slower than iteration. Now let's talk about tailed recursion. So tailed recursion is a recursion, obviously it's a program wherein our last step is the recursive call. Let's take an example. So, for example, this is a function and we are implementing this function or this method using recursion. So what is happening? We check the base conditions, we do our stuff, whatever we want to do. And then the final step is that wherein we call this function is the recursive call. So it is the last step of the implementation. Obviously now this is faster approach of recursion as compared to non-tail, and in this tail recursion we will never require to maintain the activation record. Now what does this mean? This means that let's take an example. Again we will take this at that simple example wherein we want to print all the numbers from 1 to n. Okay, so now in this case let's see, we are returning white, and now we're checking the base condition. If n is equal to 4, then do the stuff, right? And if it is 4, then we return. Now if it is not, then we are going to print the number, that is n. I'm not getting into the syntax, okay? And then we are calling, this is printf, and then we are calling this print method that is there on n plus 1, okay? Now, as I told you earlier, wherein the actuation records are created the stack on the stack one after the other, that will not happen when you are dealing with tail recursion. I know earlier I told you every time the recursion, whenever you implement recursion, at that time actuation record is created, but that is not the scenario when we are talking about tail recursion. So now what happens? Your actuation record is here. This is your actuation record. Now we have also the main function, and that in the stack main function is called, then this function, then this actuation record is created. Now at n equal to 1, it will see, okay, if n is equal to 1, right? I'm talking about this one. So is n equal to 1? No, it is not. So it will be not execute this, right? And then it will print. So we are printing the statement, that is n1 is printed. And then as soon as it sees that, okay, this recursive call is the last statement, so what he will be doing, he will be calling this function at n equal to 2, and it will never create another activation record. Instead, it will just re-update, or it will update this activation record, and this time around for n equal to 2. So it will check, okay, is n equal to 2? No. Printf n, that is 2. Then what happens? Update your function call with new arguments, that is n equal to 3. Okay, this is the last step. Again, this will happen on the same activation record. Check, this check, print it, again call it on 4. So this time around it will call it on 4. So it will check, okay, now it will be returning. So it will return. Now there is no step to be executed. So after this, there is no step in the activation record 4. When n is equal to 4, there is no step to be executed. So it will pop this function out of the stack, and it will go to the main driver function. So 1, 2, 3 is printed. So this is the beauty of recursion. That is the tail recursion, that you are not using any extra space. We'll also talk about the space complexity and time complexity of these problems individually. But herein you get the point that, okay, whenever you're using, or whenever you're converting your non-tail recursion into tail recursion, you are automatically reducing the space complexity, okay? So this is tail recursion. Now, what is a non-tail recursion? Obviously, when the recursive call is not the last step of the implementation, that is your non-tail recursion, and it is slower than the recursion, which is a tail recursion, okay? So it activation record. Now in that case, in the tail recursion, activation record was maintained, and but it was maintained in a much more efficient way. Here activation record maintenance is required, right? We are creating another activation record, then function calls, we create another activation record, and so on. Okay, now let's see the example. Obviously we have already covered those examples. I'm using simple examples. We have this print int equal to n, and this time around I want to print, instead of 1, 2, 3, I want to print them use in a reverse manner, that is 3, 2, 1. So what did we do earlier we did this thing. We check the condition. If n is equal to 4, then we will return, right? And then what happened? We call this print on n plus 1, and then finally we had this printf statement that was left behind, and we were printing n. I'm not going into the syntax, this printf statement, okay? Now these are our first, this is our second, and this is our third statement, okay? Now what is happening over here, every time when we have this activation record at n equal to 1, we will check the condition. We will now call this function on n equal to 2. Now next time around, new activation record is called because this statement is left. This is not a tail recursion. This is a non-tail recursion. Now obviously we are not using efficiently the call stack, but now what happens in this case, we are creating a new activation record every time because there are statements that are left, so we need to keep track of that. So obviously if we check, it will call the function on n equal to 3, and still this 3 is left, the statement 3. Now n, it will check, nothing will happen, it will check, it will call it on n equal to 4. Now it will check, okay, this will return it. Now we have our activation records in place. Now to check the condition, okay, this is equal to 4, so we will return, and then we will execute the step, the last step, that is of printing. Now here in this activation record, these are our activation records, and in this activation record the n is left to be printed, which is obviously 3 will be printed. It will return to the function which is called, so it was called here. The next step is to print, which will be 2 printed, and then we will return 1 is printed. Obviously we keep popping out these from the stack. Now 1 is printed, 3 to 1 is printed, and finally we'll go to our main function, that is our driver function. So this is an example of non-tail recursion. Now if you observe carefully, you will see a lot of difference between a non-tail recursion and a tail recursion. In tail recursion, no activation record was there. Obviously there was a single activation record, but we don't need to maintain it as long as we keep on calling our functions, because it was the last statement and it was much faster, and the stack, obviously the space complexity was reduced. It is much faster than the approach that we used in non-tail recursion. Now let's talk about direct recursion. So when a call is made, right, when a function call is made with a function, right, and we call the same function. If you see in this example, this function f is calling the function f again, that is the same function. It is calling the same function again, and only one function is involved. So this is nothing but your direct recursion. We are not using any another function in this function. Let's suppose we have another function f dash. We are calling that f dash function, and in that f dash function we are calling f function. So that is not the case. Only single function is required, and we are playing around the same function. That is known as your direct recursion. So now if you see the example, we have already seen it, the print statement wherein we were executing, we are printing from 1 to n, we were having this function print, and in this we had the base condition, we were printing out this n, and then finally we were calling this print, obviously printf, and then we were calling this print on the same but different arguments, in the same function but with different arguments. So this is your direct recursion. Okay, now it might be self-explanatory to you guys that what will be indirect recursion. So when a function call is made on a different function, so if you see here we have a function f1, and in that function f2 is called, and in f2 another function f1 is called. So this function is there and it is calling this function, and this function it is calling this function. So two or more than two functions are involved in this type of recursion, and this is nothing but your indirect recursion. Now obviously there will be much more dependency in terms of function calls, right? As you can see, in direct we were directly calling the same function. In this we are calling different functions. Let's suppose we have this example wherein we were printing something from 0 to n, and in this function we have another function. We'll check the base condition and then we'll call our function. Let's suppose we are calling some helper function over here, and in this is a base condition, and then we are printing out some statements, right? And in this what happens, in this helper function we will be having some base condition, and then finally we will be calling this printf again on some arguments obviously, and let's suppose, and then we are printing something. So obviously now this function call is calling this function call, and this function call is internally calling this function call. So now we have, in this case, in this type of indirect recursion, the example that I have shown you, we are calling two functions. It can be more than two, but it will not be direct, right? Like we have seen in the earlier examples, that printf or the print function call was made again in the function, and it was the same function, that is print function, wherein we were printing from 1 to 3 or 3 to 2, 3 to 1, right? So this is the difference between indirect recursion and direct recursion. Now let's talk about recursion time complexity. Now if you see, if we have this print of function, right, and in this print function we had this argument n, And in this, we were checking the base condition first, right? This was our base condition. And then we had this print statement wherein we were printing what, n. And then finally, we were calling this print on n plus 1. So if you see in this recursion, we are traversing, right? If we have the same loop in here, right, n is equal to 0 and I is less than 3 or 4, we will print them, as we will do nothing. So if you see, the difference between this and this is not much. Obviously, in this, we are not using any space. We'll talk about space differently after this slide. So in this function, what is happening, we are traversing every time we are calling a function, we are calling this printf function on n, right? N times it is called. This function is called n times. First 1 was printed, then 2 was printed, then 3 was printed, and so on to n number of, obviously it depends on the n that is here and the base condition when it meets, right? So if we are traversing in this manner, that we are calling for every n, we are calling that function print again and again for every n, that means that the time complexity of this is big O of n, which is similar to this, but we'll talk about what is the difference between these two in the next slide where we talk about space. So this is straightforward, right? Now if you talk about binary search, now what is happening in that binary search, we have this array, and every time we are dividing our search space into half, right? Now we are dividing and we are looking for something that is on the either on the left side or on the right side. So every time we are recursively calling the function on the right side or on the left side. So every time we are breaking our problem into two every time. So when that is the case, even if we are using recursion, right, we will check if start is less than end, and then we find the middle, we check the base condition. If that is the case, we will return. Then we find the mid, right? This is what happens in binary search. We'll talk about these in searching algorithms, right? And therein we will see both implementation, the iterative implementation of binary search as well as the recursive implementation. And then what we will do, we'll check if this mid is greater than ARR of I. That means if this middle position element, right, if ARR of mid is greater than ARR of what? ARR of this left hand side, right? That is here. If the ARR of is greater than the item that we are looking for. Let's suppose we are here at 3 and the item that we are looking for is 2. Now ARR of mid is greater than, that means the element will be on the left side, then that means it will never be on the right side. So what we will do, we'll recursively call this binary, but with the updated, like we have seen in printf statements, but the updated end part. Let's suppose this is the end, and we'll update our end to mid minus 1. Okay, so mid minus 1. So whenever we are using this scenario wherein we are skipping half of the portion, or every time we are dividing our search space into two, that time we are using recursion. Even if we are using recursion, the time complexity will be still big O of log n. Okay, so this is about recursion time complexity. Now you might be thinking, okay sir, now this time, there is not a lot of difference between time, but when we talk about space, even if in that linear search, right, even if we have the linear search or the print that we have seen, that we were printing from 1 to n, we are not explicitly using any memory, right? But there's a difference when we are using that statement wherein we had that n equal to let's suppose n equal to 4, and then we were printing, and then we had the last statement as our recursive call. Therein we are reducing the space complexity, and the space complexity is constant in that case because we are not creating any extra activation record, which was evident, right? We were not creating any extra space. But obviously when this recursion is not maintained, this tail recursion is not there, and we have a non-tail scenario, at that time the space complexity will be big O of n. Okay, is that clear? Right? So at that time, we have this big O of n, but what if we have this tail recursion? At that time it will be constant, and it will be for all the scenarios. Okay, wherever you are creating any new actuation records, be it binary search or be it a normal print statement. So in this case we will be having big O of log n, but in that binary search wherein we are dividing our search space, at that time we are only creating what, log n times. We are only creating, if we have 8, n is equal to 8, that means the array length is 8, and we are only traversing 3 times, that means this is a log n situation, and we are creating only log n amount of space, log n times the activation record is created. So at that time the space complexity will be big O of log n. Similarly, in this case, every time you're calling this function, if we are using tail recursion, then it will be constant, but if we are not, it will be big O of n. So this is the space complexity. Now let's talk about searching algorithms. And the first searching algorithm that we are going to talk about is linear search algorithm. So what is linear search? It helps us to search an element in a linear data structure. Now let's talk about one example wherein we will be searching some element inside the array. So let's suppose this is an array and the elements are 10, 20, 30, 40, and 50. Now, if we are trying to search an element that is 50 inside this array, how linear search works is that it checks each and every element that is to be searched, right? That is there in the element array, right? Let's talk about this example here, 50. Now 50 will be compared, right? We'll check, is this 10 equal to 50? No. Is this 20 equal to 50? No. Is this 50 equal to 30? Is this equal to 40? Is this equal to 50? Yes. So here we were able to do a linear search, right? We were searching for this element inside this array one by one. We compared first it with 10, then 20, then 30, and then 40, and finally then with 50. At the end, we were able to find this element in the array in a linear fashion. Now, this is what is termed as linear search. Now let's talk about linear search algorithm. Since it is a very straightforward, or you can say a brute force algorithm, right? It's a brute force algorithm of finding the element in the array. So this is how it works, right? We have one for loop wherein we will be what, iterating through all the elements, that is from 0 to n, and inside that what are we doing? We are looking for the item, that is that element that we want to search, right? Let's suppose this is 50, right? This 50 will be, we were checking if this 50 is equal to the element that is ARR of I, right? And then if that is the case, if we find out the element in the entire array, we will return its index, right? That is index, right? That I, we will return this I. Now there might be the case as well, if we are at the end of the array and we have exhausted the last element as well, and we were not able to find this 50, right? Let's suppose this is 10, 20, 30, and 40. Now this 50 is not present in the entire array. At that time, what we are going to return is -1. So we will say that, okay, we were not able to find this element whenever we are returning this -1 in this array. And this -1 indicates that we were not able to find that element. Now let's look at this demonstration wherein we are trying to search for an element that is 20 in this array. And the elements in the array are 23, 10, 16, 11, and 20. So now in the first iteration where I is equal to 0, we'll check, is 23 equal to 20? No, it is not. One iteration is done. In the second iteration, we will compare 10 with 20. No, it is not equal. Second iteration is done. In the third iteration, what is happening? 16 is compared with 20, right? This 16 is compared to 20. No, we were not able to find this. This is the third iteration. In the fourth iteration, 11 is compared with 20. Now, this 11 will be compared with 20. No, we were not able to find this 20. Now, in the final iteration, that is iteration number 5, 20 is equal to 20, and then at that time we will returning the index of this array, right? At this location, what is the index? It is 4, right? So we can say that we can either return 4 plus 1, specifying that okay, it is the fifth element in the array, because indexing always starts from 0, that is obvious, right? So we can either return 4, or we can either return 4 plus 1, depicting that this is the fourth, or we can say that it is the fifth element in the array where we were able to find this 20. Now if this 20 would have not been here, right, let's suppose this is 24, right? In that case this will not be equal to 20, right? 24 will not be equal to 20. Now in that case we will be returning minus 1, because at that point when we have exhausted this entire array and we were not able to find any of these indexes that is there, so which specifies that this is at present at that particular index, so we will be returning this minus 1, depicting that we were not able to find this element in the entire array. Now let's try to understand the implementation of linear search. Now it is obvious that it will be returning the index, so that is why this method that is there, the linear search method, is having a return type of integer. So this is the integer array that we are taking in as an argument, right? Let's suppose this is 10, 23, 30, and 40, and 10, 50. And this is the name of the array as ARR. So this is the first argument. The second argument is the target element. That is the element we want to search. Let's suppose 50. So this will be 50. And then n is the size of the array, which is in this case 0, 1, 2, 3, 4, which is 5, right? So now we are traversing from 0 to n times, right? So we will traversing for 0, for 1, for 2, for 3, and for 4, right? And then we are looking, or we are searching for AR of I and comparing it with target element, which is 50. Now in first case, or you can say that in first iteration 10 will be compared with 20. Is 10 equal to 50? No, it is not. We will move on to the second iteration. Is 20 equal to 50? No, it is not. And then we will move to third iteration and so on. When we are at the fourth iteration, right, 50 is equal to 50. Now in that case we will be returning the index, that is this 4 is returned. So 4 is returned, and this will never be executed because we are exiting this whole method before that, right? So in that case this 4 will be returned and this int will contain 4. Okay. And now what if we would have been searching, or we would the target element would have been 60, right? In that case this if will never be executed, this if block will never be executed, and in that case we will be returning minus 1. So this integer will contain minus 1 in that case, right? So now let's try to implement this using code blocks. So we are implementing it on code blocks, which is an ID, and the language we are implementing it in is C. So now if you can see that we have this linear search method that is there, right? Here you can see, and we are doing the same stuff, right? We are iterating through the entire array and we're looking for this target element, and then we are returning either I, that is the index of the element, or minus 1. So now let's minimize it. Then we have our main function, or you can say the driver function. In this driver function, we have one static array which contains 22, 6, 41, 0, 1, and 19. Then the target element that we are looking for is 4, right? Or you can say, or not 4, it is 1, right? So the element we are looking for is 1. So if you can see what is the index of this 1, right? So 0, 1, 2, 3, 4. It is on the fourth location, or you can say the index of this element is 4, right? So we should get an output as 4. Now let's look at the how do we calculate the size of this array with the help of size of operator. We calculated its size, and then whatever is returned with this linear search method is stored in answer. In our case it will be 4. Now linear search is called and we are passing in 3 arguments. The first argument is the array, the second the target element, and third the size of the array, which is in this case 0, 1, 2, 3, it is 6. Okay. Now whatever is written in this answer, we are checking if this answer is equal to minus 1, we would have printed the element is not present in the given array, element not present in the given array. Else we would have printed element found and the index, not the exact index, but it will be index minus 1, or you can just return whatever is this, you can just add 1 to it, okay, so that you get the appropriate index, right? In this case it will be the fifth element, or you can, now since we are talking about the index, so index is 4, or you can change it, the element is found at, or you can say element found is the hmm, so now what you can write, you can also write person D, that means is the fifth element, right? Fifth element in the entire array. It is the fifth element. Okay, fifth or fourth or fifth. Okay, so we got the point, right? So person D, th, that means fourth, fifth, sixth element in the array. In the array. Right? It is the fourth element in the array. Now, if you're playing around with indexes, then you can just write answer. That's it. Okay. So now we are again calling it, but this time around we are looking, or the target element is 7. Since 7 is not in the entire array, what we are looking for, we are checking if answer is equal to minus 1. In this case, it will be minus 1 because the 7 is not present in the array. So what we are printing, element not present in the given array, right? So now let's save this file, and now let's try to debug it, build and run. So when we debugged it and run it, we have fifth element in the array, right? The element that we were looking for is the fifth element, right? If you can see, and in the next case, the element is not present, or element not present in the given array. Now let's press enter. Now if you see the one that we were finding earlier, the target element was 1. It was 1, 2, 3, 4, and fifth element in the array, right? Now if we are trying to play around with the indexes, right, you can just write this thing, element found at element found and then the index. Now let's save this, and we don't need this plus 1, and this time around let's save this file, and now let's try to build and run this again, and this time around we found element found, and it is at the index 4, and then in the next case element was not present in the entire array. So in this way, we were able to run our code using code blocks, and the language we implemented it in was C. Now let's talk about the time complexity of linear search. Now, if you observe carefully, let's try to understand this best case, right? So now if you are looking for the element, and let's suppose these are the elements in the array. Now, let's suppose in best case, what can happen? You're looking for 10, and 10 is the first element in the array. Now, how many iteration did you require? Did it require to find you the 10? None, right? The constant time, right? Only one single unit operation was done, and you were able to find this 10. So this is the best case time complexity, where the element that you're trying to find is the first element that you search, right? In this case, you are looking for 10, and 10 is the first element. So this is your best case. Now, what about the average case and the worst case? Now, let's suppose average case is that you were looking for an element which is at the middle point, right? Let me just see. 0, 1, 2, 3, 4. Now, or you can put another and looking for 60. Now, in this case, or you can just skip it, okay? No need to add one more. Okay, so now you're looking for an element which is somewhere around in the middle. Okay, in this case you're looking for 30. Okay, so now if you observe, you are only iterating half of the elements, that is 5 by 2, which is nothing by n by 2, since constants doesn't play in do not play any role when you're talking about time complexity. So that is why average case still boils down to big O of n. Now what happens in worst case? You're looking for an element that is 50 and which is present at the end of the array, or in the worst case you're looking for something that is not present in the array, that is 60, let's suppose, and in that case you will still iterate through the entire array, and that is why the worst case time complexity in that case will be big O of n, because you are iterating through the entire array and that element was not found. You're looking for 60 and that is not present there. So you're iterating through the entire array. That is n operations are done. So that is why it boils down to big O of n. Now let's talk about the space complexity of linear search. When we are trying to find the element in the array that is 10, 20, 30, and 40 and 50, we were not using any extra memory, right? We were not using any auxiliary memory, that is what we mean by auxiliary memory or extra memory, in order to find that element. We were just looping around these elements one by one, and we were doing it on this particular, on the same array that we were given, right? Since we are not using any auxiliary memory, that can be in the form of what? A stack, a linked list, or an array, or a string, or a queue. We are not using these auxiliary memories because they are not required, right? We are searching for an element in this particular array that was given to us, right? So the space complexity of linear search is constant, right? We were able to find it in a constant amount of space. Okay, we are not using any extra space. Now let's try to understand binary search algorithm. What is binary search? So binary search is one of the searching techniques, right? Like we saw in linear search, wherein the time complexity of linear search was big O of n, right? We were iterating through all the elements, and now this is a much more efficient algorithm as compared to linear search. Now again, why do we need searching is the thing that, let's suppose if you have a given set of elements and you want to search if that element is present in your array or not, that time, right, we can use either linear search or binary search. Now binary search is much more efficient and it is used on a sorted array, or it can be used on an array wherein some order is maintained, because based on that order we will divide our array, right? It is a searching algorithm which is or which follows the divide and conquer strategy, right? Let's suppose this is our array, and now since it will be divided in such a way that we can neglect one part of it, right? We will be dividing and then conquering. That means we will be then searching for our element. Now, let's suppose we are looking for something that is, now let's take an example wherein this array is written, or the elements contained in this array are in such a way that we if we skip this part, or the left hand side will be skipped or the right hand sides can be skipped in such a way that they don't affect our output. So every time in linear search our search space is reduced unless and until we find that element or the array is exhausted. Okay, so our search space is reduced to half in every iteration. So this is what a binary search is. We'll look for an element in such a way that every time we are neglecting half portion of the array. And let's take an example when we have this entire array. So first half, that means if if there are 8 elements, 4 on this side, 4 on this side, these 4 will be neglected. Then we have 2 on this side, 2 on this side. These 2 will be neglected. Then 1 on this side, 1 on this side. Then this one will be neglected unless and until we find that element or the entire array is exhausted. Right? So this is how your binary search works. Now let's try to understand binary search algorithm. So first we are going to understand the iterative approach, and then we are going to understand the recursive approach. So iterative, as the name suggests, we are going to use for loops, right? We will start with a for loop and it will iterate, and we will iterate unless and until the beginning is less than the end, right? So because we will be updating our both beginning in some cases, and in some cases we'll update our end. Now what happens, now since we know that in this iterative approach or in this binary search, it doesn't depend whether we are using iterative approach or recursive approach, the logic will remain same, right? So we will be having this array and it will be in some order so that we can neglect some part of it. It doesn't have to be sorted always. We can still apply binary search even if the array is not sorted, but still some order is there so that we can neglect some part of it. Because again, keeping this thing in mind that it follows the paradigm of divide and conquer. So now we have this beginning and end at place, and we will always iterate when beginning is less than end, right? So now what happens after that? Now we have this array, and now what we will do, let me take new pointers. So this is your beginning and this is your end. So this is your beginning and this is your end. Now you will be taking a new middle index, right? M, let's call it M. And now let's name these things 0, 1, 2, 3, 4. So you will do what? Beginning plus end divided by 2 so that some part of it can be neglected, right? So it will be 2. So your mid is at this position. Now you will see, okay, the element that I'm looking for is, let's suppose, is 50, and the element that I am currently at is 30. So obviously it will be never from this side. There is no chance that we will be able to find 50 from this side, that is the left hand side, right? First we will check, okay, is this 30 equal to 50? No. So this will never be executed, right? Then we will check, is my item that is there, is this 30 less than or greater than 50? If it is greater than 50, right? If the element that is, if item that is 50 is greater than 30, right? Which is in this case, our 50, that is the element that we are looking for, the item is this point, is greater than 30. So there is no point that it will be on this side. So we will skip or we will neglect this half portion of the array. So that is why our new beginning is updated. It will be new, it will be middle index plus 1, that is middle index was 2 plus 1, that is this will be our new beginning. So we have smartly skipped the half portion of the array. So now let's rub all of these things and now let's see what happens in the next iteration. Now we'll keep this thing in mind that we are not looping or we are not exceeding this limit, that is beginning should be always less than, or it should be always less than or equal to end. Okay, so this condition should be maintained. And similarly we'll again divide our array and then look for the same things, right? First we will look for the element, then we'll skip some part of it. So this is the iterative approach for binary search, right? Now let's look at the recursive approach or recursive algorithm for the same. So again, beginning, the ground rule will remain same. We'll always iterate or we will always recursively call binary search unless and until this beginning is less than end. Done. Now what happens, we'll again find middle index, that is beginning plus end divided by 2. Then we will look for the element. These three steps will remain same even if you're using recursive approaches. Now what happens in recursion, right? We again call the function again and again. That is what is recursion. So in this entire tutorial we will be covering recursion as well, but in the later part of the course. Here you can get a good intuition, or let me give you a brief intuition about how recursion works. So let's suppose this is your activation record. Every time when a recursion is there, an activation record is called. So let's suppose you have these three statements. And let's suppose in your algorithm you have statement P1, P2 and P3, right? And at P2 you're calling the function again, right? You're calling this function again. So now what happens, an activation record is called. He will check, okay, is this statement executed? Yes, so one will be executed. Is second executed? Yes, so second is executed. But at second you're calling this function again, so at that time again a new activation record is created. Now this third step is left behind, right? Now this will be covered when we come back or return from this function call that we called here. So let's suppose this function was here. Now in here, you are returning, right? This function called, let's suppose this is not less than beginning. Beginning is not less than end. So this will be somewhat, this case is relatable, right? This is similar to what we are looking for, right? Let's suppose there is some similar situation wherein beginning is not less than, and at that time you will be returning from this. Right now, once you have returned, you will be then calling this function again, but this time around for this. And let's suppose this time around you are calling this one is executed, step one is executed. Now again, this activation record is called, this activation record is one, and then again this is called, right? This is executed again, this two is called again, a new activation record will be created, and these three steps, the step third will be still left for execution. So now here you return, right? Then it will go back to this step, right? And then once you are done with this, now there are two positions or two possible scenarios where you can return. Either you are returning from this function, just like we have executed this condition and we return, right? Another is that once you are done with this entire activation record, at that time you will also return. Okay, so these are two scenarios. Now you have executed this, there is no step to be executed, it will return. Now this was left behind, this will be executed. Now nothing is to be executed, it will go to the caller, which was this, and finally it will go to the main method wherein we call this at the first place, this function. Okay, so this is how an activation record is created, a stack is maintained. Okay, even if you might be thinking we are not using any extra space, but whenever recursion is there, an extra space that is in the form of stack, that stack is maintained. So you need to keep this thing in mind while you are playing around with space complexity at the time when you're using recursion. Okay, so now with that being said, let's clear our screen and let's see how recursion is called here. So again, now recursively what we will doing, if now we have this mid, right? And let's take an example of an array 0, 1, 2, 3, and 4, 10, 20, 30, 40, and 50. So middle index will be 0 plus 4 divided by 2, that is 2. So this is our middle index, right? So this is 0, this is our beginning, and this is our end, right? So now we are hit here, right? So we again check the 50 that we are looking, this is our item that we are looking for. Okay, so is 50, and this is our middle index, is 30 greater than 50? No, it is not in this case, so this will never be executed. This is not executed as well, right? Now, what about this condition, the else part? Now, what we will be doing, we'll be skipping, since this 30 is less than, we'll be skipping this part and we will focus on middle index plus 1, which is nothing but this. So this will be our new beginning and our process will start moving, right? So now again, then the same thing will happen unless and until this condition is false. Okay, so this is how your binary search works when you're using recursion. So now let's try to understand binary search and let's see its demonstration. Okay, so we are looking for 20 and this is our array, right? 10, 11, 16, 20, and 23. Now this array is sorted, right? So we can apply binary search. Okay, since we can neglect some part of the array based on some conditions. Okay, so now our beginning in the first iteration, what is happening, our beginning is 0, our end is 4, and our middle is this element. Now what we will be looking for, is 16 equal to 20? No, it is not, but 16 is less than 20, so we will skip this part. In the next iteration, what happens, we'll be focusing on these three elements, right? That is 20, we will be focusing on this part, rather, if we say, we'll focus on this part, right? Focus on this part. Okay, so now in the second iteration, what will be happening, our beginning is updated. Now our new beginning is this point, our end will remain at its own position. Now we'll find the middle index, so it will be 4 plus 3, that is 3, that is 7, right? And divided by 2, it is 3.5, right? So since this will be truncated, right, the truncation will happen and the integer that is there, the middle index will be 3. So this is our middle index, right? So you can see middle index is 3. Now, is this element that we're looking for? Yes. So we'll return the index. So we found our element at index 3 and hence we return 3, because if you observe carefully, it is returning if the element is found, it is returning the index. So this will be returned. Okay. So this is how binary search works. Now let's try to understand the implementation of binary search. First, we are going to see the iterative approach, right? We can see the iteration here. First, we see the iterative approach, and then we will see the recursive approach. This is the recursion, right? So now let's see first the iterative approach. As you can see, in binary search method, we have four arguments. One is the array, second is the item that we are looking for. Let's suppose it is 50, then the beginning index, that is 0, and the ending index, let's suppose it is 5, and the array that we have is of in the length of that array is 6. Okay, so this is the ending index. So let's suppose we have these elements 10, 20, 30, 40, 50 and 60. Okay, done. So now we are returning, obviously, if there is no element, like let's suppose if we are looking for 70 and that is not present, so at that time we will return -1. So this return type will always be there, right? Because in either cases, right, if we don't have an element, we will return -1. If we have an element, we will return middle index. That will be the index of that element that we are looking for, that is the item. Okay, so in this case we are looking for 50, right? So beginning should be always less than or equal to end. That means we will not cross or will not see the situation where beginning is at, or where beginning is greater than end. We'll see this case as well. Okay, so now let's try to do a dry run of the things that are there, that are here in this iterative approach. Okay, so now let's see. So first we will try to calculate the middle index. So what is middle index? How do you calculate it? It is beginning plus end minus beginning divided by 2. Now why we are doing this? Let's suppose the integer is of size 200, right? And earlier what we were doing and this is the size of the integer, and beginning is, let's suppose, 100 and end is 200. Okay, so now in this case, let's suppose this is the beginning plus end, that is 200. Now when we add this comes out to be 300, then do we divide by divided by 200, but this then we divide it by 2, right? So this 300 makes this go out of the range. Now this is an overflow condition. Now to avoid this overflow condition, we will be using this. So it is 100 plus end, that is 200, minus 100, right? And then we have divided by 2, but this boils down to be only 200, which is still in the range of this 200. So you get the point, right? So this is for the same reason, to avoid overflow conditions. We use this beginning plus end minus beginning, end minus beginning divided by 2. Done. Then we will look if the middle index. Now let's try to calculate the middle index here. Let me just erase these things. So first, what is the end index? In this case, it will be 5. And what is the starting index? It is 0. So 0 plus 5 comes out to be 2.5, which boils down, when we do the truncation, which boils down to 2. So the middle index is nothing but 2. So your middle index will be here. And this is your beginning and this is your end, right? Done. So now what happens when we are trying to search for the element, that is middle index element is equal to 50. No, it is not. 30 is not equal to 50. So now where we will go, we'll go in the second if block. This will not be executed. Then we are looking for, obviously now this 30 is less than 50. Obviously there is no chance that we will be able to find this 50 from this side. So we will reject, or we neglect this part, right? And now our new beginning will be beginning is equal to middle index plus 1. That is, our beginning will be now here. So these are the 2 pointers that we take care of. The beginning, that is middle index plus 1, new beginning, and the end will remain same. So this is what happens since our middle index element was less than our item. So this will be executed and will not go into this, right? Again, now we'll check, is our beginning, right now our beginning is 3 is less than 5. Yes, it is. So again, we'll calculate what middle index, which will be 3 plus 5, that is 8 divided by 2, which is 4. Now this is our middle. So now I'm saying beginning plus end, but you actually what will happen, right? So our beginning is at 3. So this is 3 plus 5 minus 2 divided by 2. So it boils down to what? 5 minus 2, that is 3,
divided by 2 plus 3. So what happens? This will come out to be what? This will be 1.5, something like that, and zero point 0.5 will be truncated and you will get 1, and 3 plus 1 is 4. So your middle index is 4. Now this thing is done, and then the second step is that you will try to find out this thing, right? Let me just erase it, this thing. Our middle index is now 4. So you see, in this block, what will happen? ARR of middle index, that is ARR of 4, is it equal to the item, which is 50? Yes, 50 is equal to 50. So now what you will be returning? The middle index, which is 4. So 4 will be returned and nothing will be executed from this point onwards. Done. This is the iterative approach. Now let's look at the recursive approach. So now for recursion, there is one thing that you need to keep in mind, right? What is that? So recursion internally uses stack, or it also uses activation record, right? So let's suppose these are, let's suppose you have three statements, right? P1, P2, and P3. This is the condition where you check the base condition. This is the recursive call, and then this is a print statement. So now when this activation record is created, 1, 2, 3 needs to be executed. But if this if block is not executed, right now we are not at the base condition, so this is done, right? The second thing is we are calling this recursive function again. So what will happen here? We get the recursive call, and again the activation record will be created. So now this statement 3 is left behind. Again, what will happen? 1, 2, and 3 needs to be executed. So 1 will not be executed because we haven't reached the base condition. Then 2 will recursively call again, and this is left behind. So another activation record. So since it will be formed in terms of stack, right? So this will be the first activation record here, then the second activation record, then the third activation record, and one by one it will keep pushing it up in the stack. So now once we have reached the base condition, it will return. So this is the one return condition wherein you will reach the base condition, right? This is how you return. The second return is this. Now this will be popped out of the stack. Now what is the leftover statement? This is the leftover statement. Now this will be executed. Now once this is executed, that is the printf statement, whatever it is, it depends, right, upon what you're trying to do. So now this recursive, this third statement will be executed. Now this is how you return the second time. This is when your whole activation record is done, right? There is no statement which needs to be executed at that time. You will also return. So this is the second return. So you will return back. Now again, it will be popped out of the stack. Then it will be executed. This statement, the third statement will be executed because the pointer which will reach at this point, right? Because this is done, this is done. This was the leftover statement. So this will be executed. So this is executed and it will return to the main function which it called. Now therein we have also main function at the beginning, right? That called the first function, right? So this activation will be recorded and main function will be popped out once we are done with this entire program. Okay, done. So this is a brief intro about how recursion works. We have a separate topic, recursion, wherein we will be talking about these base conditions, activation records, and all those things more in depth, and we'll also see some examples at that point. Okay, so we are taking one array. We have the item that is 50. We have beginning index. We have ending index. Okay, done. And now we again check end should be greater than beginning. There should not be the case where beginning is greater than end. And then we find out the middle index, same as we did in the iterative approach. And then we check if array index is equal to the item. If yes, then we return the middle index. Else, what we will do? If array index is greater than, then again recursively, here you see the recursion. Recursively, we are calling this binary search again, right? With revised arguments, that is array, item, beginning, but our middle index will change because the right hand side is not valid because the element is less than the item, right? So the middle element is greater than the item, so obviously it will not be from the greater side, so we are reducing from the end. So our end will be middle index minus 1. So we have beginning and the middle index minus 1 will take care of the left hand part. Okay, so else if it is greater than, that means it will be on the right hand side, so we'll recursively call this will be called recursively. So at that time beginning will change, which will be middle index plus 1, and will remain as it is. If our whole array is exhausted and we're not able to find the element, at that time we will return minus 1. Done. Now let's see its implementation in code blocks. Okay. Here you can see we are using code blocks and we have implemented it using C language. So we have this binary search method wherein we are implementing it iterative manner. So it is same what we have explained, right? What I explained you earlier. So we have the binary search which takes in several arguments. We find out the middle index. We check if that middle index is equal to the item, the array of middle index, obviously. So then we check if it is greater than or if it is less than, we do the stuff, right? Done. And in the main function, we have the static array, right? 13, 45, 65, 82, 117. It is sorted. Then we find out the length of the array with the help of size of operator. Then we need to see this item 82 that is there. We want this item to be found in this array. So obviously it is at index 0, 1, 2, 3. So 3 should be our answer. Then we call the binary search and answer. Whatever is returned, we kept it in the answer. So we check if answer is -1, that means element was not present, else we print the index. Okay, done. Let's build it and run it. Okay, so our answer should be 3. Index 3 is our answer, right? Now what about the recursive one? So you see binary search, and now here we are using recursion. You see recursively we are calling binary search with the revised arguments. That is what happened. That is what happens in recursion, because we need to keep that function same for all the function calls, but with revised arguments. Only then we will reach this condition where end is greater than or equal to beginning. And when that is the case, that means we haven't found our element, and at that time we will return -1. That so in that this thing is clear to you guys, right? And in the driver function, we are this time around we are looking for 117. So the index will be not 3 this time, index should be 4. Okay, now let's run this thing. Our answer should be 4. Yes, it is. So in this way, we saw both the implementation, that is using iteration as well as using recursion. Now let's talk about the time complexity of binary search. Now in the best case, now what is the best case? Now let's take an array, and in that array 1, 2, 3, 4 and 5. These are the elements. Now the best case is that not that if the element, like we saw in linear search, this element, when we are looking to search for this same element, at that time that was the best case scenario for linear search, right? But in this binary search, the best case scenario is when your middle index is at this location, and you're searching 3 in the entire array. So at that time, this will take a constant amount of time, and this is the best case time complexity in that case. Okay. Now in average case, what happens, right? If you talk about this algorithm, let me just clear out my screen. So it follows a paradigm of divide and conquer. So let's suppose you have 8 elements first in the array. It will be divided into 4, because these 4, or either it can be on the left side or on the right side, will be neglected. And then we deal about these, then we focus on these things. Okay, these 4 elements. Again, it will be divided into 2 and 2. Then we will neglect 2 elements. Then 1 and 1. Then again, there will be one of the element can be neglected. So there are 1 and 1. So we focus on this element. So the entire operation will be done, or entire searching will be done in 3 steps, right? Now, I take an example, and if I do a log 8 to the base 2, what should be the value of this? Obviously, when I do this can be written as 2 raised power 3, right? And this can be written as 3 into log 2 to the base 2. Now this is 1, and now you get the answer as 3. So this 3 and this 3 are equal. That means if I talk about the worst case time complexity of binary search, it will be somewhere around log n. As we saw in 3 steps, we were able to find the element, and the log n, that means log 8, the answer of that is also 3. So you get the point, right? So the worst case time complexity of binary search is log n, and same goes for the average case, wherein it will be somewhere around log n divided by 2, neglecting log n divided by 2, neglecting the constant terms. It will be again, or it boils down to big O of log n. Okay. Now let's talk about space complexity of binary search. Now, when you talk about space complexity, right, we only think of auxiliary memories, or you can say that what any extra memory that you guys have used. Since we did not use any extra memory, that can be in the form of array, or it can be in the form of stack, or it can be in the form of queue, or linked list, or even strings, right? Since we never use these extra memories in our implementation, so the space complexity of binary search is bigger of one. That is, it takes a constant amount of space. Bubble sort algorithm. Now let's try to understand what is bubble sort. Now before we understand that, let's try to understand the word sorting. So sorting is nothing but arranging your numbers or set of students with respect to what roll numbers. You're trying to sort them either in ascending order or in descending order, right? So it is one of the easiest and one of the brute force sorting algorithm. Now easiest is self-explanatory, but what do you mean by this brute force? It means straight forward, right? So it is a straightforward algorithm wherein we will be comparing first element with every other element in the array, right? So with this, we can either sort our array in ascending order or in descending order. Now, basically what we will be doing in this algorithm, we will also talk about its algorithm, time complexity and all those things, right? But here we can get a brief idea that we will be swapping elements, and we will be swapping them in such a way that with each iteration the last element that is there will be the largest element in the whole array, because we will be trying to sort our array in this video. We'll be sorting them in ascending order. Okay, so the last element that is present in the array will be fixed in the first iteration, and it will be the largest in the array. And we'll be using or implementing this bubble sort with the help of nested loops. Now, what do you mean by nested loops? That it means that we will have a for loop, and inside that for loop will be another for loop. So this is what I mean by nested for loops. Bubble sort algorithm. So as you can see that in this algorithm, as I told you earlier, when we were talking about what is bubble sort, in that I told you that we will be implementing this bubble sort with the help of two for loops, that is the nested for loops. So as you can see, we have two for loops. That is, this is the first for loop, which in this we will be iterating from 0 to n elements. That means if there are 5 elements, we'll be traversing from 0 to 4. So with that, every element will be compared with the rest of the elements. So that is done with the help of this second for loop, and don't worry about it right now. This I, why I'm subtracting I from n minus 1, and why n minus 1 I'm doing, let me clarify it here, because we are comparing the jth element with j plus 1 element. Now when our j is at the second last element, that means if this is the array, and let's suppose this is the array, and j is here, the second last element, at the second last element it will be compared with this element. Now at the last step, wherein if j would have been here, it would have been compared with the element which is not there, so it would have resulted in error. So to avoid that error, wherein we will get this element, we are trying to access the element which is not there, we are subtracting 1 from n, so thus keeping it within the array, right? And what about this I? It will be covered in the next slide, wherein we will talk about one example, and where there I will talk about this I, why I am subtracting this I again and again. Okay, now if our j is greater than j plus 1, let me take an array here. If j is greater than j plus 1, that means this element is greater, we swap them. And we swap them in such a fashion that after the first iteration that this loop does, the entire iteration of this loop, when this loop will be exhausted, the last element that is there will be largest element in the array. Okay, done. And then we will start moving to the next element, and we will start our iteration again from 0th element, right? Because they would have swapped. Now, this might not be clear to you guys right now, but let's take an example and let's see how it works. So as you can see, this is our input array wherein we have 23
10, 16, 11, and 20. So these are the elements in the array, and the index of this is the last element is 4. That means the end here, the size of the array is 4. Okay, done. Now that we know this is the array, now let's talk about the first iteration. So the outer loop will work from 0 to n, right? So that means the outer loop that I is at right now is at this location. And what about that j, the inner element? So that is this j. Where is it? Let's talk about that. So if you can see, j is right now at this location and it will be compared with j plus 1. Okay, so now what happens? So this 23 in this j and this 10 will be compared. So since 23 is greater than 10, we will swap them. That is what is happening, right? We will swap them if j is greater than j plus 1. So once we have swapped them, so you will get 10 here and 23 will be here. So 10 here and 23 will be here. Now we increment our j. So j will be here. Again, it will be compared with the 16. Again, it is greater than. So we have 16 here and 23 here. Now 23 is here and it will be compared with 11. Again, they will be swapped. So 23 will be here. Now, after this iteration, the last iteration, what happens? This 23 and 20 will be compared. These will be swapped. And at the end, we will get 23. Now, that is what is done in the inner loop after the whole inner loop is exhausted. Right? It is exhausted once, the inner loop. Okay. So this is what you get, right? It's 10, 16, 11, 20, and 23 at the end. Now, what happens? I told you the one condition, that is n minus I minus 1. So n minus 1, why we are doing this? This is clear to you guys, just to avoid that error situation. But now, this I. What is the value of this I in the first iteration? It is 0. So nothing will happen. So your n is 5, 5 minus 1 minus 0. Or if you have written this, it will be 5 minus 0 minus 1. That is 4. Okay, so the inner loop will work 4 times. First, it will be compared. This is the first iteration. This is the second. This is the third. This is the fourth. So 4 times your inner loop will work. Now, next time around, in the second iteration, our I is 1. Now, this time around, what happens? It will be 5 minus 1 minus 1. That means it should iterate only 3 times. That means we will be comparing this element with this element with this element with this. Do we need this element to be compared? No. Why? Because this is in the entire array, this is the largest element and its position got fixed during the first iteration. So that is why I'm keeping this n minus I minus 1 or n minus 1 minus I. It doesn't matter. Okay. So now this thing is clear to you guys why I'm subtracting this I. So now next time around, what happens? This 10 will be compared with 16. So nothing will happen because 10 is less than 16. Next time 16 is compared with 11. They will be swapped. 16 will be here. Next time 16 will be compared with 20. Nothing will happen because 16 is less than. So after the second iteration, you will get 10, 11, 16 and 20. So again, now you see this was not compared after the first iteration. Now after the second iteration, we will not compare this element, these two elements, because they are at their original positions. Now what happens in the third iteration? Again, let me go back first. So now what happens? Let me just clear the screen. So these two will be compared. These two will be compared. So 10 is less than, 11 is less than 16. So nothing will happen. So you will get 10, 11, 16, 20 and 23. In the fourth iteration, so now only these two elements will be compared. So nothing will happen and we will compare these two elements. And after third iteration, these will be the elements 10 and 11 and this. So after that, on the fourth iteration, nothing will happen and we will get our sorted array. So this is the whole demonstration of how bubble sort works. So your elements will be placed like a bubble. So after first iteration, the largest bubble that is there will be at its original position. After second, the second largest. After third, the third largest. After fourth, the fourth largest. After fifth, the fifth largest. So this way around, like a bubble, all your elements will be sorted. Now let's talk about bubble sort implementation. So this is the method wherein we are implementing our bubble sort. In this method, we are the first argument that is there is the array, that is our array, that is this array, wherein let's suppose we have 0, 1, 2, 3, 4, 5, 6, and 10, 2, 3, then 4, then 1, 9, and 0. These are the elements in the array. And the size, now this is very important. What are you passing? Are you passing n minus 1 from the driver method that will be there? Are you passing n minus 1 as your length, or are you passing n? So it depends upon what you are passing. Okay, so let's suppose I am passing the size, that is the length of the array, which is, we have index 6, that means 7 is the length of the array. I am passing that 7 here. Okay, so size is 7. So now accordingly, what I will do, let me just clear out this screen a little bit, and let's go and debug it. Okay, so now what happens in this outer loop? So index I is referring to this index, right? 0, iterator I, and then we have iterator j, which is also pointing to this 0. Now we know why this size minus I minus 1 is there. This is clear, right? Now this j will be compared with j plus 1. And then what we will doing, we'll be swapping them if j is greater than. That means this will be 2 and 10. Then our j will be incremented, and this will be pointing to this new j, right? This will be our new j. So 10 and 3 will be compared. So these will be swapped. We have 3 and 10. Then 10 and 4 will be compared. We have 4 and 10. Then 4 and 1 will be compared. Then we have 1 and then 10 and 1 will be compared, then we'll have 1 and 10, and then we have 10 and 9, then obviously we will be having 9 and 10, then 10 and 0 will be having 0 and 10. So once this entire iteration is done, wherein we will be swapping these elements, so after one iteration, what will be our value? It will be 2, then 3, then 4, then 1, then 9, then 0, and then 10. So this will be after one iteration. That means this entire for loop has been exhausted once. So now after that, the next time I will be incremented, and that will be pointing to this one. And our j will start again from this pointer, and it will be compared with this. 2 and 3 will be compared, nothing will happen. 3 and 4 will be compared, nothing will happen. 4 and 1 will be compared, and therein the swap will take place. That means 1 and 4 will be swapped. 4 and 9 will be compared, nothing will happen. 9 and 0 will be compared. Now swapping will occur. That means 0 and 9 will happen. And then this element will not be compared because of this condition, size minus I minus 1. Okay, so this is the implementation of bubble sort. Now let's go ahead and we will implement it. Obviously, this implementation this might seem to be language agnostic. So we will be implementing it in C, and the IDE that we will be using is code blocks. So now as you can see that we have this method, that is, or function, we have here this function which is bubble sort, which takes an argument as array and size, and then we have these two for loops, nested for loops, and here the swapping will take place if j is greater than j plus 1. Done. This is our bubble sort. Now therein we have another function, that is print array, wherein we will be just printing our elements. That is, we have an iterator, that is I, and it will loop around the length of the array, and one by one we'll be printing them. Okay, this is the print array method. And then we have our driver method, wherein we just have the static array 14, 17, 8, 19, 11, and 2, and then we'll check the size of the array, that is with the help of size of operator, and then we will print our array before we applied sorting, and after that we'll print a message that after sorting what happened, what was the array. Okay, and in between, while we are printing it, in between we have this bubble sort method which will be called, okay, just to sort the elements in the array, and then we'll be printing them. Okay, so now these are the three methods, that is bubble sort, print array, and our main function, that is our driver method. Now let's build and run this program at the same time. Okay, now before sorting the array, our elements were 14, 17, 8, 19, and 2. And after we applied sorting, our elements are 2, 8, 11, 14, 17, and 19, which are in sorted manner. So in this way, we implemented bubble sort with the help of C programming language, and the editor which we used was code blocks. Now let's talk about the time complexity of bubble sort.
Now, if you can observe that we are using two nested loops, right? For, and inside that again we are using a for loop. So it's quite obvious that it will be order of n square, right? Because one of the for loop is traversing from 0 to n, right? That means all the n elements are covered, and for every element that is starting from 1, 2 to so on to n, the first comparison that will happen for this first element will be big of from 0 to n minus 1, then 0 to n minus 2, and so on to 1, right? So if you can observe, right, that we follow a pattern and this boils down to big of n square, right, in the worst case. Now in the average case, it will be big O of n square again, because even if half of the array is sorted, still we are going to compare it with all the other elements, no matter if half of the array is sorted, right? So in average case, it will be again big O of n square. But now the thing is, now you might argue, right? If our array is sorted, in this case, that means 1, 2, 3, 4, 5. Our array is sorted. And now what we are going to do, we are going to compare all the elements with the rest of the elements, right? But in this case, right? If we modify our algorithm or our implementation by using a simple flag variable, I will go back to the implementation, right? Now, what I'm going to do here, I'm going to initialize a flag variable and I'm going to initialize it with 0. Now, if our array is sorted, right, that means 1, 2, 3, 4, 5, all the elements are sorted. That means this condition will never be executed. That means there will be never a case where j is greater than j plus 1. And if I will say, after, what happens if somehow, if our array is not sorted, right? In that case, it will go inside this and I will change this flag to 1, right? But in a sorted case, it will never go to this condition, right? After this for loop is executed once, what I will do, I will just check if my flag is equal to 1. If my flag is equal to 1, that means our array is not sorted and I will continue. Else, what I will do, I will continue, right? Else, I can say break, or you can just write it like this. If flag is equal to 0, then break. That means no need to check for the rest of the elements, and we will be out of this outer loop and we will be boiling down this time complexity to big O of n. Okay, so that is what is written in here. The best case when we modify our bubble sort, it will be big O of n, right? So this is all about time complexity. Now let's talk about bubble sort space complexity. Since we are not using any auxiliary memory, right? Like auxiliary memories can be in the form of what? Stack, can be a queue, it can be another array, can be a string, can be a linked list. So since we are not using any of these auxiliary memories, that means the space complexity of bubble sort is constant, that is big O of 1, right? In the implementation, if you can remember it, right, we didn't use any of these extra spaces, right, in the form of stack, queue, array, string, or linked list. We didn't use it, right? So that is for the same reason the space complexity of bubble sort is big O of 1, that is constant. Now let's talk about bubble sort analysis. Now, if you observe carefully in the array, right, let's talk about this array: 10, 9, 8, 7, and 6. So this is our array, and this is in descending order, and we want to arrange this array in an ascending order. So in worst case, when we talk about worst case, number of comparisons required, right? The number of comparisons that are there are n square. We go of n square. Now, why this is n square? Because every time when our j that is at this location and j plus 1 that is at this location, both of these will be compared. Now, if it is less than this, then they will be swapped. So we have 9 and 10. Then again they will be swapped.
8 and 10. Then again it will be swapped 8, then 7 and 10. Then again they will be swapped 6 and 10. So this is what happens every time in the first iteration. The largest element that is there is at the end of the array. So this is how bubble sort works. So these are the number of comparisons. That means we are comparing them one by one. 9 with 10 with 9, then 10 with 8, then 10 with 7, and then 10 with 6. And this is how it happens. So if you talk about the worst case time complexity in terms of number of comparisons is big O of n square. Now it might be obvious to you guys that the comparisons is n square, and after that we are swapping these. So 10 was swapped with first with 9, and then 10 was swapped with 8, 8 was swapped with 10, 7 was swapped with 10, and finally 6 was swapped with 10. So if you observe, every time that 10 was swapped with all the elements, similarly 9 will be swapped with the rest of the elements, and same thing happens for 8 and 7. So in the worst case, when you talk about number of comparisons that are there and the number of swaps that are there in bubble sort is big O of n square. So I will just erase everything on screen. So in worst case, this is big O of n square. And in number of swaps, in worst case, this is also big O of n square. Now, if you talk about stability of bubble sort, it is a stable algorithm. That means if you notice that the condition wherein we were swapping them is the array of j should be greater than array of j plus 1. Only then we will swap, because we are swapping only if they are greater than, right? J is greater than j plus 1. So when they are equal, nothing will happen. So stability works in this fashion. Let's suppose you have this 10, 8, 9, or you have another 10, then you have 9, then you have 6. So now what stability is, that you can either sort it in this way or in this way. Let me tell you the first way first. The first way can be, so if you talk about this and you're trying to sort them in an ascending order, so it will be 6, then 8, then 9, and then 10 and 10. So let me represent this 10 with 10 and this 10 with 10 dash. So 10 and 10 dash, right? This is already sorted, or it can be 6, 8, 9, 10 dash and 10, right? Still, this array is sorted, right? So in both these cases, right, the array is sorted. But what happens in this case, right? Let me just put it again. What happens in this case, the relative positions of this 10 and this 10 is changed in this case, but it remains same in this case, right? This is case number 1 and this is case number 2. So bubble sort works in this way, that only when they are greater than the next element, that is 10 is greater than, only then they will be swapped. So we can be sure that after sorting this array, the relative position of this 10 and this 10 will be saved and they will be preserved, right? So this bubble sort is a stable algorithm. But now what about this in place and out place? So since we are not using any extra memory, right? We didn't use any extra memory in the form of array, stack, linked list, or queue, right? Or even string, right? We didn't use any of these extra memories, and we swapped this array within the array that was given to us. So that is the reason why this bubble sort is an in place algorithm. Okay, that's it. Okay. So let's reiterate. So big O of n square, number of comparisons, number of swaps, big O of n square. It is a stable algorithm, and finally it is an in-place algorithm.
Selection sort algorithm. Now let's talk about what is selection sort. Now before we move to this sorting algorithm, let's try to understand what is sorting. So if you have a bunch of students, and out of those bunch of students, let's suppose some of them have either left the college or school, or they are absent. Right now you want to arrange the remaining students either in ascending order or in descending order. So for that reason, you might require sorting. So this is one of such sorting algorithm wherein which helps us to sort elements or number of students. It can be any object, right? So it is a simple sort algorithm that revolves around the comparison. So now this is different from if you talk about bubble sort, insertion sort, and selection sort. This sorting algorithm is predominantly based on comparison, right? The comparisons are done more as compared to swapping. In each iteration, one element gets placed, right? If you think about bubble, how it worked like a bubble, and at the end you had your element fixed at its original position, which was at the end when we are trying to sort our array in the ascending order. Now, in the same fashion, right? In this sorting algorithm, one element that can be either the largest element or the smallest element. So we are going to put in the case wherein we will be dealing with the smallest element. In each iteration, the smallest element get its placed fixed in the original array. That means when we sort the array wherein this element belongs, that is the least element that is on the first index, right? So this element will have its position after one iteration. We will be choosing a minimum index in this sorting algorithm. We have one minimum index, and that can be named as minimum, right? Since we are dealing with the smallest element. So now that minimum element in the array is placed at the beginning, right? Beginning of the array. And later on, we will compare it with all the elements and find out the minimum and then swap it with the first index. Okay. Similarly, we are going to do for all the rest of the elements. Okay. Now, the selection sort is basically selecting an element, that is the minimum element, in each iteration and placing it at the appropriate position. So that is the basic logic behind what selection sort. Now let's talk about selection sort algorithm. Now in this algorithm, our main objective is to find the minimum index, right? So let's suppose if we have one array. Now, in this array, there is one minimum index. Let's suppose that it is at the first index, right? Since we are keeping in mind, right? I told you at when we talked about what is selection sort, at that time I told you that we can have two cases. Either you can pick up the largest element and fix its position at the end, or you can pick the minimum element, that is the smallest element. Okay, so in this case we will be dealing it with the smallest element, right? Now this is our minimum index, right? This is the 0th index. Now this outer loop will work from 0 to n minus 1. Now why n minus 1? Okay, I will tell you why. Because then what we will do, the next step is that we will have this minimum index, right? And it is pointing to 0 in this case. And our iterator, that is I, will start from this position. Then in the nested for loop, that is, again, this is condition where we have one for loop and inside that we have another for loop. That is what you mean by nested for loop. Now, since it is a comparison algorithm, what we are going to do inside this sorted part, or inside this unsorted part that is there, what you can say, the rest of the elements. Okay, so we have this j iterator which is pointing to I plus 1. That means we will not compare. It doesn't make sense, right? If I and j are at the same position and we are comparing them, it doesn't make sense, right? So we have this j placed at this iterator at this index, right? 1. This j iterator is at index 1. Now what we will be doing, we'll be comparing it because it's a comparison algorithm and number of swaps are less. That means if there are n elements, there will be n or n minus 1 swaps. Okay, so the swapping is reduced as compared to bubble sort. Okay, so now what happens, we will be comparing them. Okay, and we will be trying to find the minimum index. Let's suppose this is 3 and this is 1. So since 3 is greater than 1, that means our minimum index will be updated. So our new minimum index is what? At index is the 1, right? This is the minimum index. Okay, done. Now once this comparison is done, right? So again we will check if 4 is less than 1, no. If 5 is less than 1, no. If 6 is less than 1, no. If 0 is less than 1, yes, 0 is less than 1. That means we are again comparing it, right? And we are not swapping them. We will wait once this entire iteration is done. So I will update my minimum index to what? 5, because that is the minimum index. Then we have, let's suppose we have 8. Okay, done. So now once this entire for loop is exhausted, right? Now what we will do, we will swap this minimum indexed element with the with the minimum index that was earlier there, that is the 0th index. Okay, now we'll swap it with the 0th index. Okay, so now what happened, this we will get here 0 and we will get here 3, so only one swapping is done. So now after first iteration, all the elements will be at its own position, because since we didn't swap any elements, we swapped only a single element, that is these two indexes, that is 5th and 0. Okay, so now what we will have, 0, 1, 4, 5, 6 and 3, and at the end we have 8. Okay, done. And then we will iterate through again. So now our iterator will be here and our j will be here, and this time around minimum index will be, right, earlier it was 0. Now since we will not take care of this, or we will not think about this index now, because this is already at its original position, the element is at its appropriate position. That means when we sort the array, 0 will be at 0th index, so we will not think about it, and it doesn't matter to us now because it is at its original position. So minimum index will be now 1. Okay, so now let's try to see an example wherein we get the better understanding of this algorithm. So if you observe carefully, this is our input array, right? So we have 23, 10, 16, 11 and 20. Now what happens, we'll make this our first step, and this is our iteration number 1. Okay, so now what happens in this, we have our minimum index that is at C. This is our I and this is our J. Now we'll compare, right? Is 10 greater than 23? No, it is not. So still we have minimum index as 0. Is 10 greater than 60? No. Is 10 greater than 11? No. Okay, now this is the first step. Okay, just a minute guys. So let me erase this. So our I will be here and J will be here, and minimum index is at 0. Okay, because that is the first index. Okay, so since we are taking into consideration the smallest element, so now we'll compare. Is 23 greater than 10? Yes. What we will do, we'll update our minimum. That means this is now index 1. Now what we will do, we'll have our index updated as 1, and then what we will do, we'll compare 10 with 16, 10 with 11 and 10 with 20. Since this is our minimum index after first iteration, now what we will do, we'll swap it with the first index, that is this, and this element will be swapped. So that is why we have 10 here and 23. Rest of the elements are same. Done. So this is our first step, and our I was at 0. Now our I is at 1, so this is our minimum index, right? This is our minimum index in this case. Now 11, in this case, what is our minimum index? That is 21, right? So min is here, and 23. Now 23 will be compared. It is greater than 16, so this will be our min. Again 11 will be compared, so this is our min. Now 11 will be compared with 20, so this is not our minimum element. Now this is our minimum element, and it will be swapped with 23. So 23 and 11 will be swapped. So that is what you see here. So 10, 11 and 23 is swapped with this. So 23 here and 11 here, right? So 23 will be here and rest of the elements will be as it is. So this is after iteration number 2. Now what happens in iteration number 3? So we have 0, 11 at its original position, right? Now let's swap back and let's erase this. So now what happens? So this is our minimum index, right? And now 16 will be compared with 23, nothing will happen. 23 will become 16 will be compared with 20, nothing will happen. So this is our minimum index, and this is the ith index wherein we will be swapping it. So 16 will be swapped with itself, and rest of the elements will be as it is. So you will see 16 and then 23 as it is and 20 as it is, considering this iteration number 1. Okay, so after iteration number 3, this is our input array. So similarly, after third iteration, this thing will happen as 23 is greater than 20, so these elements will be swapped. And in the fourth iteration, is required as last element is already sorted. Okay, so no fourth iteration is required as the last element that is there which is already sorted. Okay, so this is the whole demonstration of this selection sort algorithm. Now let's talk about the implementation of selection sort. If you can see that we have this method over here that is named as selection sort, which takes an argument as an array, and the second argument is size of that array. So now let's take in one example here: 10, 6, 5, 4, and 1 and 2. So this is our array and these are our indexes. The size of this array is nothing but 6. So 6, and the name of this array is ARR. So this is our ARR. Okay, so now our outer loop works from, or it iterates from 0 to size minus 1. Okay, why size minus 1? Because if you see that this inner loop is working, that is, this is our j pointer and this is our I pointer, and it works from j plus 1. So it means if j is at this position, it will consider, the inner loop will consider iterating from this element, that is j plus 1. So that is why we are reducing this by 1. Okay, so that we don't get a condition wherein we are trying to access the elements that are not there. Okay, so then we have one index that is named as minimum index, and it is pointing to j, that means the first index, that is 0. Okay, now our inner loop only is used for comparisons. Okay, as it is already taught to you guys that it is selection sort is nothing but the comparison algorithm. So we will be comparing what the ith indexed element, that is this element, will be compared with the minimum indexed element, that is the 0th element. Okay, so these two will be compared and we find out that okay, 10 is greater or 6 is less than 10. That means we will update our min to what? 1. Earlier it was 0, now it's 1. Okay, let me change the color. Done. So now what happens? Then we will compare 6 with 5. Again, we'll update it to 2. Then 5 with 4, we'll update it to 3. Then 4 with 1, we'll update it to 1. And 1 with 2, we'll keep it as it is, right? The 4, not the 1, right? So the fourth index is the minimum index, or it is the index of the minimum element in the entire array, which is rightly so. That is, 1 is the minimum element in this entire array. Now, once this entire iteration for this for loop is exhausted, right? It is done. Then what we will do, we'll swap it with this element, with this first element that is present at the ith location, or jth in this case. So j is pointing to this. Now we'll swap them. So that means after first iteration is done, 10 and 1 will be swapped. So it will be 1, and rest of the elements, as we have seen in the demonstration part as well, will be as it is. So this is our array. I hope you can see it. Let me just write it here. After first iteration, what happens? 1, 6, 5, 4, 10, and 2, and these are the indexes. Okay, so these are the elements, and only these two elements will be swapped. So we are reducing the number of swaps, and same thing goes on for the rest of the elements as well. Okay, so now let's see the demonstration, or let's see its implementation using code blocks. And we will be implementing this algorithm using C. So now if you can see, I'm using code blocks here. So we have this selection sort algorithm in here, or you can say the implementation of selection sort in this method, right? We start from j pointer and size minus 1. Then this is the minimum index, which stores the minimum index min, and then the inner loop, which is used to find the minimum index, and then we are swapping it. Okay, so let's minimize this. Then we have this method that is print array, which is only used to print the elements, okay, of the array. Then is our main driver function, that is, we have this static array over here, and then we use the size of operator to calculate the length of the array. Then we'll print the array before sorting, and then we will print the array after sorting. In between, we will be calling this selection sort algorithm as well, or selection sort method as well. Okay, done. And then we'll be printing the array. So now these are the three methods. Now let's run this code. We'll go into build and run, and now we'll see the output. Now, if you can see before this, before sorting the array, it was 14, 17, 8, 90, and 11 and 2. After sorting, it was 2, 8, 11, 14, 17, and 90, which is obviously sorted. Okay. So in this way, we have seen the implementation of selection sort using C in the IDE, that is code blocks. Okay. Now let's see the time complexity of selection sort. Now, if you talk about worst case, that is if the array is unsorted, or it is we are trying to sort an array which is reversed in nature. Okay, so let's suppose we are trying to sort the array in ascending order and we get the array in ascending order or descending order. Okay, so that is 10, 9, 8, 7, and 6. So this is the worst case, right? And now what happens in this case? Every index, the minimum index will be updated for every element. Okay, so 10 will be compared with the 9, so minimum index will change from 0 to 1, then 0 2 3 and so on. Okay, to find the minimum index, that is this element. So this is the worst case. Now what happens? We have the outer loop that is working from 0 to n minus 1, and the inner loop that is working from 0 from j plus 1 to the size. So in any case, whether we have this unsorted array that is here, we will still be traversing big O of n square times, because we have these two for nested for loops which are working up to the size of the array. Done. And same thing happens in the average case as well, whether we have some elements in the sorted format. Let's suppose we have half of the array in this way, and then the rest of the elements are unsorted. Still, we will not update our minimum index, but rest of the elements will change for the not for these three, but for the rest our minimum index will keep on updating. Okay, so it doesn't matter. So average case type, if you talk about average time complexity, it will also be n square. But what happens if our array is still sorted, right? Or if our array, that is the array given, is already in sorted format, will there be, if we modify our bubble sort, we can get this down to big O of n. But this is not the case in selection sort. Still, we will be comparing in the outer loop from 0 to n minus 1 or size minus 1, and in the loop will be again going from j plus 1 to less than size, without, even if we are not going in this for, in this if condition, that is the comparison condition will not be executed and the minimum index will be as it is, still we are going through this for loop. Okay, whether we are not, even if we are not executing this if block, okay, it doesn't matter, still we are going, the n square time complexity will be there even in the best case as well. Okay, so this is all about the time complexity of selection sort. Now let's talk about the space complexity of selection sort. Since we are not using any auxiliary memory, so auxiliary memory can be in the form of arrays, linked list, stack, queues, or even strings. Since we are not using any of these extra memories in order to sort our array, so the reason for that is because we are doing this within the array that is provided to us, right? So the space complexity is constant. That means big O of 1, as we are not using any auxiliary memory. Now let's talk about selection sort analysis. If you observe carefully in this array, let's take an example first: 10, 9, 8, 7, 6. Okay, let me put a 6 here. So this is our array, right? And in this array, what we are trying to do, we are trying to arrange it in an ascending order. So now, if we remember the algorithm, the outer loop work from 0 to n minus 1, and then inner loop work from, that means 0 plus 1. That is, let's suppose if this is an I iterator, if we use in outer loop, we used I, and then in inner loop, we use j, then j work from I plus 1 to size, that is n, right? Now, and then inside this we used to compare. So now in worst case, every element was compared, right? J was compared with I plus 1, right? Or I was compared with J plus 1. So it was compared with this, and this. And we were selecting the minimum element in the array.
the minimum index rather. We were selecting the minimum index in the entire array. So this was working for n times, and this worked from big O of n times, right? And in worst case, the number of comparisons required will be big O of n square, because we are trying to find the minimum index in the entire array, right? And once we have that minimum index, and later on we'll swap them, right? In worst case, it will go from 0 to n, that means big O of n, and the inner loop will also go from big O of n, that means 0 to n. So in worst case, since these are nested for loops, so the worst case will be big O of n square. And for comparing them, well, I'll always compare all the elements, and it will be again, it will boil down to what? Big O of n square when we talk about number of comparisons. And what happens when we are trying to swap them? Since we have this minimum index that is there, only one swap was required, that was outside this inner for loop, right? So we have this inner for loop, and here we were doing the swapping. In worst case, the number of swaps that are required is big O of n. Okay, in worst case, that means we were swapping only single time, and it will be the case, right, that in worst case that all the elements right at the end will be swapped. So we will have at the end what? 5, 6, 7, 8, and 9, right? And we will swap them only once in the entire array, that is once for every element. So in worst case, it will be big of n square. Now, what about stability? If you talk about stable algorithm, it means that if you have this array, let's take an example, it is 10, 8, 9, and 10 again, and then 6. If you talk about this, the stability will boil down to two things: the relative position of these two elements, 10 and 10 dash. Now, if we sort this, it can be 6, it will be rather, it will be 6, 8, 9, 10, and 10 dash, right? So it will be 10 and 10, but just to separate these two tens, we are taking as an example, we are taking this, assuming this 10 to be 10 and this 10 to be 10 dash. And it can also be that it will be 8, 9, and then 10 and 10 dash and 10. So both of these are sorted, right? But if you talk about stability, this is a stable algorithm. Why? Because the relative position of this 10 and this 10 is intact, and this is an unstable algorithm. Now, when we compare or when we do the swapping in selection sort, it is not guaranteed that it will be stable, right? And the elements can be unstable. That means the resultant array will be in this format, that 10 dash may be at first and then we have 10. So it is not guaranteed that it will be always stable, but yes, we can make it stable by modifying our selection sort. But if you talk about traditional selection sort, it is an unstable algorithm, right? Now, what about the in place? That means, are we using any extra memory or extra space? No, we are not using any extra space, right? Extra space can be a linked list, it can be an array, it can be a stack, it can be a queue, right? We are not using any of these extra spaces. So that is for the same reason this selection sort algorithm is an in place algorithm, right? Because we are swapping our elements and we are comparing them within the given array, right? We are not using any extra memory, right? So for that reason, this is an in place algorithm. Let's try to reiterate what we learned so far. So if we talk about number of comparisons, in the worst case, it can go to big O of n square. In terms of number of swaps, it is big O of n. It is an unstable algorithm, and it is an in place algorithm.
What is insertion sort? So the question is that what is sorting? So you might be thinking, why do we need these sorting algorithms? So if I told you that you have a bunch of students, right? You have a bunch of students and they each have their roll number. They are not present in a numerical order, or you can say they are not present in some order. I want that order to be maintained. Let's suppose you have 1 to 10 students in those bunch of students, and each are having roll numbers from this range, from 1 to 10. Now, some of them are absent and some of the roll numbers have left the school, but the roll numbers are not changed yet. Now, what I told you, please sort them or arrange them in such a manner so that I can easily understand which roll number is after which, either in ascending or in descending order. Let's suppose 1 is there, 2 is there, then 6 is there, then 8 is there, then 10 is there. So rest of the roll numbers I can easily depict, okay, these are the ones which either are not there or are absent. So in order to do so, we have these sorting algorithms in picture. And one of those sorting algorithms is insertion sort. Now, it is the simplest, easiest, and a brute force sorting algorithm. Now, what do you mean by brute force? Brute force means straightforward, right? In a naive way, it means straightforward. That means you're not considering any efficiency, or you don't care about time complexity or space complexity. You just straight away sort it with the most simpler and naive approach. Okay, in this brute force algorithm, what happens that, let me give you an example, right? Obviously we can sort with the help of this insertion sort algorithm. You can obviously sort either in ascending or in descending order, right? Let's take one example. We all know about the card game, right? Wherein you have a bunch of cards, right? Suppose you have a single card that is in your hand, right? And you have a bunch of cards available on the table. Now you start picking those cards one by one. Obviously, the one that is in your hand is sorted, because if I told you to sort a number one, obviously there is only one element in the array or anything, right? In the linked list, I told you to sort it. But if you're having only one element, that is itself sorted, right? You don't need to sort that. Similarly, what happens now, this card is in your hand, right? It's just like playing cards, right? Now you have this one card in your hand and it is obviously sorted. Now what you will do in the next turn, you start picking up one by one from these set of cards that are available on the table. Now let's suppose this is 0. Okay, I'm considering these numerical values so that you can understand and you can just connect the dots, right? So what happens, you have the 0 and now you start comparing it. Now we are considering the scenario where you are trying to sort in ascending order. Okay, so now let's try to erase these things so that it's easier for you to understand things. Okay, so now you have these two elements, right? And now we are considering the case wherein you are trying to sort in ascending. So you check, okay, if 0 is less than 1, yes it is. Now you swap them. Okay, now you have 0 and 1. Now these are the two cards that are present and both of these are sorted. So now insertion sort works in such a manner that you will always have two parts, right? One is the sorted part, obviously, which is in your hand, and one is the unsorted part, which is on this deck, right? So similarly, you will start picking elements, or you can start picking these cards one by one and keep sorting them. Okay. Now this is one simple scenario wherein you can apply what insertion sort, right? This is the most simpler way one can explain or one can understand this insertion sort algorithm. Now it is simple, right? Now you start picking these elements and you keep sorting them, and at the end, when all of these elements are exhausted, you will get your sorted array. Now let's try to understand insertion sort algorithm. So in this algorithm, what happens? Obviously, now we know that we will have two parts, right? One is the sorted part and another is the unsorted part, right? So obviously, the one element that is present in your hand, or the element or the card that is in your hand, and there's only one element there, right? The one element in your hand, obviously that is sorted, right? So we will not consider that first element, and we will start our iteration from the second element, right? Now we understand why we are doing this, that we are starting from 2 to n minus 1 or 2 to n, depending upon the array that we are starting from. Either we can start from 0 index or we can start from 1 index, right? So we always start from element number 2, right? And then what we will do, we'll just store this value inside some temporary variable, and then we will check if that element is less than the element that we have in this sorted part. If that is the case, then we will shift their positions, right? And we will get both. Now we will have two elements in the picture, that is 0 and 1, and both of these will be sorted in ascending order. And then what we will do, we'll consider the rest of the cases, that is starting from 3 to so on to n. Okay, now you might be thinking, okay, how does this thing happen? Let me take an example and let me show you how. Let's consider this array that we have over here, that is index 0. These are all the indexes that we have, and this is our array, that is 23, 10, 16, 11, and 20. So in the first step, we are making partitions. Now this is our sorted part, that is the first element, and this is our unsorted part. Now what we will do in the first iteration, this is our iteration number 1, because this is the case wherein we will start moving from second index, that is first index, if we consider from 0, right? So we consider from second element and so on to n, right? So now in the first iteration, what we will do, we'll compare these two values. Okay, let me just erase everything so that it's easier for you guys. So now we will compare these two. Now obviously 10 is less than 23. What we will do, we'll shift their positions. Now this is your sorted part and this is your unsorted part. Again we will do the same thing, right? So in second iteration, what we will do, here comes 16. Now what we will do, we'll compare it first with 23. Okay, we know now, okay, 16 is less than 23. So now what we will do, we'll swap their positions. So this is 16 and this is 23. Now what will happen? Now 16 will be compared with 10. Obviously it is not less than 10, so it will remain as its own position, that is its new position at index 1, right? So this is the second iteration, and after second iteration, this will be your sorted part. As you can see that I have bolded this text, right? Bolded the borders of these two elements and bolded the same for these three elements, because this is the sorted part that we have over here and this is the unsorted part. Now what will happen in the third iteration, that it will check for this number that was there, it is 11. So for 11, what we will do, we'll compare it with what, read this thing. Now we'll take 11 into consideration and now we'll check it, we'll swap them. Then 11 is here, 23 is here, we'll check them, we'll swap them. 16 is here, 11 is here, we check them. So since 10 is less than 11, so nothing will happen. So in the third iteration, what will happen? We will have 10, 11, 16 and 23. These are all sorted and we are only left with one element which is unsorted, right? Now in the final iteration, what will happen, that 23, now this 20 will be at its original position, that is there, and rest of the elements will be sorted. Now since we have exhausted all the elements have been exhausted, and we at the final step, that is in iteration 4, we will have this array that is sorted. Now let's try to understand insertion sort implementation. So consider this function which is written in C. Now let's see what happens in this function. So in this function, that is insertion sort, we have two arguments, that is the elements in the array, that is our array, and the size of the array. Now let's clear this thing and let's see. Let's take an example, a simple example, that is 10, 5, 6, and 20. In this we have these indexes. Now this is the name of the array, that is ARR, we have passed in this function. Now what is this n? This is nothing but size of this array, which is nothing but 4. Now we have already seen the algorithm wherein we always talked about two portions, that is the sorted part and the unsorted part. Now we know that the first element is sorted in itself and this is our unsorted part. So that is for the same reason we are starting our iteration from 1, that is this index. Now let's try to erase this thing and let's see what are the pointers, or what are the iterators and variables that we have used. So let me clear out this thing, and we all know now this sorted part and unsorted part. Now let's see what are our iterators. So we have our j pointing to this index, that is ji minus 1, and we have our I which is pointing to this element. We also have a temporary variable which I will tell you, that is tmp. Just a minute. Okay, so we have 10, 5, 6, and 20. This is our j, this is our I, these are our indexes, and this is our tmp temporary variable, which is right now 5. Now, let's talk about the first iteration. What happens in that first iteration? We are over here. We talked about these pointers, right? Now we are checking if j is greater than 0. Yes, it is. It is greater than 0 or equal to 0. This time around, it is equal to 0. Now, why we are checking this, you will understand in a bit. Now, we are also taking into consideration that temp should always be, or it should be less than ARR of j. Now, if 5 is less than 10, that means this will be our new sorted array. And in that sorted array or sorted part, this is the unsorted part, obviously. Now, in that sorted part, 5 should be first because we are considering the ascending array and we are trying to sort our elements in this array in ascending order. So this should be the scenario. Now, this condition holds and this condition also holds. Now, what we are doing, we are changing the j plus 1 index. That means we are talking about this index and we are writing 10 over here with this step. Now, you might be thinking, okay, now we have an array in which both of these elements are 10. But we have already stored this in a temporary variable. That is for the same reason we were using this temp variable tmp just to store that element. Okay, now that is done. But now we are considering in the backward direction. We are trying to sort whatever is in that portion, in that sorted portion, because this will always be the sorted part and this will be the unsorted part. So now we have checked this element and we have swapped them. Not swapped them, we have shifted them, right? We haven't yet changed this temp back, right? We have a new array that is 10 and 10 in this portion, right? And now what we are doing, we are decrementing the j. Now j will be pointing to -1. But now that there is no such element in here, so this condition will not hold and this should be given as false, right? And now we will be out of this while loop. Now in the final step, what we are doing, we are now changing this j plus 1, that is this element that is there, that j plus 1 element, which earlier was minus, which now once decrementing it, it is -1. Now what we are doing, we are incrementing it again. That means we are talking about j plus 1, that is -1 plus 1, and this is the index. That means we are talking about ARR of 0. And now what we are doing, we are storing that TMP, which is nothing but 5. So this element, let me just erase it. So this element will be now 5. So now you see how our dots got connected, and this is the array. Now this is only this thing happened only in first iteration. Now what about the second iteration? Let me just erase it and let's talk about the second iteration as well. So we have now 5 and 10, and then we have 6 and also we have 20. So these are all the indexes that we have, and this time around our I is incremented because this is the second iteration. So I will be pointing over here and j will be 1 less than I, that is j will be here. And in our temp, we are storing this 6, right? So these are the things that happen in these two steps. Now this thing is also done. Now we are again checking if j is greater than 0. Yes, it is. Right now j is 1. So this condition holds. And we are also checking if temp is less than ARR of j. Yes, temp is 6 and it is less than ARR of j. Now what we will be doing, we will be changing the positions or shifting this 10 to this, right? Now here we have 10, right? And this is also 10. Now this is also 10, right? Now after that, what we'll be doing, we'll be decrementing j. Just using the eraser away. Now what we will do, we will just decrement our j, and now this time around j will be on 5. Now that is done. Now again, we are not out of this while loop yet. Now again, we will check, is j greater than or equal to 0? Yes, this condition holds true because right now j is equal to 0. And is temp less than ARR of j? Is 6 less than 5? No, it is not. It will not hold, so it is false. So we are out of this while loop. Now this time around, j is still at 0, right? In the second iteration, j is at 0. Now what we will be doing, we'll be using this last step that is over there. We are just doing j plus 1, that is 0 plus 1. At this index, please store temp. That means ARR of 1. That means we are talking about this position, which was earlier we overwrite it, or we had 10 over there, right? And now we want there to have this 6. So we will overwrite this 10 with 6. So in nutshell, what we will have over this position in this position we'll be having 6 because of this step. So this step is very important, right? This is the most important step, and this is the one that is responsible for making all those shifts. Okay. So now this happens in the second iteration, and now we have our sorted part, that is 5, 6, and 10, and finally we have at this 20. And the last iteration, nothing will happen because we will be out of this loop because AR of j, that means this is our I and this is j. This is not less than 20, is not less than, so nothing will happen at this time around. This temp will be changed with this 20, so 20 will be changed with 20, so nothing will happen. And at the last step, in the last iteration, we'll have a sorted array, that is 5, 6, 10, and 20. Done. Now let's see its implementation. So now if you can see that the ID that I am using is code blocks. Okay. So you see this is our display function, which is just displaying the array. That means we are iterating from 0 to n, and we are just printing out the elements in the array. This is our display function. This hash includes studio.h. This is just for implementing the printf and scanf statements, if there are any. Okay. So then we have this insertion sort function, which is similar to what we just saw. So we are starting from I equal to 1 and then to n. And then we have this temporary variable, which is storing the element. And then we have this while loop, which helps us to make those shifts. And finally, the most important step that is over here, which is the exact location of that element, which is being shifted, okay, which has to be shifted. And now that we have this main function over here, that is our driver function. In this, we are using the static array, that is 95143. And then we are first calculating the size with the help of size of operator. And we are calculating the number of elements in this array. That's it, right? And then we are printing the elements before sorting and calling the display function over here. Then we are calling insertion sort function. Then we are again printing the elements after sorting and with the help of display function. Okay, so now let's save this file, and now let's try to build it and run it at the same time. Now if you see, the elements before sorting were 95143, and after sorting it is 13459, which is obviously sorted. So in this way we implemented insertion sort using C. Now let's talk about insertion sort time complexity. So in the worst case, when all the elements are in haphazard manner and we need to sort them one by one. So obviously we are talking about first the outer loop, which runs from 1 to n, and then the inner loop, which runs backwards. And in the in the first iteration, we only consider the 0th element. Then as we move along, it will be running from n to 0th element, right? We will be considering the whole n elements. So in that case, the time complexity in the worst case will be order of n squares, because we have two nested loops. That is, one is for loop, and inside that for loop we have that while loop, right? So this is in the worst case, and it happens also in the average case, where some part or the sorted part is already there, and it is, let's suppose we have 5, 4, 5, 6, 7, 8, and then we have the unsorted part. So half of the elements are sorted and half of the elements are not sorted. So it will be n squared by 2. So we are not considering the case where we talk about constants and we are negotiating the constants. And in that case, the average time complexity will be n squared, right? But the most important thing that is there in this time complexity is the best case. That means when your elements, that is 5, 6, 7, 8, 9, and 10, when the elements in the array are already sorted, what happens in this case? If you observe, the for loop that runs from 1 to n will be always there. So n is always there. The time complexity, the big O notation, big O of n will be always there. But in this while loop, wherein we were checking for if j is greater than or equal to 0 and if AR of j is less than 10, right? In that case, this will never be executed, because this AR of j will always be greater than 10. Why? Because we are talking about this element and we are checking if this 6 is less than 5. No, it is not. If this 7 is less than 6, no, it is not. So this condition will always be false for all the elements. So in nutshell, we are just checking these steps only once in every iteration. So that is for the reason that the whole time complexity in the best case will be big O of n and not big O of n square in the best case. Okay. Now let's talk about insertion sort space complexity. If you have observed in algorithms and in implementation, we never talked about any auxiliary memory, right? We were not using any extra space, either in the form of array, linked list, stack, queue, or anything, right? So that is for the reason the space complexity of insertion sort is big O of 1. That is constant amount of space. Now let's talk about insertion sort analysis, wherein we will be analyzing comparisons, number of swaps, stable or unstable, in place or out place. So first let's talk about number of comparisons required. In this we will talk about two scenarios, wherein we will talk about worst case and average case. In worst case, the number of comparisons required is n square by 2. Now, if you talk about average case scenario, it is n square by 4, which is twice as much as this, right? It is 2 times. If you talk about number of swaps that are required in insertion sort, in again we will talk about two scenarios, average and worst case. In average case, it is n square by 8, and in worst case it is n square by 4. These are the number of swaps required. And if you want to check those, if these statements hold or not, if these equations hold or not, you can always take an example wherein you will be considering both the cases, even as well as odd. So take an example and run through it. Now, if you talk about stability of insertion sort, it is a stable algorithm. What do you mean by stable? So if you have an array which contains 1, 3, 1 dash, and 5, in this array, the relative position of these two ones, that is this one and this one, let me change the color and let me show you. The relative positions of this one and this one will remain intact. What do you mean by this thing? That whenever you are sorting it, you can sort it in two different ways, right? This is also sorted and this is also sorted. That means you can either have 1, 1 dash, 3 and 5, or you can have 1 dash, 1 and 3 and 5. This is obviously that this number is repeated, but this is the first number. This occurred here the first time, and here it is the second occurrence. Now you want to keep their relative positions intact, right? So both of these are sorted, right? But if you talk about stability, this is known as stable and this is unstable. Okay. Now, insertion sort, whenever you are trying to implement insertion sort, it is stable. That means the relative positions of both these ones will be intact. Okay. So if someone asks you if insertion sort is stable or not, you will say yes. Why? Because the relative positions of the numbers that are repeated remains intact. Now, what about this in place or out place? Since we are not using any auxiliary memory, right? We didn't use any stack, queue, linked list, or array. That is the reason that whenever you are not using any extra memory, it is supposed to be in place algorithm. So if an algorithm is sorted within the array that was there earlier, that means you're not using any extra space, that algorithm is known as in place algorithm, which is evident now in insertion sort as we are not using any extra memory. So insertion sort is an in place algorithm. Now let's look at the example wherein we will implement insertion sort. If you can see, we have this example over here wherein we have 6, 5, 3, 2, 8, 10, 9, and 11. And we have been given this key. What this key signifies that the maximum swaps or comparisons needed for this tree, either on the left side or on the right side, right? The number of positions that this tree needs to get to its original position is 3. So this is a question that is known as nearly sorted array or k sorted array. We do not need to sort all the elements in the array, but we are specifically looking for those elements which are not at its original position. And if we want to get them to their original position, the maximum comparisons or swaps that we require is 3. So if you see this 3, the original position of this 3 is this 5. That means in the sorted array, it will be here. Similarly, if you talk about this 2, the number of swaps that it should do is 1, 2, and then it will be at its original position. Or you can say that 1, 2, and 3. So max it can go to 3 positions. Okay. So similarly, it will be the same for all the elements. So at most 3. Okay. And at least it can be that it doesn't need to move at any location, that it will have its own original position. Just like in 11, you see 11 is at its own position in the original array as well as in the swapped array. So at most you have 3 positions. So now if you talk about its implementation, we are going to implement it with the help of insertion sort. Why? Because we know if we are not swapping it, then the time complexity will be reduced from big O of n square. Now there are some elements, and the maximum swaps that we are going to do is big O of n into k, okay, to the base 2. So maximum we are going to move, or the internal loop, that is this loop, will work maximum k times. That means what is the value of this k? So that many times this internal while loop will work. Okay. So if we can observe carefully, this is the same implementation of insertion sort that we have seen earlier, right? So we have this array, we have this size, then we have these 3 iterators I, k, and j, wherein this is the outer loop, this is the inner loop, and instead of temp we are using this time around, we are using this variable k. That's it. Okay. So at the end, this is the most important step, which is wherein you are storing that element at its original position. That means, let's suppose you have this 10, 6, and 5. Then this time around, this 5 at the last step, this 5 will be here in this step at its original position. Okay. So we have 5, 6, and 10. Because in the meantime, what will happen? The 6 will be replaced with this 6. Then this 6 will be replaced with this 10. Then we have this 10 over here, 10 and 6. So in the meantime, we will be having this array, 10, 10, and 6. So at last we will be having this 10, 10, 6. But we are missing one important fact, that obviously these two elements should be sorted in when we have moved to this step, this third step. Obviously these two should have been sorted. So this will be 6 and 10. Then we have 5. So this will go 10 and 10. This will go here 6 and 6 in the second iteration in this while loop. And finally this step will be there, and it will replace this 6 by 5, and this will be your sorted array after in the second iteration. That's it. Okay. So this is the same algorithm or implementation that we have earlier seen in the insertion sort, right? And now let's see its main function, or the driver function. That is, here we have this array in which we have all the elements that is nearly sorted or k sorted. And then we calculated the size of the array, and then we have this k. You might be thinking, okay, why we are not using this k if this is given to us? Since this is not the efficient approach, right? This is not the most efficient approach to use the insertion sort. But yes, there is a 50-50% chance that you might get selected if you apply your brains and you use insertion sort, because it is obviously better than n square. That is the most naive approach. You are using something that is better than n square. You're using n into k. Okay. Why this n is there? Because you will be iterating through all the elements one by one, and you will be swapping them in the internal loop only k times. So you have this k over here, which is 3, and we will be displaying our elements before they were sorted. And after we apply this insertion sort function, we call this function over here, and then they will be sorted, and we will check with the help of display function. We will implement this display function as well, right? And we will see if our elements are sorted or not. So now if you can see that the IDE that I am using is code blocks, and if you see, we have implemented 3 functions. Now let's see first our main function, that is our driver function. In this, we have this array that is there. Then we calculate the size, we have this key, we have this elements before sorted. Then we are calling display function. Then we are calling insertion function, insertion sort function. Then we are printing these elements before sorting and after they are sorted. Okay. So this is our main function. And if you talk about insertion function, it is similar to what we have seen earlier. So in this case, we are using this temp variable, not k, and we have this temp as arr of I, and then we are calling these functions. And then what we have inside this for loop, we have this while loop, and then there is this step, the most important step, wherein we are swapping them at the end. This is our insertion sort function. And then finally, we have our display function over here, wherein we are just iterating through all the elements one by one. So we have these three functions over here. This hash include stdio.h is nothing, but since we are using this printf statements or scanf statements, if we had used any, so in order, if you want this array to be dynamic, right? So the user should enter those elements, then you can use scanf. So you don't have to implement those functions. Those will be included with the help of this library. Now let's save this file. And now let's run this file. Let's build and run, and let's see the output. If you see, the elements before sorting were 6, 5, that is not sorted. And after sorting, we have 2, 3, 5, 6, 8, 9, 10, 11. So this is your implementation. So this is your implementation of this example, which is sorting nearly sorted or case sorted array with the help of insertion sort.
Now let's talk about selection versus bubble versus insertion sort algorithm. Now if you can observe in selection sort what we were doing, we were having this minimum index, and that minimum index after an entire iteration we were finding the minimum index, and then we were doing a single swap. That's it, right? We can also go for the largest. In bubble sort, every adjacent element was compared, and we were swapping and comparing them in the same order, right? Let's suppose this is an array wherein you had 10, 8, 1, 2, 3. Every element was compared, right? J was compared with j plus 1, 8 was compared with 8 plus 1, and then if 10 is greater than 8, then we used to swap them, and then if 10 is greater than 1, we used to swap them, 10 is greater than 2, we will swap them, and at the end we will swap them. So at the end, the largest element that was there in the array was at the end, look at the end of the array, right? So that is what happened in bubble sort. The number of comparison, the number of swaps were done very rigorously. In terms of insertion sort, we used to have one sorted part and one unsorted part, and every time, let's suppose if there is only one element, and we were always starting our search, or we were always iterating from the next element, right? The second element, on the first element itself is a sorted element, so we used to have this sorted part and the unsorted part. We take and put the element one by one, and let's suppose there are elements on the deck, those was considered to be unsorted. We used to pick one element and compare it and put it at its right position every time with each iteration. So this is a definition, you can say. This entire thing, this first row is about definition, what they do. What about the other parameters? In best case, when you talk about the best case time complexity, selection sort will still be big O of n square, but in bubble sort, the best case is big O of n. If we modify it a little bit, right? Modified bubble sort, it can be big O of n. And insertion sort, it will be big O of n as well, because if everything is sorted, then we will never go into that condition where we are comparing and where j is less than the array element, or if j, right, if this is the sorted part and this is the unsorted part, there will be never this case, then these elements will be swapped and we will never enter that while loop, the second inner while loop, right? We have seen that already. Now this was all about the best case time complexity. Now, in terms of swaps, selection sort will have minimum number of swaps. If you observe the analysis part of all of these sorting algorithms, this is this works in big O of n time, because only one swap was done for the entire in the entire iteration. That means that, and that too, it was outside the for loop, the inner for loop. Okay, so it even works better than insertion sort in terms of number of swaps, right? Now, when we talk about bubble sort, right, the number of swaps are very high. And obviously, we were swapping if this is greater than, as we have already seen in the algorithm, right? If this is greater than that, if this is greater than the next element, or right, a of I is greater than a of j plus 1 or a of I plus 1, we'll swap them, right? So swapping was very much, and it is the worst efficiency, right? It works in terms of swapping, it is the most inefficient one, right? Now it works better than bubble sort, insertion sort, but the number of swaps are as compared to bubble sort, they are significantly low, right? But they are not as good as what selection sort. This is in terms of swapping. Now, if you talk about in place, that means whether we use any extra space. So none of these sorting algorithm use any extra space. So no extra space is required, neither for bubble sort, neither for selection sort, neither for insertion sort. Now, what about stability? As we have already seen in the analysis part of each of these algorithms, selection sort is the only algorithm which is unstable or it is not stable. Apart from that, bubble sort and insertion sort, both of these algorithms are stable. Now, before we understand what is quicksort, let's try to understand what is sorting and why do we require sorting. So sorting is a mechanism wherein we will be sorting or arranging our data either in ascending order or in descending order, right? So let's suppose you have a students, you have 10 students, and all those students have roll numbers allocated from 1 to 100, and you want to know which roll numbers are present and which are absent and which have left the college or school, right? So in that scenario you can easily implement sorting, right? And you can understand, when you have that sorting arrangement in place, you can easily detect which elements or which students are absent or not, right? So herein you can use sorting. So in this tutorial we are going to understand quicksort algorithm. It is one of the most widely used algorithm. It follows a paradigm of divide and conquer. What do you mean by divide and conquer? Basically, we will be dividing our array in such a way that every time we will be dividing, let's suppose this is an array and now we will be dividing into two, then further we'll divide it into two, then further we will divide it into two, and so on, right? So we'll see in the algorithm part how we can implement this divide and conquer paradigm. And in this tutorial we will be implementing this quick sort using recursion. We'll see how we will recursively call those functions based on some pivot element. Now in this recursive call we'll choose a pivot element. Let's suppose you have this array and we were choosing this element as pivot. Obviously you can choose any element as pivot, right? So it can be first element, it can be last element, it can be any random element. But once we have chosen that pivot, now what we will do in each iteration, right, in quicksort, what happens in each iteration, this pivot will have its original position. That means this will be the position in the original array as well. Let's suppose this is our pivot. Now this pivot will have its original position after one iteration. After that iteration is over, and all the elements that are less than this pivot are on the left hand side, and all the elements that are greater than will be on the right hand side. Now then we will be choosing another pivot. Now what are those pivots? We'll see in the algorithm more extensively what are how we can choose that pivot. Now let's suppose we chose this pivot, and this pivot is here, and after the second iteration what happens, this pivot, this will be our next pivot, and this will be our next pivot. Now we will be having two pivots. So this is how we induce that we are implementing divide and conquer approach. Okay, with each
step our problem gets reduced to 2, which leads to quick sort, right, or quick sorting algorithm. Okay, so now we'll be dealing with this subarray and we'll be dealing with this subarray, and now we'll be implementing the same procedure on this subarray. That means this is the pivot and this is the pivot, right? Now let's try to understand the algorithm of quick sort. So now we have this first the method that is there, that is known as quick sort, in which we will be calling this quick sort recursively again and again. But first time around, what happens, we will check, okay, now we have this array, always we will check beginning should be less than end, because that way we can keep the track of things, that okay, this is the part that is already sorted and this is the part that is unsorted, right? And now we will be checking, and after checking that, we will be calling this method. We will see what this method is, we will see the algorithm, and we will see how this partition happens, and we will get the index of the, let's suppose we pick this element as pivot, and after partition, what happens, this pivot has its original position at index 3, right? And that will be returned, and that will be contained in this pivot index, right? And now what happens, now we know that this is its original position in the original array wherein we will get the sorted array. This will be its original position. That means this element, let's suppose is 8 will be at index 3, and this will have its original position after each iteration. Now first time around, what happens, this partition is called. Next time around, what happens, this quick sort algorithm is called again recursively, first time on the left hand side. That means this portion, now in this portion, this will be your pivot. Okay, you see beginning is we are sending the arguments as beginning and pivot index -1. That means we are not including this element because this has been already sorted. We are not including this element, and we are calling this function on this subarray again, and this time around this will be our pivot, and same thing happens. Similarly, when we are done on the left with the left hand side, now we'll be moving to the right hand side. That is, we will be implementing it on pivot index +1. That means this element from this element that is there to the end of the array, and this time around this will be our pivot. Okay, now with that being said, this is what happens when we are implementing quick sort. But now what about this partition method? Let's see how that happens. So in partition, what happens, we will be setting up the pivot element, that is setting up the element which is our pivot. Obviously you can choose any element, but in this tutorial what I am going to use, and what you should try first, that we should try to pick pivot as the last element. Obviously you can pick any element, and its time complexity and depends on which pivot you will be choosing. We'll see that in the time complexity part. Okay, now we have set this pivot as the last element, and now what we are doing, we are saying that okay, the pivot index, this step refers to what, this is the index from, let's suppose this is the pivot index, and what happens, this will be our pivot. Okay, what happens, this pivot index maintains that order. Okay, from this index everything on the left hand side is less than the pivot, and everything on the right hand side is greater than the pivot. So we'll see when we will see an example, and therein I will show you how this pivot index is very important. Okay, now what we will do, obviously at start it is at this position. That means we have no such scenario wherein we have some elements that are less than pivot and we have some elements that are greater than pivot. Okay, so now let's suppose this is our array and this is our pivot, right? And this is our p index, that is the index, pivot index, and it is -1 right now. Okay, now these two steps are done. Now what happens in the third step, now we will iterate from beginning, that is this point, and we will check if any element is less than pivot. If that is the case, then what we will do, we will increment this and swap those elements, that is the the first element and the index that is present at, that means now if you see this step, now we have incremented it first, right? Now let's suppose if any element that is less than pivot, we first increment the pivot index. That means that pivot index will be here, and we will be swapping it with ARR of I, and ARR of I is also at this location, so this element will be swapped with itself. Now you might be thinking, okay, so why we are doing this, right? Why we are swapping this with
its own position. You won't get the intuition in this step, but in the next step you will definitely get the intuition. Now let's suppose this is the thing that happens in the for loop. Now let's try to reiterate this. Now if an element is not less than pivot, let's suppose there was, here we had 5 and here we had 3, so it was less than and we swapped it with itself. Now let's suppose we have this element 6 and it is not less than pivot, right? And what happens over here, so we will not execute this if block, right? And then we'll have this ARR of I. Now I will be here, now I will be incremented, and this time around we have 2 and P index is still here, right? Now this time around it is less than 2, right? And now what we will do, we'll increment first the P index, it will be pointing here, and then what we will do, we'll swap these two elements, right? These two elements will be swapped. So now you have 2 here and you have 6 over here, right? So you see, this is the reason why we have this pivot index in place and why we are swapping them. So in the first step it was that it happened due to the fact that the element was less than pivot, and if the element wouldn't have been less than the pivot, then we have incremented the I pointer and P index would have remained on -1. Now finally what happens, now once the entire iteration is complete, and let's suppose we have 8 over here and we have then 10. Now once the iteration is completed, now what we will do, we'll swap these two elements. That means 5 and 6 will be swapped, and we have 5 here, we have 6 here, we have 8 here, we have 10 here, and we have 3 here, and we have 2 here. So you see, after one iteration, all the elements that are less than pivot will be on the left hand side, and all the elements that are greater than will be on the right hand side. And finally we will return pivot index, that is P index plus 1. That means we will be returning this index, so that this element is not considered or will not participate in any further iterations or any further recursive calls. Because you see, if you observe carefully, that we were sending pivot index -1, that is without 5, all the elements on the left hand side, and +1, that means without this index, all the elements on the right hand side. Okay, this is how partition works. Now you might be confused a little bit. Now let's try to demonstrate this with the help of example. So you see, we have an example over here, right? We have 5, 10, 9, 6 and 7. These are the elements in the array, and we have this pivot here, the last element. We have chosen last element to be the pivot, and after that what we are doing, we have this end pointer and we have this beginning pointer. Also we have that pivot index which will be somewhere around here, right? That pivot index which will be -1. Now this 7 will be checked. Okay, is 5 less than 7? Yes, 5 is less than 7, so it will be swapped with itself, and pivot index will be incremented first and then swapped with itself. Now pivot index will be here. Next time around, our I pointer will be here. First it will be here, then what, it will be incremented. Now we will again check. Okay, is 7 less than 10? No, it is not. So our I will be incremented. I will be now here at this position, right? Now again it will be checked. No, again it will be checked. Yes. So now what happens, 7 and 6, this 6 will be replaced with what, 10. So you have this 6 in here. Obviously pivot index will be incremented first, and then we have the 6 over here and it will be swapped with 10. So 10 will be here, right? Done. And finally when we are at the end, once the entire iteration, this is the step 1, once the entire iteration is completed, we have 5, 6, and then 7 will be the last swapping that we did, the last swap that we did. If you observe here carefully, this swap that we are doing, this is the one that is responsible for swapping this 7 with the pivot index, that is pivot index plus 1, that is this location, and we have this 7 over here and it will be replaced with 9. So that is why we have 9 over here, and 10 was here, and this is the array after first iteration. Now you might be thinking, okay, now this element is fixed. Now we will never talk about this element because this has its original position in the sorted array as well. Now what we will be dealing with, we'll be dealing with this left part and dealing with this right part. So now what happens in this part, right? And what happens in this part? You see, now we have this is our beginning and this is our pivot because this is the last element that we will be picking, and this is our end. Similarly, this is our beginning, this will be our pivot, the last element in this subarray, and the end will be here. Now we'll be again doing the same step, and this time around we'll be checking, okay, pivot is less than, no, nothing will happen, and then we will be swapping this thing with itself, right? And now once this entire subarray is completed, we'll not go any further because this time around beginning is not less than end. Both elements are at 0 and 0 is not less than 0. And now if you observe carefully, this is the condition that we were setting at the start of the function, that is the quicksort function, and we were checking if beginning is less than end, right? So this is the importance of that. Similarly, the same thing will happen over from this side, and again beginning will not be less than end part, and we will not go any further. So after 2 iterations, our entire array is sorted, right? So this is the step 1. After step 2, our entire array is sorted. Now let's try to understand the implementation of quicksort. We have already seen this quicksort function. This is similar to what we saw in the algorithm. So here we have 3 arguments, right? The first is the array, the second is the lower, that is the starting index, and then there is higher, which is h, which is the ending index of the array, end index of the array. That means if you have an array of 3 elements or 4 elements, 0, 1, 2, 3, 4, this is the index, that is high, this will be 4, and this will be 0, and we are passing in this array, and we will be checking. Now we understand why we are checking that low should be always less than the high, L should be always less than H, right? After that, what we'll be doing, we'll be calling the partition function, and wherein we'll be passing these 3 arguments, L, H, and ARR, that is the array, and we will get the index of the pivot, that is this. Let's suppose this is if this is your pivot, we'll get the index of it, that is 2, and then we'll be calling this on 2 minus 1, that is from lower to 2 minus 1, that is what we have written here, p index minus 1, we'll be calling on this part, and then p index plus 1, that is 2 plus 1, that is 3 to 4, that means on this part we'll be calling this quicksort function again. Now let's see the implementation of partition. In partition function, what we are passing, the array, the lower and the higher, that is L and H. Now we are setting the pivot element as the last element in the array, that is your pivot, that is ARR of H. Suppose this is your array, you have 10, 5, 6 and 4. This is your pivot, right? And these will be the indexes, right? And after that, what this p index is, this is somewhere around here, and it is minus 1. Okay, so this will have the index, and this p index is minus 1. After that, what we are doing, we are iterating through it, right? We have I equal to L, and we are iterating to H less than H. That means this element will not be considered because we are comparing it with its same element, with the same element, right, with the H. Now we are checking if ARR of I, that means we have this iterator over here, and we are checking if ARR of I is less than what? If it's less than pivot, no, it is not. So this will not be executed. Now second time around, what happens? Our I will be incremented. Is this less than 4? No, it is not. Is this less than 4? No, it is not. So in entire iteration, this loop was never executed. This if block was never executed. So p index is at its original position, that is minus 1. Now what we will be doing, we'll be swapping p index plus 1. That means earlier it was on minus 1. Now we are incremented it. That means ARR of 0 and ARR of H. That means these two elements will be swapped with each other, and we will be returning p index plus 1. That means this is the index, right? Now once these are swapped, let's swap them, 5, 4, 6 and 10. Now once these are swapped, and now what we'll be sending, p index plus 1. That means this is the index, right? We have this index, that is this 0, right? This is p plus 1 because p index was minus 1, and then we incremented it to 0. Here we are incrementing it, but we are not assigning it. Same thing, we are incrementing it. Now 0 is the index, and it is the original position of this element in this array when this array will be sorted in ascending order. Now what happens? Now this is the that this is the P index, and all the elements that are on the left hand side will be less than. In this case, there are no elements, but all the elements that are on the right hand side are greater than this P index. Okay, is this thing clear? Right, now let's try to see its implementation, and for that we will be using code blocks. Now if you see, we have this partition function over here, and in this partition function we are doing the same things that we have learned so far. We have the last element as pivot, and then we have pivot index, then we are looping around it, then we are swapping it in between when if the elements are less than pivot, and at the end we are swapping it with the P index. So this is your partition function, right? And in the quick sort we are checking if L is less than H, right? And then we are calling the partition function. And similarly, we are calling the quick sort function on the left hand side and on the right hand side. Done. So this is the another function that we are using for checking for printing the elements in the array. There is just one loop, and we are looping around with all the elements through all the elements, right? Done. What is this swap? If you see that we are calling this swap function here, swap elements, and this swap elements we are passing in the addresses of these two indexes, right? Since we are not passing the array, we are passing the elements, and we are passing their references, their addresses, right? And we have this pointer in place wherein this will help us to swap these elements, right? We have this temporary iterator temp, and we are just storing the first element. This is the first, that is P index and ARR of I. We are swapping these, and the changes will happen in the original array as well as we are passing on the addresses, right? Done. This is your swap function, this is your partition function, this is your quick sort function, this is your print array function, and then you have your driver function. In this driver function we have the static array, that is ARR of, and this will help us to calculate the length of the array, that is with the help of size of operator. And then we will print before sorting what were the elements in the array, we are printing out those elements. Then after the sorting, what were the elements in the array, we are printing out those elements once they are sorted. In between we are calling this quick sort function. Here you see on the length -1 and not the length, so that is why we are straight away in the partition we are picking up that H, that higher, that end point. We are not doing H-1 because we are passing, we have already reduced that 1 because indexing starts from 1, so we have excluded that 1, that extra index, right? If we have sent the length would have been 5, and 5 is no index, is not the index in the array. We have 5 - 1, that is the index, because indexing starts from 0 to 4, and it starts from 0, and if we have 5 elements, indexing the elements will be on the indexes 0 to 4 and not the 5. So that element has been removed, and then we are calling out the function print array to check if the elements are sorted or not. Done. Let's try to run this code. Let's try to build and run this, that is compiling it and running it. Now if you see, before sorting the array it was 14, 17, 8, 19, 11 and 20. After sorting the array it is 2, 8, 11, 14, 17 and 90. That is, we have successfully sorted our array, right? So in this way we have seen the implementation on the code blocks of quicksort algorithm. Now let's try to understand the time complexity of quicksort algorithm. In quicksort algorithm, we have now seen that partitioning of elements takes place, and we are partitioning all the elements. That means all the n elements. If there are 8 elements, all the 8 elements will be, we iterate through all the 8 elements, right? So partitioning them takes n time, that is order of n time, and then quicksort problem divides it into the factor by the factor of 2, right? Every time we are dividing it by 2. So the entire process or the time complexity of quicksort in best case and in average case takes order of n time, that is big O of log n. And same thing happens when we are talking about the average case as well. But why this is n square in worst case, that is the question, right? So let me clear it out. So the question is that why this thing happens if you are picking either the smallest element in the array or the largest element in the array as pivot. In that case you are traversing through all the elements again. That means this n is already there for partitioning them. That means you will be iterating through the array. But the extra n, and that means inside that n you're again traversing through all the elements and swapping them, because you have picked your pivot. In worst case, you can either pick it as smallest or the largest element in the array. In both these cases, you will be swapping all those elements with itself. That this element will be swapped, right? This is the largest element, right? This is, let's suppose this is 8, so nothing will happen, right? So this is smallest, then it will be swapped with itself. This is smallest, this will be swapped with itself, this will be swapped with itself, this will be swapped with itself. So all the elements will be swapped, and finally this element will have its original position at the end, right? So this thing will happen if you are picking your pivot as the smallest element or as the largest element in the array. Okay, so in these two cases, this is not the case. You are picking your pivots as random. You are picking your pivots randomly. Okay, in nutshell, when you are picking your element, that is your pivot element, as smallest or the largest element in the array, in that case, that will be your worst case time complexity, and it will be big O of n square. Now let's talk about the space complexity of quicksort. Now you might be thinking, okay, we are not using any extra space, right? We are not using any auxiliary memory like in the form of array, stack, queue, linked list, or anything, right? But for calling this function, that is the quicksort function, we are using recursion, right? We are calling this quicksort again and again, right? Two quicksort calls are there. For maintaining the call stack, we require order of n space, that is the time complexity will be big O of n when we are using this approach. And in the worst case, this will be the scenario that all the elements will be on the call stack. Okay, so in worst case, the space complexity will be big O of n. But if we modify this approach of storing the elements and calling the call stack and maintaining the call stack, we can reduce it to big O of log n. Now let's try to analyze quicksort algorithm. Let's first try to understand the stability. So let's suppose if you have this array 1, 3, 1 dash and 4. Now an algorithm is said to be stable if both these 1 and this one, both these in the sorted array will maintain their relative positions. Now you have this sorted array, right? And both this one and this one are maintaining their relative positions which were earlier in the unsorted array, right? So if that thing is maintained, right, if that thing is maintained, the algorithm is stable, else it is not stable. Obviously you can have another way with which this is also sorted, but this is not a stable, this is unstable algorithm. And if you are sorting in such a manner and you have these things placed, this algorithm is unstable. So if you talk about quicksort algorithm is an unstable algorithm, although we can do some modifications and we can stabilize it, or we can make this algorithm as stable. But as of now, if you talk about quicksort algorithm, it is an unstable algorithm. What about in place and out place? Since we are not using any auxiliary memory, right? We are not using any extra space explicitly, right? In the form of array or linked list or stack, right? Or even queue. We're not using any extra memory, right? So this algorithm, quicksort algorithm, although we are maintaining a call stack wherein we are maintaining a call stack and we have a space complexity of big O of n, but since we are not explicitly mentioning these auxiliary memories, this algorithm is an in-place algorithm. And these are the two analyses that can be done on quicksort. So in nutshell, if you talk about quicksort, right, it is unstable algorithm and it is in place algorithm. Now let's see an example wherein we will be implementing quicksort algorithm. We have a question wherein we have an array and you want to find the kth largest element in that array. Let's suppose you have an array 3, 2, 1, 5, 6 and 4. In this array, what we are trying to find out the second largest element. Now if this array would have been sorted, right, 1, 2, 3, 4, 5 and 6, so we can easily find out the second largest element that is present on this location with the help of the length of this array, that is, let's suppose the length of the array is len length, right? This is the variable which contains 0, 1, 2, 3, 4, 5, that is 6 is the length of the array. Then we will subtract what? The k from it. That means length minus k, which is nothing but 6 minus 2 and 4, and we will get the index of the element that is largest. In this case we have 5, and the index the number at index 4 is 5, so 5 is the second largest element in the array. But for that we need this array to be sorted, and if we apply any sorting algorithm, in the worst case, the best time complexity that we can have is n log n, but we want to do something that is much better than this, right? So we will be implementing quick sort, right? And we will implement its partition part, and also the swapping will be there, the swapping functions will be there. So now let's see how we can do it. Let me clear this out and let's move on to the next slide, wherein we'll be talking about the implementation. So we have this function in place, find kth largest, and we have this array that is named as nums. Okay, let me just write this similar array: 3, 2, 1, 5, 6, 4. 3, 2, 1, 5, 6, and 4. This is the array that we have, and we want to find the second largest. Okay, done. Now what is the desired location? As we have already seen, the desired location is length minus k, that is if this array would have been sorted. Now what we will be doing, we'll be calling this quick method, and in this method we'll be passing the array, the desired location, the starting index and the ending index, that is this 0, 1, 2, 3, 4, 5. This will be 5. The starting index will be 0, the desired location is 4, and the num is the array name, this nums. Okay, done. Let's see how we can implement this quick method. The quick method, in this quick method, obviously we'll be having these parameters, right? And now what we are doing, we are calling this partition, right? We are calling this partition, and in that partition we will be doing same stuff, right? Same stuff means that we'll be having this last element as our pivot, and then we'll be arranging elements in such a way that on the left hand side of the partition, that pivot element will be elements that are less than this, and on the right side it will be greater than. Okay, so now what happens once this pivot is done, then we will be having this pivot element and it will be returned to us. Then we'll be checking if that p, that index, is equal to the desired index. That means if 4 is equal to 4, that in this case, right, we have this 4, right, the desired index. If that is equal, those two indexes are equal, that means we have found our element and we will be returning that element, right? So nums, that is the name of the array, nums p, that is the index, right? So if that is the case, we are done. This is the algorithm is finished and we have solved this problem. But if that is not the case, then we will check. Obviously, if we are checking for something that is if the desired location is greater than that, right? Let's suppose we have a desired location 4 and we have a pivot index 8, then obviously all the elements on the left, on the right hand side will be useless for us, right? So that is why, if that is the case, we'll be neglecting this part, and if vice versa, we'll be neglecting this part. So same thing we are doing here. So if desired location is less than the pivot, that is p, we will recall, or we will again call this function with some different arguments. That is, nums will be there, obviously desired will be there, and start will be there, and p index -1. That means all the indexes apart from that, that means the right hand side will be neglected, and in this case the left hand part will be neglected. So in this way you will be implementing this with the help of quicksort. Now let's quickly see the implementation in code blocks. So now if you can see, we have the swap elements that we have already seen, the swap method that is there. We are just swapping the elements. Done. We have this find kth largest element. This method is there, and in this we are just calling this quick method. That's it. And we have found out, we know how to find out this desired. We have already talked about this. Desired location will be when the array is sorted, and then the element that you are looking for will be at this location. Okay, this is your find kth largest. This is your quick, right? Your quick will have these arguments, and this is how you neglect some part of the array, that is either the right hand side of the pivot or the left hand side of the pivot. Done. This is your quick function. This is your partition function. Already you have seen this, and same thing we are doing here. we are picking up the last element as pivot. We have this p index wherein this will be the smaller element, and after that all the elements from the pivot will be less than this index, and all the elements will be greater than on the right hand side from this index. Okay, then we are looping around it and we are finding out, we are swapping these elements. Swap elements method is already defined here. So we have after that, once this loop is over, and then we will be swapping these with the last element, that is the pivot index. And once this is done, we will be returning this p index plus 1, that is the pivot index. Done. This is similar to what we have already seen in the quicksort algorithm, right? And then after that, what we are doing, we are just printing out the array, or we don't require this because we are just we are trying to find out what the elements in the array, the largest element that is there, right? We don't require this thing. Let me just remove this method. So one method is removed. Done. Okay, we have this thing in place. So these are all the four methods, and then finally what we have our one more method, that is our driver function, and in that we have the static array, that is 3 2 3 1 2 4 5 5 6. So in this array, what we are doing, we are trying to find out the fourth largest element. If you observe carefully, what will be the fourth largest element? It will be 4, because 6 is there, 5 is there, 5 is there, and 4 is there. So fourth will be the element which is the fourth largest in this array. And with the help of the size of operator, we are just trying finding out the length. Okay, so then once this is done, what we will do, we'll call the kth largest element. This function has been called, and then we are passing on the arguments to the quick method, and then that will call partition, and then that will call swap. So this way around, we have these methods in place. Now let's try to run this. The output that we are expecting should be 4. Let's try to build and run this example. So you see the output is 4. Okay, so in this way you have seen the example wherein we implemented some functions. Swap function was there, then the kth largest, find kth largest function was there, right? We have quick, it is also known as quick sort or quick select. Okay, this function was there, right? Quick function was there, and partition function was there, and finally we had our driver function, which was. So in this way we solve this problem of finding the kth largest element in the array.
What is merge sort? If we talk about merge sort, let's try to understand first sorting. So sorting is a mechanism of giving order to your values, right? So let's suppose you have some values, random values, 10, 30, and then you have 5, 2, 1, and so on, right? You have these values, and now you want to maintain some order. So in order to visualize this data, let's suppose you want to see the ascending order of it or the descending order of it. That is what you mean by sorting. So let's suppose you have a class, and in that class you have several roll numbers, and some of the roll numbers are not present, and then you want to sort those roll numbers in terms of ascending or descending order. That is when you require sorting. So this is the basic intuition behind sorting, trying to give order to some kind of values or some kind of a data set, right? So in this particular tutorial, we are going to talk about merge sort. So merge sort is a classical sorting algorithm. In this sorting, every time your problem is divided into sub problems so that your problem set is reduced, and then you will be focusing on that sub problem. Similarly, every time when you're dividing your sub problems, you will keep on dividing it unless and until there is only one element left, right? If you compare it with simpler sorting algorithms like bubble is there, insertion is there, selection is there, quick is there, when you talk about its time complexity as compared to these algorithms, this is very much efficient. Now it follows a paradigm of divide and conquer. What does this mean? This means that first you keep on dividing your sub problems, and then you will conquer those problems, and then you will combine those things. Okay, so herein we will see when you are trying to divide your sub problems, and then when you have your problem set and those problem sets are conquered, that means those problems are further, when you talk about in this example, those sub problems are sorted in this case, and then you have conquered them, and then you will combine them. That is your merge phase, wherein you will be combining your problem again, and then for forming again a single sub problem. So every time you will be dividing that sub problem, you will be conquering it and combining it. So this is how this divide and conquer paradigm works. So basically, when you're dealing with merge sort, you are focusing on two functions, that is your merge function and your merge sort function. So now let's talk about this divide. That means you're dividing your subproblems, which continues unless and until there is only one element left, because one element in itself is sorted, right? Now this is your divide phase. What about conquer? Basically, you are conquering those individual sets and then merging those two subproblems into a single problem. And finally, you will be doing it on each step, and finally you have your original array, which is sorted. Now let's talk about merge sort algorithm. So first let's talk about merge sort method. So in this method, what we are doing, we are dividing our array into further sub arrays. How we are going to do that? We are basically, if we have this array, right? And this array, let's suppose this contains 8 elements, right? This is our array. And let's suppose this is our left pointer and this is our right pointer. And now what we are doing, we are dividing it. So we need some kind of an iterator wherein we will store the sum of, and we try to calculate the mid value. How would you do it? In simple words, we calculate left plus right divided by 2. That's it, right? So we have this division, and then we will divide this part because we are calling this function again, right, on the left hand side. So this is going to call on this side. That is, we will be talking about now only 3 elements. So this is let's suppose, or let's take 4 elements on this side and 4 elements on this side. So our mid will be 3.5. So we'll be talking about elements from 0 to 3. So we will be talking about 4 elements, and then further these 2 steps are remain. Why? Because we are implementing this in recursive fashion. So now let's suppose this is our first function call, and you have these 3 steps. Let's name it 1, 2, and 3. Okay, so in the first function call, 1, 2, and 3. So this is the first function call, and in this we're calling again, this is the second function call, and we are calling again these 2 remaining, right? And we are calling again 1, 2, and 3, right? So in this case, again we are calling it on these 4 elements, and it will be divided into further 2 elements, 0 and 1, right? And in this case, again this will be called on these 2 elements, right? Here we are talking about only 2 elements. So this is the third function call, and again we will be dividing it. These 2 and 3 steps are still remaining. So in the fourth step, what we are dealing with only single element, right? And in this case, we are talking about only this element, right? And further, we will not be able to divide it. And in that case, our left will be greater than or equal to right. And in this case, it will be equal to. So we will return. So now it will be returned, right? And then whatever was the left over, right? Now we talk about this single element, the other element that was left behind. We'll talk about that. So again, that will be divided into 1, right? And again, this second option, I'll just erase it because it looks a little bit messy. So now what happens? Let me just put it again in red. So here we call this 4th time, and this time it returned, right? So in this case, now we will be on the second step. Now again, it will be called on that single element, and again left will be greater than or equal to. In this case, it will be equal to, and then we return. So again, we are returning. So we have these 2 elements, 1 and 1. That means not 1 and 1 element, but there is only a single element in both these arrays, right? Why I'm saying that in these 2 arrays, we will check when we talk about merge. Okay, we'll see how that is implemented. Okay, so now these 2 function calls are done, and then we deal with merge. Now before going into the merge, let me show you a demonstration of how things look. So you have these elements, and here you have how many elements? You have 5 elements, right? And now you're dividing it into 3 and 2. Now this is your first step. The second step will be this. So now will you go ahead and create this as your third step? That means you will move on to this? No, because we saw unless and until left is not, there is no left, right? We will not go to the right. So this is your second step. Then this will be your third step. This will be your fourth step. Now you will move on to your fifth step, right? And now once you don't have anything on the left, nothing on the right, then what happens? Will this be your sixth step? No, your sixth step will be merge. So let's move on to merge now. So in the merge function, if you see, the algorithm for that is simple, that you create two sub-arrays, that is, one is your left array and another is your right sub-array. Now in this you have, obviously in the last case, if you have seen, we have a single element here and a single element here. Now once we have deduced out the length of these arrays, what should be the length of these sub-arrays, and we have declared the length or declared these arrays, and then we have initialized these arrays. Once these 3 steps are done, then what we are going to do, we are going to create 3 iterators, I, j and k, and those iterators deal with, I iterator will deal with the left array, j iterator deal with right array, and k with the original array, which helps us to insert the elements. So once we have everything in place, what we are going to do, the next step is comparing the values, right? If this element, that is the element in left array, is less than the element in the right array, we are going to insert that in the original array. So now let's suppose you have 10 here and 23 here. So 10 is less than, so we are going to insert this and we increment the k pointer. And now also our I pointer will be incremented. It was earlier, it was 0 and it will go to 1, right? And now what happens? Now our I is pointing to 1 and our length is also 1. So now that in that case, when one of the array is exhausted, the next array, whichever is left, right? It can be either the left array or the right array. Those elements will be directly inserted in the original array, because we know for the fact that both of these left as well as right arrays will be sorted in itself. Okay, so let's see what is the next step in the demonstration. So here we had our steps, right? And this will be the 6th step wherein we are going to merge this thing. Now, will this be your 7th step? No, your 7th step will not be this. Your 7th step will be here. This will be your 7th step. Now 6th step is done. Now you will be dividing it and you will be creating all those arrays. Now once you have your right array, and there is no right because this left is already done, and now you had your right left. Now this is also done. Now your 8th step will be this, that you will be merging it. This will be your 8th step. Then you will be merging it. Now will this be your 9th step? No, you have your this array, that is your left array, in place. But what about the right array? Is this in place? No, it is not. So now let's try to calculate that. Now what will be your 9th step? This left is done. This is your 9th step. Then what will be your 10th step? This is your 10th step. Well, now there is no left, right? Now we'll move on to this right. So this is your 11th step, because this is the right side of it, right? And now when you don't have anything on the right, now you will be merging these 2 steps, and this will be your 12th step, which is over here. So this is your 12th step. That means you will be merging these 2, and the final sorted array is this array, and you will get this array in the 12th step. So you see 10, 11, 16, 20 and 30. Now if you observe carefully, you have these individual arrays 1 and 1. So now while you are merging them, you are also sorting them. So the left array is sorted, and same thing happens on the right hand side as well. If you see 3 and 4, these 2 elements are sorted in this left array. So this is the reason in the right array, right? Not the left array. So now when you are merging them, you will get again an array which is sorted in itself. You see 10, 16 and 23. So if one of the array is exhausted, the next array elements can be directly inserted in your original array. Let me erase this, and you see you have your left array which is sorted, and then you are merging it with the right array which is also sorted. Now, if one of the arrays is exhausted, the next array, either it can be left array or the right array, the elements from that array can be directly inserted in the original array, because we know the elements itself in either of the arrays, either the left or the right, are sorted. Okay, so this is how you execute your merge function.
Now let's see the implementation of merge sort. So in this merge sort, we first have this method or function over here, which is merge sort. And it takes in the argument as the array that we want to sort, the starting index and the ending index, which is length minus 1. And we will only divide our merge sort in such a way that start should be always less than the right. That means if we have this portion of an array in which we have 8 elements, right, we will divide it in such a way that 4 and 4 will be divided. Then we will divide it further that 2 and 2 elements are divided, then 1 and 1 elements are divided. And based on these, after the complete traversal is done, that means once we have these single elements in place, and then we will start to merge them. As you can see that we over here we will stop when this scenario fails. If start is not less than right, then we will stop, and we keep on dividing our arrays, right? You can see that we are doing over here mid equal to start plus right divided by 2. So we keep on dividing unless and until there is no division possible. Now what we are doing, we are implementing this merge sort using recursion. Let me clear my screen. Now if you see this 1, 2 and 3 steps, let me just put an activation record over here. Now how does recursion happen? That 1, 2 and 3 functions are there, right? So function call to this will be called again, right? This merge will be called again, activation record second will be created, again merge sort will be called, unless and until this start is not less than right. Now we will return. Now the second step is there. Now this will be executed for this activation record. Okay, then how it executes, it will execute on the right hand side. Okay, from mid plus 1 to right. That means once we have divided our array that was of 8 elements into 4, then into 2 and 2, then into 1 and 1. Now once we have this 1 in place, then it will call the right hand side of this one element that is left. Once both of these elements are divided, then only we'll call the merge sort on them that we have already seen, right? We'll call the merge sort and we'll merge them 10 and 23, right? We'll merge them together. So now this is how your merge sort works, right? This will work on the left part and this will work on the right part. Then finally we call our merge function. So now let's see how it is implemented. If you can see in this merge function, we have an array that is an argument, the starting index, the middle index and the end index. Okay, now then we calculate the length for both the arrays that we are going to use. Then we declare our arrays over here, and finally over here we will initialize our array. So basically over here what we are doing, we are creating two arrays, that is our left array and our right array. Once we have calculated the length, then we declare it and then we initialize it. Once these steps are done, the next step is that we have these three iterators, right, I, j, k, which help us to iterate through the elements. Now let's suppose we have this the single elements that we have, like 10 and 23, let's suppose 23 and 10. Okay, now we have these elements over place. We have this I pointer for this to iterate through the left array, and to iterate through the right array we have this j pointer, and finally we also have this k pointer which helps us to iterate through the original array. Okay, so we have these three pointers. Now we will check if I is less than the length that we calculated. Obviously 0 is less than 1 and 0 is again less than 1. So what we are doing, we are comparing them, and the one which is less than will insert that element in the array. So in this case 10 will be inserted, and then we increment our k. So I pointer will be not incremented because that was not picked, so I is still there. J will be incremented and j will be at 1, right? It was earlier at 0, now it will be at 1. So now once j is incremented, we inserted the value after that, right? You see a of k equal to left not the left, this part was not executed, this part was executed. So what happened? AR of K, that means this array was updated and with the help of a right array, and we incremented our J pointer, now J is 1, and then we also incremented our K pointer because now the next time we'll start inserting value over here. Now, once we again check the condition, this time condition fails. This condition is true, but this is false. So now what happens next is that these two for loops helps us to pick up the remaining elements that are there. In this case, let's suppose this this array was done, but the left array is still there. So for that, what we do, we calculate if 0 is less than 1 in that left part. Yes, it is. So we pick the elements and start inserting it into this array. So 23 is picked and inserted into this array. So that means these are merged together. So now once this is done, then we update our I, and I now is to 1. So 1 is not less than, so the condition fails. Plus we also update our K pointer. So now this I is pointing to 1 and our K pointer is over here next time, so that we can use it for the next time. Similarly, there can be one or more than one elements left either in the left subarray or in the right subarray. Anyways, these subarrays are in themselves sorted. So if one of them array is exhausted, the other array we can directly insert them in the main array, that is with the help of this K pointer. So that is not an issue. So these are used for picking up those elements and inserting them in the original array, because we know for sure that left and right sub arrays are sorted in itself. Now let's try to implement this in code blocks. So you see we have over here, we have this library, and then we use this merge function. In this we have 4 arguments. We calculated the lengths, we declared our arrays, then we initialized our values, then we have these pointers I, K, I, J and K. We initialized them, and then we iterated, right? With the help of this while loop, we pick up the smallest element, and unless and until the condition fails, the rest of the elements that are present either in the left array or in the right array, we will insert those values directly with the help of this for loop in the left array and with the help of this for loop from the right array. Then we have this merge sort function wherein we have 3 arguments and we are calculating the mid. Then we are calling merge on the left hand side and then calling it on the right hand side. Once we cannot call it any further, then what we are doing, we are merging them with the help of this merge method. We have also this display method that is over here, which helps us to print all the elements in the array. Then we have a main method, that is our driver method. In this we have array that is 6, 5, 12, 10, 9, 1. We calculate the size of this array with the help of size of operator. Once we calculated the size, then what we do, we display the elements, right? We display the elements that were there before sorting. Then we will call our merge sort, and we will pass in array 0, that is the starting index, and the ending index, that is size minus 1. Once we have called the merge sort, then what we are doing, we are then displaying the elements that are there after we applied sorting. Now let's build and run this program. Now as you can see, the original array was 6, 5, 12, 10, 9, 11, which is obviously unsorted. Then we have the sorted array as 1, 5, 6, 9, 10, 12. So in this way we implemented merge sort. First we implemented the merge sort method. Then we implemented the merge function, that is the merge method, and then the display for displaying all the elements. Then we also implemented our main method, that is our driver method, with the help of which we initialized a static array, or we declared their static array, and based on that array we called merge sort. So in this way, we have implemented our merge sort in the code blocks using C language.
Now let's talk about time and space complexity of merge sort. So first we are going to talk about time complexity. So as you can see that every time we are dividing our problem, or if you have 8 elements, we are dividing our array into further sub problems. That is, we are dividing it, right? So if we are talking about 8 elements in the first array, then we are talking about 4 elements, then we are dividing into 2 elements, then we are dividing into single element. So every time our problem is reduced by half. So when this is the case wherein you have n, then you will talk about n by 2 elements, then you will talk about n by 4 elements, then you will talk about n by 8 elements, and so on, right? If this is the case, this is the case where you are dealing with log to the base 2 and n. Why this is the case? Let me take an example. So let's suppose your n is 8 in this case, right? Log to the base 2 and value of n is 8. So this is 3. That means you will be dividing your problem 3 times. That is the correct scenario that follows in here. So you have 8 elements, then you are dividing it into 4. Then you are dividing into 2. Then you are dividing into 1. That's it, right? So you have three such instances in this example that you are dividing your problem 3 times into half. So this is the case where your complexity is log n. So to the base 2, obviously, right? So this is the scenario, but this is a scenario only for the first phase when you are dividing it. But then you are also merging it. That is the second phase. In that phase, you are doing it for all the n operations or all the n elements or iterations. And in that case, you are dealing with all the n elements. So the total time complexity is n into log n. So this is the time complexity of a worst case. And obviously this will be the time complexity for best case, because in best case, only the comparisons, as we already seen, only the comparisons will reduce and rest will remain same, because you're again checking for all the n elements, right? So in that case also, your time complexity will be n log n. And for all the time complexities, that is best case, worst case, and average case, the time complexity of merge sort will be n into log n. Log n, because of the reason we are dividing it, and then we are dividing it again and again and again. So this is a case where log to the base 2 comes into picture, and we are doing it for all the n elements. That is in the second phase where we are merging it. So that is your n. So the total time complexity is n into log n. Now, what about the space complexity? If you talk about space complexity, here we are using an extra memory, right? And every time we are using, let's suppose in the last case, we are using memory of size 1. And in the above case, before that, we are using memory of size 2, then 4, then 8. So in the worst case, when we are talking about space required, is that we are using n amount of memory, right? So all the n elements are stored, because in the last step, we are using an auxiliary memory wherein we are storing all the 8 elements. So in that case, what we are doing, we are copying our elements in an auxiliary memory, wherein at worst case, the space that we require is n, that is the number of elements. In this case, we require 8 memory spaces, right? And so the space complexity of merge sort is big O of n. Now let's try to analyze merge sort. First, we are going to cover number of comparisons. Then, is it stable or unstable algorithm? Then we are going to cover, is it in place or out place algorithm? So now let's try to understand how many comparisons are required when we are dealing with merge sort. So let's take an example. Let's first talk about worst case and then we'll talk about best case. Space complexity, we always talk about worst case. That is big O notation. It can be n, it can be anything, right? So we always talk about big O notations. So let me clear it out and let's talk about this thing. So for worst case, let's take an example. Let's suppose we have, this is the second last step wherein we try to merge these two and we merge them in a single array, right? This is about merging, where comparisons happen and then we merge them in a single array. So let's take the second last step. In that, let's do 1, 2, 3, then 4, then 5, then 6, then 7, then 8. So this is the second last step wherein we have these two partitions and we are trying to merge them in a single array. So let's see how many comparisons are required in this step. Okay. So 1 will be compared with 2. So here you have it, 1 comparison, and we'll merge them into a single array. Now this is gone. Now still 2 and 3 are remaining. So now what we do, we compare 3 and 2. So 2 is smaller and it will go in this array. This is also gone. So 3 and 4, 3 is smaller. Now we move on to 5. So 5 is gone. 5 and 6 will be compared. 5 and 4 first will be compared. We have 4, then 5 and 6, we have 5, then we have 5 and 6 and 7, we go 6, then 7 and 8, we have 7. So after this 8 will go directly in this, because we know if one of these arrays, that is your left array and right array, if one of them is exhausted, right, the next element will go directly in the merged array. So this is your sorted array, and the number of steps or comparisons required is 1, 2, 3, 4, 5, 6 and 7, that is n minus 1. Okay, now if we would have the best case scenario wherein this array is sorted, right, 1, 2, in this manner, 1, 2, 3, 4, and then 5, 6, 7 and 8. In this case, this would have been compared, this would have been compared, this would have been compared, and we have this 1, 2, 3 in this array, and rest of the elements would have been directly inserted, 5, 6, 7 and 8. Okay, let me just write it somewhere else, as this might not be visible to you guys. So just a minute. So what would have happened? So we have this array at the end, we have 1, 2, 3, and then rest of the elements 5, 6, 7 and 8 would have been inserted directly. So the number of compares would have been n by 2, that is 4, right? Only 4 comparisons. But this is the best case, and we never talk about best case. So now let's try to erase everything, and now let's see. So we have 7 steps, right? Now this we came, how would we evaluated this? By n minus 1. Now what about these two cases? So we have this, first we talk about this array wherein we have 4 elements on this side and 4 elements on this side. But how would we have evaluated this array? We would have something like this, 2 comparisons, these 2 sub arrays, this is the left and the right, and then this would have been merged into this, and there would have been another 2 sub arrays that would have been merged to this, right? So how many comparisons would require to get this merged array? So now let's look at that. Let me erase everything. Now let's talk about these 2 partitions first, right? So now we merge this into that, getting those 4 elements, right? And getting these 4 elements. So now it seems that we could have compared this and then this, and rest 1 element would have been directly. So 3 comparisons here, and we have similar case here. So 3 plus 3, 6 comparisons. Now if we evaluate this and put it in a form, in the form of formula, it would have been n by 2 minus 1 into 2. Why this 2? Because same thing happens over here. Okay, so we are just doubling it out. So let me put it, in this case we have n equal to 8, and 8 divided by 2 minus 1 into 2. So this is nothing but 4. 4 minus 1 is 3. 3 into 2 is 6. So 6 comparisons, right? So this is the formula. But what happens when we talk about this? How we evaluate it? How would we have evaluated this case? Now let's talk about that. Erase this thing. So in that case, we would have something like this, right? So we would have this 2, and this would have merged into this. And similarly, this would have happened 4 times, right? 3 more times, that is 4 times we would have such scenario. So here the comparisons would have been only 1 comparison, right? So in that case, it would have been something like 2, n divided by 2 raised power, let me put an arbitrary value, like, or let me put a value for in this case, then we will evaluate a formula. So minus 1 divided by 2 raised power 2 into 2 raised power 2, right? So in this case, how many comparisons? We would have n equal to 8, and this is 2 raised power 2, which is 4, which would have resulted in 2. 2 minus 1 is nothing but 1, and multiplied by 4. So 4 comparisons. Make sense? This is 1 comparison, and this would have directly inserted in, we would have directly inserted in this merged array. So only 1 comparison is required. Similarly, we have other 3 situations, that is total number of situations. Such situations are 4. So in the first iteration, when we talk about these 8 elements, when n is 8, we had 7 comparisons. then we had 6 comparisons, and then we had 4 comparisons. So total of 17 comparisons. So now let's try to evaluate a formula so that we will get this 17 as it is for the number of comparisons. So if we talk about this thing, we would have something like this. N, if we evaluate the formula, we have n divided by 2 raised power I minus 1, then minus 1, and then into 2 raised power I minus 1. Now what is this I? This is nothing but your number of levels, okay? And this level is nothing how many times you are going to get that comparison situation. In this case, when n was what? N was 8, we had 3 levels, right? So it would have been something log n to the base 2. Now this would have been only 3, but the last merge is also there, so plus 1, okay? And this is only for the case when n is even. What about odd cases? So we take the seal of this, that is, we take the larger side. So this is the number of levels, that these I. What about this? This is nothing but your comparisons, how many comparisons you are taking, and this is nothing but your nodes. So if we try to evaluate this thing, this turns out to be what? N, the seal value of log 2 to the base n minus 2 raised power log n to the base 2 plus 1. Now we need to find out that if this 17, if this equation holds, right? So in this case, n was 8, right? And the seal value of log 2 to the base 8 is nothing but 3, right? 2 to the base log 2 to the base 8 plus 1. So now if you evaluate this, this will be 8 into 3 minus 2 raised power 3 plus 1. So this turns out to be 17. So our equation holds, and the formula for calculating number of comparisons is nothing but n. Then you have your seal value of log n to the base 2, right? This is a seal value because we are taking into consideration both even and as well as odd cases. Then minus 2 raised power log n to the base 2 plus 1. What about unstable or stable? Merge sort is a stable algorithm. What does that mean? It means if you have an array wherein you have 1, then you have 3, then you have 2, then you have 4, then you have 2 dash. Now these two, this 2 and this 2 is repeated, right? Now in the sorted array, this order will be maintained. That is what is known as stability. So you have in your sorted array 1, 2, and then you have 2 dash. That means this 2 and this 2, the order will be maintained in the sorted array as well. So it is stable. And what about in place or out of place? So in place means that you are not using any extra memory, but in our merge sort, as we had already seen, that we were using two arrays, that is the left array and the right array, for storing, which also helps us in comparing the values and then inserting them in the original array. So we are creating extra memory, right? So in that case, this is an out place algorithm. All right. So this is the whole analysis of merge sort algorithm. Now let's try to analyze merge sort. First, we are going to cover number of comparisons. Then, is it stable or unstable algorithm? Then we are going to cover, is it in place or out place algorithm? So now let's try to understand how many comparisons are required when we are dealing with merge sort. So let's take an example. Let's first talk about worst case and then we'll talk about best case. So anyways, when we are dealing with number of comparisons or anything like space complexity, we always talk about worst case. That is big O notation. It can be n, it can be anything, right? So we always talk about big O notations. So let me clear it out and let's talk about this thing. So for worst case, let's take an example. Let's suppose we have, this is the second last step wherein we try to merge these two and we merge them in a single array, right? This is about merging, where comparisons happen and then we merge them in a single array. So let's take the second last step. In that, let's do 1, 2, 3, then 4, then 5, then 6, then 7, then 8. So this is the second last step wherein we have these two partitions and we are trying to merge them in a single array. So let's see how many comparisons are required in this step. Okay, so 1 will be compared with 2. So here you have it, 1 comparison, and we'll merge them into a single array. Now this is gone. Now still 2 and 3 are remaining. So now what we do, we compare 3 and 2. So 2 is smaller and it will go in this array. This is also gone. So 3 and 4, 3 is smaller. Now we move on to 5. So 5 is gone. 5 and 6 will be compared. 5 and 4 first will be compared. We have 4, then 5 and 6, we have 5, then we have 5 and 6 and 7, we go 6, then 7 and 8, we have 7. So after this 8 will go directly in this, because we know if one of these arrays, that is your left array and right array, if one of them is exhausted, right, the next element will go directly in the merged array. So this is your sorted array, and the number of steps or comparisons required is 1, 2, 3, 4, 5, 6 and 7, that is n minus 1. Okay, now if we would have the best case scenario wherein this array is sorted, right, 1, 2, in this manner, 1, 2, 3, 4, and then 5, 6, 7 and 8. In this case, this would have been compared, this would have been compared, this would have been compared, and we have this 1, 2, 3 in this array, and rest of the elements would have been directly inserted, 5, 6, 7 and 8. Okay, let me just write it somewhere else, as this might not be visible to you guys. So just a minute. So what would have happened, so we have this array at the end, we have 1, 2, 3, and then rest of the elements 5, 6, 7 and 8 would have been inserted directly. So the number of compares would have been n by 2, that is 4, right? Only 4 comparisons. But this is the best case, and we never talk about best case. So now let's try to erase everything, and now let's see. So first we have 7 steps, right? Now this we came how would we evaluated this? By n minus 1. Now what about these two cases? So we have this, first we talk about this array wherein we have 4 elements on this side and 4 elements on this side. But how would we have evaluated this array? We would have something like this, 2 comparisons, these 2 sub arrays. This is the left and the right, and then this would have been merged into this, and there would have been another 2 sub arrays that would have been merged to this, right? So how many comparisons would require to get this merged array? So now let's look at that. Let me erase everything. Now let's talk about these 2 partitions first, right? So now we merge this into that, getting those 4 elements, right? And getting these 4 elements. So now it seems that we could have compared this and then this, and rest 1 element would have been directly. So 3 comparisons here, and we have similar case here. So 3 plus 3, 6 comparisons. Now if we evaluate this and put it in a form in the form of formula, it would have been n by 2 minus 1 into 2. Why this 2? Because same thing happens over here. Okay, so we are just doubling it out. So let me put it in this case we have n equal to 8, and 8 divided by 2 minus 1 into 2. So this is nothing but 4. 4 minus 1 is 3. 3 into 2 is 6. So 6 comparisons, right? So this is the formula. But what happens when we talk about this? How would we have evaluated this case? Now let's talk about that. Erase this thing. So in that case, we would have something like this, right? So we would have this 2, and this would have merged into this, and similarly this would have happened 4 times, right? 3 more times, that is 4 times we would have such scenario. So here the comparisons would have been only 1 comparison, right? So in that case it would have been something like 2 n divided by 2 raised power, let me put an arbitrary value, like or let me put a value for in this case, then we will evaluate a formula. So minus 1 divided by 2 raised power 2 into 2 raised power 2, right? So in this case, how many comparisons? We would have n equal to 8, and this is 2 raised power 2, which is 4, which would have resulted in 2. 2 minus 1 is nothing but 1, and multiply by 4. So 4 comparisons. Make sense? This is one comparison, and this would have directly inserted in, we would have directly inserted in this merged array. So only one comparison is required. Similarly, we have other 3 situations, that is total number of situations. Such situations are 4. So in the first iteration, when we talk about these 8 elements, when n is 8, we had 7 comparisons, then we had 6 comparisons, and then we had 4 comparisons. So total of 17 comparisons. So now let's try to evaluate a formula so that we will get this 17 as it is for the number of comparisons. So if we talk about this thing, we would have something like this. N, if we evaluate the formula, we have n divided by 2 raised power I minus 1, then minus 1, and then into 2 raised power I minus 1. Now what is this I? This is nothing but your number of levels, okay? And this level is nothing, how many times you are going to get that comparison situation. In this case, when n was what? N was 8, we had 3 levels, right? So it would have been something log n to the base 2. Now this would have been only 3, but the last merge is also there, so plus 1, okay? And this is only for the case when n is even. What about odd cases? So we take the seal of this, that is, we take the larger side. So this is the number of levels, that these I. What about this? This is nothing but your comparisons. Your comparisons, how many comparisons you are taking, and this is nothing but your nodes. So if we try to evaluate this thing, this turns out to be what? N, the seal value of log 2 to the base n minus 2 raised power log n to the base 2 plus 1. Now we need to find out that if this 17, if this equation holds, right? So in this case, n was 8, right? And the seal value of log 2 to the base 8 is nothing but 3, right? 2 to the base log 2 to the base 8 plus 1. So now if you evaluate this, this will be 8 into 3 minus 2 raised power 3 plus 1. So this turns out to be 17. So our equation holds, and the formula for calculating number of comparisons is nothing but n. Then you have your seal value of log n to the base 2, right? This is a seal value because we are taking into consideration both even and as well as odd cases. Then minus 2 raised power log n to the base 2 plus 1. What about unstable or stable? Merge sort is a stable algorithm. What does that mean? It means if you have an array wherein you have 1, then you have 3, then you have 2, then you have 4, then you have 2 dash. Now these two, this 2 and this 2 is repeated, right? Now in the sorted array, this order will be maintained. That is what is known as stability. So you have in your sorted array 1, 2, and then you have 2 dash. That means this 2 and this 2, the order will be maintained in the sorted array as well. So it is stable. And what about in place or out of place? So in place means that you are not using any extra memory, but in our merge sort, as we had already seen, that we were using 2 arrays, that is the left array and the right array, for storing, and which also helps us in comparing the values and then inserting them in the original array. So we are creating extra memory, right? So in that case, this is an out place algorithm. All right. So this is the whole analysis of merge sort algorithm. Now let's talk about merge sort example. In this example, we are given 2 sorted arrays. As you can see that this is our first array. Let's name it ARR1 and let's name it ARR2. These are 2 sorted arrays. As you can see, 1, 5, 8, 10, and 20. And the another array that we are given is 4, 6, 9, 15, 40, 55, and 92. So these are 2 sorted arrays, and we want to merge them in a single array. And obviously the output should be also in a sorted format. So 1, 5, 6, 8, 9, 10, 15, 20, 20, and then 40 and 55 and 92, which is obviously sorted. Now, for this question, in order to solve this question, we can use or implement the merge method that was there in the merge sort algorithm.
We can see we have implemented this merge method over here, which takes in two arrays as an argument, which is our array 1 and array 2, then the size of those arrays, right? Then what is happening, we are creating one temporary array and the size is equal to the number of elements in array 1 and array 2. We have three iterators over here. Then what we are doing is simply looping around and checking if ARR of I, that is the first array, if that element, picking up the first element in the left array or in array 1 and picking up the first element in array 2 and checking them. If the one which is less will put up in the answer array, will, let's suppose this is our array. This is 5, 6, 8, and this is 1, 2, and 1. Let's put it this way. Let me just clear its screen and put a good example so that every case is followed. So let's put a 5 here, then put a 8, then put what, 10. This is our first array, and in our next array, let's put an array values as 4, then 6, then 9. Okay, done. So this is our first array, and this is our second array. So now what we are doing, we are first creating an array which is obviously of the same size, which is addition of this and this, which is 3 plus 3, 6, 0, 1, 2, 3, 4, and 5. 6 is the size. Now this is our answer array, and we have three iterators, one for this, one for this, and one for this, I, j, k. Now we're checking if I is less than n. Is I less than n? That is the length of this. Yes, it is 3, and I is currently at 0, n is 3. Is j less than 0? Yes, j is 0. Less than 3? Yes, I. Obviously, the size of this is again 3, so it is also less than 3. Then what we are doing, we are checking if this element is less than this element. No, 5 is not less than. So what we are doing, we are picking up the element and doing a post increment, right? So k, we are storing at this location and then incrementing the k. What we are storing is the element from array 2, which is 4. We are storing it over here, and then we are doing a post increment on j, so j will be here. Again, this condition is checked. We are still in the while loop because both of these conditions hold. If any one of these don't hold, we are out of this while loop. So now again we check, is 5 less than 6? Yes, it is. So I is incremented, 5 is stored here, k is incremented, done. So both of these are over here. Again we check, is 8 less than 6? No. J will be incremented and 6 will be inserted over here. I will remain as it is. Then again we check, is 8 less than 9? Yes, it is. So I is incremented, 8 is over here, k is incremented to this point. Okay, then what we are doing, so obviously it's a post increment. So first we store the value and then increment it. So I is over here and this is over here. So j is obviously 10 is not less than 9. So we go into the else part and we do a post increment. We store the 9 and then increment this j as well as this k. So k is over here. Now what is happening over here? This condition while loop is exhausted. We are out of this because now j is not less than m. 3 is not less than 3, right? So we are out of this while loop. And then what we are doing, we are just picking up the elements. Either it could be the left array, that is array 1, or it can be the right array, that is array 2. Any elements left, we are straight away picking them and dumping them in the answer array, because we know for sure that array 1 and array 2, both of these are sorted. So in our case, this array is exhausted. Obviously, we are at this location j, but this we are picking up the elements, only 10 is left. So once we are, oh, again we fall in the same bracket and we are always checking that condition where I is less than n. But this time around 3 is not less than 3, so we pick up the element, we increment our I, right, and increment our k. This time I is not less than n, so we are out of this while loop as well. Then finally what we are doing, we are printing out all the elements, that is 4, 5, 6, 8, 9, 10, which is obviously in sorted manner. Now, how does our main function looks like, our driver function? We are just declaring and initializing two arrays that are here, array1 and array2, then calling the merge function, and that's it. And also sending in the size, that is with the help of size of operator, that is the size of array1 and the size of array2. Now let's try to implement it in code blocks. So here you have your merge function, right? In this we have array1, array2, n and m, which are sizes, right? Then we have this array, the answer array. Then we have these three pointers over here, I, j, k. Then we have this while loop, which helps us in order to pick the elements either from the left or the right, depending upon which one is less. And we also have these two while loops, which helps us to pick up the elements from any one of the arrays. It can be either the array 1 or array 2. So once we are picking up the elements, so once we are exhausted with both these arrays, then what we are doing, we are just printing them over here. Okay, that so this is our merge function. So also we have this hash include studio.h header file, which helps us to use these printf and scanf statements if there are any. So we have this driver method over here, the main method, in which we are declaring and initializing our arrays in the same line, the static arrays, and then calling the merge function over here, in which we are sending array1, array2, then size of the array1 with the help of size of operator. We are calculating the size. Similarly, we are calculating the size of array2 with the help of size of operator. And once we are done with this thing, in the merge function, we are also printing it. We can either print it in the merge method, or we can create a separate method once they have been sorted on answer in, and we can call it pass in the answer array, and then we can print it. So now let's run this. So as you can see, we have this output array as 1, 4, 5, 6, 8, 9, 10, 15, 20, 40, 55, and 92, which is obviously sorted. So in this way, we implemented merge method for this particular problem. So in this particular problem, what we did, we implemented first the merge method, wherein we sorted the two arrays, and then we implemented the main method or the driver method, in which we just declared and initialized two arrays. Both of these arrays are sorted and then called the merge method.
Now let's try to compare quick sort with merge sort. So we know that in merge sort, every time we are reducing our problem into half, right? So we have first four elements, then we have two, then we have one, then we merge them. So every time we are splitting our array. That will not be the case in quick sort. In quick sort, we have one pivot element wherein that element is the element wherein the right, if we talk about the elements on the right side of the pivot and on the left side of the pivot, will be elements either smaller or either greater than. So we have that pivot element as the separator between the elements that are greater than and the elements that are less than. And the pivot will have its original position in the array every time, right? That is how quick sort operates. Now, if we talk about worst case scenario, we have already studied that in worst case time complexity, the time required by merge sort is n log n, which is not the case in quick sort. It will be n square. Now, merge obviously takes n amount of, or if you talk about big O notation, it takes order n space complexity. If you talk about consistency in terms of the size of the elements, it does not depend on whether your data sets are large or small. That means number of items. Wherein it will, if you talk about quick sort, it is faster than other sorting algorithms for small data sets like selection sort. In selection sort, if the data set is small, it will take a huge amount of time. Not huge, but comparatively, quick sort will be faster than selection sort in that case. If we talk about using extra memory or using the array that is there and inserting values in that same array, that is not the case in merge sort. We are using extra memory, that is, this is an outplace algorithm, and in this case it is an in-place algorithm because we are not using any extra space. If we talk about stability, quick merge sort is much more stable in terms of if we have 2 and 2, this 2 will always be in front of this 2. That is what is stability. That means if you have some order at the time of insertion, that order will be maintained, which is not the case in quick sort. So this is the comparison between quick and merge sort.
Now, let's go into the first topic of the agenda, which is what is heap sorting. So before starting heap sort, I must tell you that there are so many sorting algorithms which we can use, such as bubble sort, merge sort, quick sort, and one of them is heap sort algorithm. Now, what is the sole purpose of these sorting algorithms? We use these sorting algorithms to arrange a list of elements in ascending order or descending order. So if you have a list of elements which is jumbled up, it is not in sorted order, these sorting algorithms will make sure that your list of elements will be sorted. It can be either in ascending order or in descending order. Now, this heap sort algorithm uses one of the tree concepts, which is heap tree. Now, tree concepts, when I say, I mean that it's a hierarchical tree concept. Now, if you look at the diagram given below, you can see that it's a tree concept. Now, there are a list of elements which I have taken here, which is 7, 15, 6, 8, and 4. And I have arranged it in a heap tree concept. So if you can see, 7 is the parent node. So we call that as a node, and 7 is the parent node. From 7, it is getting divided into two child nodes, which is 15 and 6. So we can say that 15 and 6 is the child node of 7. If you look into 15, 15 is a child node of 7, but it is also a parent node for 8 and 4, right? So we can say that 8 and 4 are the child nodes for 15, which is also a child node of 7, right? Okay. So this concept is called as heap tree concept. Now let's look into the third point, which is very, very important. So heap tree can be of two types. One is minimum heap and other is maximum heap, which is also known as min heap and max heap. Now what happens in max heap? Max heap is used to arrange a list of elements in ascending order. That means you can see in the heap tree which I have given here, it's all jumbled up. 15 is kept somewhere in the middle and 8 is kept in the last. There is no order here, right? Now when you do a max heap, there will be a particular order which is ascending order. So all the numbers in the heap tree has to be designed and kept according to the ascending order. While in minimum heap, what happens? It is used to arrange a list of elements in descending order. So just the opposite of what you will do in max heap, you will do it in min heap. So you have to start from the biggest number and you have to go down. Something like this. So if I talk about min heap and if I create a heap tree of the list of elements, for example, if I take these numbers, it will be something like this. Here it will come as 15, then it will come 8, 7, 6 and 4. That is what is descending, right? And the opposite of this, which will be ascending order, will be a max heap. We will discuss max heap more in detail in the next topics, because in heap sort algorithm topic, we will be covering how to convert a heap into a max heap, which we'll see in the next topic in our agenda. Now let's see the next topic in our agenda, which is step-by-step execution of heap sort algorithm. So what are the steps which we need to take to complete this sorting algorithm? Now, before starting the step 1, I must tell you that these steps are really very important for you for the whole video. Okay. So when I'm reading step 1, step 2, step 3, please keep memorizing that what are these steps. It will be really helpful for you to understand the whole video if you understand these 5 steps. Well, I will be explaining using an example and a diagram, but make sure that you remember these steps. Let's start with the step 1, which is we first build the heap using the given elements. That means we will be provided with some 5 elements or 6 elements, and we have to create a heap tree out of it. Numbers can be kept anywhere, that's not a problem. So if I have a list of elements, I have to build the heap. That's it. That is step 1. What is the next step? Once you create the heap, you have to convert it into a max heap. Now, if you remember, in the previous topic, I told you that max heap will be used in heap sort algorithm, and max heap always follow ascending order. That means the heap which we will create, we have to convert it into a max heap which will have the elements in ascending order. We will see how we can convert this, and I'll tell you the steps for that also. Once you converted your build heap into a max heap, next what? Let's see the step 3. Once the sorted max heap is created, we swap the root node with the last node. That means root node is a parent node. The parent node will always be swapped with the last node, the extreme last node. No matter what the element is there, it has to be swapped. Now when it is swapped, the last element you need to delete it. That's what it's written here, and delete the last node from the heap. So that means you have to delete the last node from the heap. So you will be left with n minus 1 elements. Okay. Now some of you must not have understood this, but in the later topics, when I'm taking one example, I'll be telling you what is this step 3 and how to do it. So stick to the video till the end. Now, step 4, we have to repeat this process of swapping the parent node with the last node till you get only one element left. That means till the heap gets empty. Once the heap gets empty, you will get your sorted list. And then you can display your sorted list. So this is what is the 5 steps of heap sort algorithm. Now, before moving into the next topic or before moving into the demonstration, I must tell you one thing. If you look into the step 3, it says once the sorted max heap is created, right? When you are creating a max heap, you need to focus on one thing. That one thing is that your parent element should always be greater than your child elements, or it can be equal, but your parent element should always be greater than or equal to the child nodes. So now let's move into the next topic, which is the demonstration. And here you guys need to focus a bit more, because now is the time when I will be taking one example and I'll be demonstrating how this sorting algorithm works. So remember the 2 steps which I told you. So let's revise those steps. Step 1 is we first build the heap using the given elements. And we then create a max heap to sort the elements in ascending order. So let's first see what are the elements are we getting. So these are the elements which I'll be taking for an example. So the elements are 7, 15, 6, 8 and 4. And as you can see, these are unsorted, and we have to use the heap sorting algorithm to make it sorted, right? So that's why I've written consider the following list of unsorted numbers which are to be sorted using heap sort. Okay, now let's build the heap. So if you can see, randomly I have just created the heap tree, which is something like 7, 15, 6, 8 and 4. And the numbers I have written down below. The step 2 was that I have to create a max heap out of it. So let's transform it into a max heap. When I do that, it looks something like this. Remember the point which I told you. I told you that when you create a build heap into a max heap, you have to make sure that parent node should always be greater than the child nodes. If you can see, 15 is a parent node which is greater than 7 and 6, which are their child nodes. So it's perfect. But when you look upon 7, 7 is a parent node for 8 and 4. And 8 is greater than 7, right? So don't you think we need to make this max heap more accurate? Yes, we have to make this max heap more accurate, right? So right now my max if contains this. Now I think we need to swap this 8 with 7 because parent node should always be greater than the child node, right? Now if you look into step 3, we will do that swapping again, but first let's see what is a step 3 so that you don't forget what are the steps. Step 3 says once the sorted max if is created, remember till now you have not created the sorted max if. There is an error, right? A slight error is there. We swap the root node with the last node and delete the last node from the heap. So once I will do all those swapping and all, once the max if is created, we have to swap the parent node with the last node and the last node should be deleted. And we have to repeat this same process until you get only one element in your heap, right? Let's quickly do this. So remember I told you that in max if parent node is always greater than or equal to child nodes. Now see, I have swapped this 8 with 7. Now can you tell me if everything is in order and it's a perfect max if? Yes, we can say that it's a perfect max if because all my parent nodes are greater than the child nodes. So what is the step 3 now? So once you have created the max if, we have to swap the parent node with the last node. Last node is 4 and parent node is 15. Should we swap it? So when you will swap it, you will get something like this, right? Now after swapping, you are getting something like this. Now what we have to do? A step was that we need to remove the last node, right? So we should remove the last node and 15 is gone. What is the meaning of that this last node is gone? That means 15 is sorted and it is kept at the last. So 15 now we don't have to work upon because already 15 is the most highest in this list of elements, right? That's why I have marked it as red in color. Okay, I hope till here there is no doubts. Now let's move. Before moving into the next slides, let's see what are the numbers we are getting here and is it a max if? So if you look here, 4 is a parent node. Is the parent node greater than the child? No, right? 8 is and 6 is much more greater than 4. Don't you think we need to swap these? Okay, before that, let's see what is here. 8 is the parent node and 7 is the child node. And this looks perfect, right? Because 8 is greater than 7. Let's move and let's see what we will do. Max if parent node is always greater than or equal to child nodes. So we have swapped the 4 and the 8. 4 was here and 8 was here. We have swapped it so that 8 comes to the parent node. Now still, is it a perfect max if? I don't think so because 4 is again a parent node and it is much more smaller than 7. Don't you think we need to swap this also to make it a perfect max if? Let's do that. So you can see now we have swapped it and now it's a perfect max if because 8 is greater than 7 and 6. 7 is greater than 4. And that's what I'm always repeating. Parent node is always greater than or equal to child nodes. Now what we should do? We have to swap the parent node with the last node. So let's do that. We have to swap the first and the last node and delete the last node from the heap. 8 was here and 4 was at the last. We have swapped it. Now that we have swapped it, we have to remove the node. Which node? The last node. So we have removed the 8. Once you do that, you are left with 4, 7 and 6. And 8 is removed. That means it is sorted. So I've marked it in red in color. 8 and 15 is sorted. Now we have to only work with 4, 7 and 6. What next? Obviously, we have to repeat this same process, right? So you can see that it is not a max heap again. We need to convert this into max heap. Now you guys must be knowing what should be the next step. I don't have to tell that, right? So parent node is always greater than or equal to child node. So we have to swap that. 4 and 7 is swapped. Now is it a perfect max heap? Yes, you are right. It is a perfect max heap. You can see 7, 4 and 6. 7 is the parent node which is greater than 4 and 6. What next? Yes. So see, the steps when you cover it or when you know that what are the steps, you generally figuring out on your own what are the next steps and how we can sort it, how we can go with the algorithm, right? And that is why writing the algorithms or writing the steps are very much needed. Correct? Let's do this and complete this particular algorithm. Let's see what is the sorted output we'll get. Okay, so we have to swap the parent node with the last node and we have to delete the last node. Let's do that. So I have swapped the parent node with the last node, which is 7 and 6. It is swapped and we need to remove this 7. So we will remove that 7 node. It's gone. And we are getting the sorted one, the half sorted list, which is 7, 8 and 15. 7, 8 and 15 is already sorted now. We are left with 6 and 4. Looking into this one, do you think it's already a max heap? Yes, it is already a max heap. So what we have to do? Yes, we have to swap the parent node with the last node. So it's very simple. We have to just swap it. Once you swap it, you have to delete the last node, which is 6. You are now left with only one node, which is 4. That means we are now in the end of this sorting algorithm and we can display our sorted list, which is 4, 6, 7, 8 and 15. Now this was a very easy and simple demonstration of heap sort algorithm. Let's see what are the algorithms we have to check when we are writing a program in C language. Now, when we talk about the actual algorithm, we actually talk about the real-time code which we'll be using in our programming language or in the program so that it becomes easy for us to write the program. So before seeing the actual program or the actual implementation, let's first see what we can actually come up with an idea to solve this heap sort algorithm. So what we need is, we need two methods here. One is heapify and the next one I'll discuss after this. So let's first see what is this heapify method and what we have to do here. So basically what we need to do here is, we need to make sure that my program, whatever I will write, it should be knowing automatically that which one is parent node and what is its child node. So we have to use a basic formula to do this. And if you can see, I have written a question here, how to find the left and the right child of a parent node. So suppose if the parent node is 7, what logic I can write so that my system knows that 15 and 6 is its child node. How can we do that? Let's see what formula I have written and let's discuss this. So if you look here, it's written left child of 7. For finding the left child of 7, which is having the index 0, right? When you write it in an array, this list of elements, obviously the 0 index element will be 7. If anybody who doesn't know what is index, basically when you write an array of elements, we represent it by the index items. So index numbers. So if you say 0, 0 is the first list of element. The first element. When you write 1, it's the second one. When you write second index, it's the third element. When you write third index, it's the fourth element. And when you write fourth index, it's the fifth element. So that's why left child of 7. 7 is the index 0. So I have come up with this particular formula, which you can see. 2 into 0 plus 1. That means 2 into, let's say I is the index. So I plus 1, right? If I say 2 into I plus 1, 2 into 0 plus 1 will give you how much? It will give you 1, right? Because 2 into 0 is 0 plus 1 will give you 1. What is the element in 1 index? 15. Are we getting the left child of 7? Yes, we are getting the left child of 7. If I have to find the right child of 7, what logic we can use? We can use the same logic. We just have to mention here plus 2 rather than writing plus 1. When we do that, what will happen? 2 into 0, 0, 0 plus 2, 2. Element in second index. What is the element in second index? Second index, not second element, right? Second index I have 6, and that is what I am getting here. So we have come up with two formulas. How can we find the left child of my parent element and the right child of my parent element, right? In this particular method, which is Heapify method, we will be using this concept when we will come to the topic of implementation. So remember this concept. Okay. Now let's see what is the another method which I was talking about. I've just given a similar example of left child of 15 and right child of 15. So if you can see, left child of 15 is 8 and the right child of 15 is 4. How we have done that? The 15 index is what? 1. So I've just, in that formula where I was 0 in the previous example, I have just taken 1, and 2 into 1 plus 1 gives you 3. What is the element in third index? 8. And 2 into 1 plus 2, which is 4. What is the element in fourth index? 4. That's how this formula works to find the child of the parent node. Okay, let's quickly see the another method, which is heap sort. This is the method which we will use to basically complete the two steps, which is step 3 and step 4. Now, I hope the people who are concentrating in this particular video, they must be remembering the step 3 and step 4, right? Step 3 was, once the max heap is created, the sorted max heap is created, we have to swap the first node, that means the parent node, with the last node, and we have to delete the last node, right? That's what we are going to do here in this code. I'll explain you this now. So if you see here, for I is equals to n minus 1, right? N minus 1 means what? N is the size of the list. Size of the list is 5 in my example. So 5 minus 1 will give you 4, right? I is 4. 4 is greater than equal to 0. What does that mean? That means it is asking, is that condition true or false? 4 is greater than 0, that is true. So it will come down. What is there in ARR 0? That means the parent node, isn't it? Always the 0 index will be the parent node, right? And ARR I is what? 4 here, right? And that's our last node. So we are swapping that here. Can you see? Swap is a method inside which we will write the 3 steps for swapping something. I hope while you are learning C programming language, swapping is the very first thing or very first program which you have worked upon. And you guys must be knowing how we use temporary variable to swap two items, right? If you don't know, then stick to this video. In the next topic, I have written the code and I have explained you how we can swap the two items. Meanwhile, just understand that here we are calling the swap method so that these two items can be swapped and removed. I mean removal of the last node, right? Okay, so I hope this particular code you have understood. This is the step 3, which is this for loop. And if you see, you must have figured out that I skipped this part, which is the first for loop. Why I skipped this part? Because it is calling the Heapify method. We have already seen how this Heapify method works. That's why I skipped this and moved to the next for loop. Okay, so let's see what all things we have seen here. We have seen this for loop, which is calling the heapify method. Inside the heapify method, what we are doing? We are writing an algorithm to find the left child and the right child of our parent node. And in the next for loop, what I am doing, I am swapping the first node, which is the parent node, with the last node, and I'm removing that last node, right? And the last, you can see why I'm calling the heapify. Heapify root element to get highest element at root again. Remember one point which I told you while I was demonstrating, that when you are creating a max heap, remember always that parent node should always be greater than the child nodes. So if you want to make sure that parent node is greater than the child nodes, you have to call this heapify method, which is arr, I, 0, to do that heapify thing again and again, so that always your parent element will be the highest one. That is why we will write this and we will call this method heapify. Now, because it is an algorithm, it is kind of half of understanding of heap sort algorithm, that how we can write a program. But now in the next topic, we are going to see how we can actually write a code and what is happening inside that code. How are the numbers moving from here and there, and how this build heap is converting into max heap and all the other steps. So let's quickly see the implementation of C programming language for heap sort algorithm. You must be knowing that whenever you start writing a C programming language, we start with the main method, because that is the heart and soul of the program. So let's see what all things we are writing in main method and what are the methods which we are calling from here. So if you can see in the main method, I have written an array, obviously, which is very, very important, because you need to have the unsorted elements, which you need to write it in an array format. So I am taking the same example, which is 7, 15, 6, 8 and 4. Now what is this n variable doing here? N variable is nothing but taking the size of the array divided by the size of the 0th index of the array. Now this is not even important to write, because in the n, basically I want the length of the array. My length of the array is 5. So remember always that n will be 5 in the whole program. So if you already know the elements, you can directly write n equal to 5. But if you want to mention it in a formula basis, you can write size of arr, which will obviously come at as 5. If anybody who is very new to C programming language, int is nothing but the data type. So the array is containing only integers. That is why I'm writing here int. N is a variable which is also containing only the integer, which is 5. So that's why I'm writing here int. And if you have any question regarding this main method, why is int written here? So we can write void also, but void is no return data type. That means when you write void, it doesn't return anything. But when you write int or float or any other data type, it should return something. So it all depends on you. If you want to write void, you can write here. There's no problem. Now, let's see what are the methods which I'm calling. And once I'm calling that method, we will directly jump to that method and we will see what is happening there. So in this particular video, please stick and please analyze how step by step these programs are running. Okay, let's start. So we are calling one method which is heap sort, and it is having two parameters, which is an array and a n variable, which is here. So let's jump to this heap sort method. Okay, and let's see what all things is written inside that heap sort method and analyze that. And after those all things, we will come back to this particular slide and we will see what is this printf and print array method. Cool. Okay. Now, if we go to the heap sort method, ARR is the array. That means this all 5 elements is coming inside this ARR parameter. And inside n, obviously 5 will come. So let's move to this heap sort array. Now if you can see, this is the heap sort array and the whole program is written. Do you remember in the algorithm also I showed you the same kind of algorithm where we were calling the heapify in the first for loop. In the second for loop we were swapping the parent node with the last node, and at last we were doing heapify again with the 0th element, because we want that parent node should always be greater than the child nodes. The same thing I've written here, but in a very deep manner. Let's understand how each of the for loop is working. Okay, so remember when we were calling the heap sort, 2 things were coming. One was the array and one was the size of the array. So here all the array elements will come, and in this particular parameter not all the, so basically the n, which is the 5, will come, right? Now let's first see what is this first for loop. We will understand this for loop. Once we will understand completely what is this, we will again come back and we will see this for loop. Then we will understand this one. Again we will come back and we will see this heapify. Right? Let's quickly see this particular portion. So this particular portion, what is happening? A for loop is there in which is written I equal to n by 2 minus 1. Right? Let's see what is happening here. So remember, this is my unsorted list, right? Now, if I imagine that n is 5, right? So 5 by 2 will always give me 2.5, right? And 2.5 is approx to 2. Why I'm approximating it? Because my I is an integer. I can't take a decimal value, which is 2.5. So I'm approximating it, converting into an integer and taking it as 2. Now to that 2, I have to subtract 1. So how much is left? 1. That means I value is 1, right? Now, what is in the condition of for loop? It's written 1 is greater than equal to 0, which is basically true, right? Now, once it is true, what do we mean by that? We mean that loop will run from 1 to 0. First, this condition will be true. It will go and call heapify method. So that means it will call heapify ARR, 5, 1. Once that heapify completion of the code happens, it will come back to this for loop. It will decrease the I value to 0. And again, it will call the heapify method with the value ARR 5, 0. Right? So that is why I'm saying that loop will run 2 times. Once when the I value is 1 and once when the I value is 0. So don't worry, we are going to see both the looping thing. We are going to loop it 2 times and we will see in a very detailed manner what is happening when it is calling the heapify when I is 1 and what is happening when it is calling the heapify method when it is 0. Okay, let's quickly go and see what happens when I value is 1 and it is calling the heapify method. Heapify method looks something like this. And I hope you must be remembering that in the algorithm, I told you how to find the left child and the right child of a parent node, right? That's what is the formula I have written here. Can you see this? Guys, don't look at the whole code. You will get disturbed because it is much of codes are written here. Don't look at that. Just look at the 3 lines which I have bolded enough, which is this part, right? And why I have written this formula? Because I want to know that what is the left child and the right child of the parent node. Okay, let's do it very slowly and precisely. Let's not quick it off, right? So let's understand only this portion first. Okay, we will see the rest of the code after this. So let's see what is written here. I hope you remember that we are first taking I equal to 1, right? So when we are taking I equal to 1, does that mean this largest equal to I means largest value will become 1? Yes, it will become 1. Let's put the formula and put the values inside the formulas. So left equal to 2 into I plus 1. Left equal to 2 into I plus 1 will give you 2 into 1 plus 1, which is 2 into 2 will be 2, 2 plus 1 will be 3. So left is 3. Left is 3, okay? Now, tell me one thing. When my I is 1, which is the one index in this array, in this list of element? 15, right? One index is what? This is 0, this is 1. So 1 is 15. Largest equal to 1. That means largest becomes 15 for now. Largest is 15. For left, what is the number I'm getting? 3. So let's go to the third index. 0, 1, 2, 3, which is 8. Now if I look in the diagram, am I getting the left child of the largest node, which is 15? Yes, that means my formula is working fine. What about the right one? For the right one, I'm getting the index as 4. 0, 1, 2, 3, 4. For fourth index, the value is 4 itself. That means 4 is the right child of the 15 largest node. Yes, it is. That means my right formula is also working, right? So now my system knows that which is the left node and right node, I mean left child node and right child node of this parent, right? Because see, computer does not understand this heap tree, right? We can see the heap tree because we are designing it, but computer can't design it, right? So we have to tell the computer that, you have to figure out a way. I'll help you with that. I will write a formula and you have to figure out what is the left child node and the right child node of the parent. So now we know that this particular formula is working and we got the left and right. Remember, we are using the heapify method with the value I1. Still, we are left to do the I equal to 0. Remember that and keep it in mind. I don't want you to forget that. Okay, so this is done. Let's see the rest of the code, what was there. Till here we have done. There is a 3 if conditions and we need to check all the if conditions, which one is correct and which one is wrong. So let's work on that. Now, I have just kept this list of elements and the heap tree in place so that you can always refer to this and analyze how the indexing is done and how the swapping is happening. Okay, so for your understanding, I have kept it here. So should we start doing this if thing? So let's complete this if conditional statements. What is written in the first if conditional statement? It's written left is less than n. What is the left value which I got? I think I got 3, right? 3 is less than n is 5, right? The size of the array. I hope you must be remembering that. So 3 is less than 5 and ARR left. That means what is the value inside the third index? Third index, the element is 8. So it will be 8. What is the element inside the largest? Largest was 1, right? What is the value inside 1? 15. So I've kept it there. Now let's see which condition is true and how this AND operator is working. If anybody who doesn't know what is AND operator says that when both the conditions are true, that is the only time when your whole condition will be true. So both the conditions has to be true when you're using an AND operator. But we can see here that 3 is less than 5, which is true, but 8 is greater than 15, it is false. So what does it results in? It results in false. That means, can you see this statement, largest equal to left? It will never work. That means it will never work. That means we have to ignore this sentence. Just ignore it because my condition is only wrong, right? Should we go to the next if? Please don't get confused here. It's not written else if. It's written if. If it would have been written else if, then we do not have to go to this if because it's saying otherwise or it's saying else you do that. But right now it is not saying else, right? So we have to go with this if condition. Let's see what is here happening. Right value was 4, if you remember, and n is 5. Then ARR right, what is the fourth value? Fourth index was 4th, right? So 4 is greater than ARR largest. ARR largest was 15, which is one index. ARR 1 is 15. I got 15. There is same AND operator used here. So let's quickly solve this. 4 is less than 5, true. But 4 is greater than 15. Again, it is a false statement. And AND operator says that when both the conditions are true, then only your result will be true. But as you can see, one of the condition is false. The if statement is also false. That means you have to ignore this particular line also, right? But still there is a chance because we have one more if. Let's see what is that. Largest not equal to I. Largest value was 1. I value was also 1. 1 is not equal to 1. That is wrong because 1 is equal to 1. So these two lines, again, we need to skip it. I hope you understood these all things. So that means, what does it mean? It is just saying that, you know what? Your max heap is sorted here. You do not have to swap any item. You can see that 15, 8 and 4, it is a perfect max heap. 15 is greater than 8 and 4. You do not have to swap anything. That is why all the conditions came wrong. That is what we are doing here basically, these all things, right? So for 15, which is index 1, is sorted. But remember, we have one more heapify. Yes, so we have just completed this heapify, ARR 5.1. Now we have to go and take a look upon what will happen when I'll go to heapify ARR 5.0, right? Let's quickly go to the heapify and let's see what happens when I give the I value as 0, right? So I have come back to this particular program again. And if you can see, I have this particular 3 lines. Yes, we need to do that because I value got changed, right? I is 0 now. That means largest is 0 now, right? Largest is 0. Let's do this. So this is the arrangement which I have got. For your reference, I have got it here so that you don't forget that what we have done till now. And if you can see, largest will be 0. That means 0th index. What is there in 0th index? 7. So largest is 7 now. Now you must have understood that this is wrong. 15 should come here, right? 7 should come here and 6 should come here, right? That means here, those 3 if conditions, some of the if condition should come correct. Then only we can decide and swap these 2 elements. Okay, before going to those things, let's understand one by one. I equal to 0, largest will become 0. And if you look into the left and right, let's find it. Left equal to 2 into I plus 1, 2 into 0 plus 1, which will come 1. So let's check whether I'm getting the correct one or not. Left will be 1 index. If I go to 1 index, what is there? 15. Is my 15 the left child node of parent? Yes, it is. If I find the right formula, 2 into I plus 2, 2 into 0 plus 2. 2 into 0 will give you 0. 0 plus 2 will give you 2. Right? Now, what is the second index? 0, 1, 2. In the second index, I'm getting the value 6. Right? So, whether it is my right-hand side child of the parent, yes, it is. So, it's working fine. Now, keep it in mind 3 things. I value is 0, largest value is 0, left value is 1, and right value is 2. And let's see the if conditions, how we can fit it here and how it will work. Fine. Left was 1. 1 is less than 5. ARR left, that means ARR 1, which is what? 15. is greater than ARR largest, which is what? 0. ARR 0 is what? 7. 15 is greater than 7. Same AND operator, that means I'm again repeating, if both the conditions are true, then the result will be true. So 1 is less than 5 is true, 15 is greater than 7, perfect, it is also true. That means my condition is correct, it's true. When it is correct, what will happen? Largest equal to left, that means largest will become 1, right? Largest becomes 1 now. Remember, now largest is not 0. Now largest is 1. And if you see, what is there in 1? 15. Right? Okay. Now let's quickly go to this next if condition and let's see whether this is also correct or not. Right value was 2, right? If you remember. So 2 less than 5. ARR 2 is what? 6. And ARR largest. Remember, now the largest value has got changed to 1. So we have to see ARR 1. What is ARR 1? ARR 1 is 15. So we have to write here 15. Okay, my bad. Here 15 will come. Okay, here the 0 will not come. We have to change this ARR. It will be 1 and it will be 15. I'm so sorry. So here there is some mistake. So it will be 6 is greater than 15, which is false. 2 is less than 5, which is true. So true and false will give you false because both the conditions are not true. That means we need to ignore this statement. Now the main part here is, are you understanding what is happening? We are just telling the computer that computer, you have to understand that you have to only swap these two elements. That means the parent with the left child, because right child is in the current position. It is in the correct position. It is less than the parent node. So it is in the correct position. We don't have to even touch the right child. And that is why this condition came as wrong. Because we don't have to do anything with the right hand side part. Correct? I hope you are understanding. Now, let's move to the next if condition. What is happening? Largest is not equal to I. Okay, largest, what was the value? 1. 1 is not equal to I. I is nothing but 0. Right? So, yes, it is not equal. That means that's true. So, we have to come down to this swap method. Right? Let's see what is happening in this swap method. Okay, I have just explained that this is true. So, swap method we have to come in. Swap method, what is written? AND operator is an ampersand because in C language, we use the concept of address and pointer. So whenever you are swapping, you are basically using the pointers, okay, which will hold the address of that particular location. If you don't know the concept of pointers, then please revise it and then come back. So if you can see, pointers will be using here, and that is why I've written ampersand. Ampersand will take the address of this location. Let's first analyze what is this ARR I. Remember I was 0. So ARR 0. ARR 0 is what? 7. ARR largest. ARR largest means ARR 1. What is that? 15. Swap those two things. So it will swap those two things means 15 will come here, 7 will come here. Perfect. And it will become a max heap. Right? Let's see how this swapping is happening, because I told you that I will be explaining how we are swapping two elements. So let's do that. I'm just writing here that ARR 0 and ARR 1 is the numbers which we are taking and going to the swap method. Let's go to the swap method. This is how I've written the swap method. And if you can see, I've used the pointer. Pointer is always denoted by the star, which is also called as asterisk. So here comes the value ARR 0, which is 7, and here comes the value ARR largest, which is 15, right? 7 and 15. Remember, why are we putting the pointers? Because we want to swap the value using the address of those locations. Okay. In C, this is how you do it, because it is called as call by reference. That means call by address. So we do this. Now, some of you who must be knowing C programming language, I know you are connecting to me. Okay, now let's see how this swapping is happening. So if you see, this was the number 715, 684. When we do this formula, which is temp equal to A, temp will have the value 7 because A was 7. A equal to B means A will become 15 because B was 15, right? And then B equal to temp because temp was 7, B becomes 7. And thus, A becomes 15 and B becomes 7. Swapping is done. Now, one thing to notice here, that don't get confused why we are using temporary variable. See, we are using temporary variable because without temporary variable, it's very difficult to swap two things. Because if you are thinking that you can swap like this, A value give it to B, B value give it to A, it won't work. Because when you give A value to B, B value is gone. Then what you will swap from B value to A? Because B value is already done, right? It's gone. So that is why to save that value in a temporary variable, we use the temp, right? Once this swapping is done, you will get this array, which is 15, 7, 6, 8, 4. Now this looks a perfect max heap because here all the parent nodes are greater than the child nodes. 15 is greater than 7 and 6. Now look here, 7 is again an error coming here. That means we need to again do the heapify thing. And it will, because there's a for loop, right? Okay, let's come back. If you can see here, we completed this swap, right? We completed this swap. Now if you can see, we have left one program, one line of code, which is calling of heapify method with ARR 5 and the largest, which is 1. Imagine that if it goes again to the heapify method, then what will happen? It will again take the largest as 1 and it will again check whether the left right child is there or not, and again it will check the if conditions, and there it will find that the 7 and 8 was not sorted. It will sort it and then again it will bring up the perfect max heap. So this is how this whole program is working again and again, right? So I hope you understood this part. Now we have covered this portion of the heap sort method, right? We are left with the next thing, which is nothing but the for loop, in which what we are doing, we are solving the step 3 and step 4. I hope you remember. The step 3 was, once you create the max heap, you have to swap the parent node with the last node and delete that last node, right? Let's see how we can do that. So this is the code which we are going to look upon now. And remember, we sorted the array. So it will come something like this when it becomes a perfect max heap, okay? Now, once the sorted max heap is created, we swap the root node with the last node and delete the last node from the heap. Repeat the same until max heap becomes empty. So what we gonna do? I equal to 5 minus 1, which is 4. 4 is greater than equal to 0, which is true. Swap ARR 0, that means ARR 0 is 15. ARR I, which is ARR 4, which is 4. Swap it. 4 will come here, 15 will come here, 15 is sorted, make it red, right? I hope you are connecting with me. Now, we don't have to write again the same logic for swap because we have already seen, right, how the swapping happens using the temp variable and using the pointers. So let's see what is next. These all things are done. We have created the perfect max heap. We have swapped the parent node with the last node, and we have removed the last node, and we got the sorted. This will keep happening again and again till you get the sorted list of numbers. Now, if we come back to this main method, I told you that these all things are happening inside this heap sort method, but we are left with printing it, right? So we are printing sorted array with a /n, which is nothing but a new line, So if you know C language, you must be knowing what is /n. And then we are calling this last method, which is print array arr comma n. Print array is a method which is taking the array with the n value, which is the 5, right? So now let's see what is going to happen when we print this. This is very easy. In the print array method, one code will be written in which you will be printing all the stuffs, right? All this sorted array. Now, because this is very easy, we will see at the last. Let's first revise what all things we have seen and what is the flow of the program, okay? So first we started with this heap sort, right? The heap sort takes us to this heap sort method, and then we have looked upon this heapify method. In the heapify method, we have seen a lot of coding. The first code we saw that how we are finding actually we are helping the system to find the left child node and the right child node of the parent. Then we have 3 conditions of if, and we are checking which one is largest, which one is smallest, and if it is the smallest, then we are swapping it. Everything is happening here. How to swap, we saw that using this particular technique, which is using the pointer, using the address, and using the temporary variable. After swapping, we again came back to this heapify method, and we saw that how can we continuously creating the max heap so that a perfect max heap can be created and sorted, right? After that, we again came back to that heap sort, because once this for loop is completed, we have to come to the step 3 and step 4, which is we need to swap the parent node with the last node, and we need to delete that last node, right? One thing to notice here, actually in writing a program, we don't delete the last node. It is just kept untouchable. So we are not touching that particular sorted list or element because it is sorted. We don't want to touch it. So when I say that we are deleting, when you're writing a program, it's not getting deleted. It is just sorted, untouchable. We don't have to do anything with that 15 or any of that number. Okay. So we saw how to swap this parent node and the last node, and how to make the last node untouchable, right, while writing the program. And after that, we are coming into this print array, which is the method, print array method. And we have seen how to print this particular sorted array. It's a very easy thing. You are using a for loop and you are calling that one by one. So all the elements are getting printed one by one. This is the sorted element which I am getting. I hope there is no doubt, and I have clearly and very easily explained all the codes one by one technically, that how and from where the code is going, how the calling of method is happening. If the calling of method is happening, then how the values are getting swapped, how the values are getting conditionally true, and what are the if conditions, how those things are working. Now that we have understood how this heap sorting algorithm is done, what is the technique, and I have also demonstrated using an example and a diagram how this heap sorting algorithm works, creating a max heap, build heap, right? Let's discuss what is the time complexity and space complexity for this particular algorithm. Now, if you can see, in the worst case, what are we doing in every iteration? We are transforming it into a max heap, right? That's what at the final we are doing. Hence, this will perform log n operations, right? Because every time we are converting it into a max heap, right? So it will perform log n operations, and this has to be done for n iteration, resulting in n log n operations in total. So in the worst case, it will be n log n. Okay, that will be the time complexity in the worst case. Now let's see in the best case what will happen. In the best case, it is already a sorted array, right? We can do some modifications by using flag to check whether the element is already sorted or not. So suppose the element which you are getting is kind of sorted, only one particular element you need to shift, or you need to shift those elements. So in the best case, again, it's already sorted or not sorted. We are not complexing it, right? Or we are not spending much time in that. we will just create it into a max heap and sort it. That's why the best case will also be n log n. That is why the best case time complexity will be O(n), which is big O of n log n. Average will be also big O of n log n, and worst case will also be big O n log n. That is the reason many real life applications or many real life developers are creating applications using heap sort algorithm. Let's quickly discuss the space complexity, which is only big O of one additional space is required because the heap is built inside the array to be sorted. Remember that whatever sorting we are doing, we are not using any other memories, right? In that memory itself, everything is happening because we are converting my elements into a heap tree, correct? Shifting of elements from one location to another is not at all happening. Every sorting thing or every sorting shift is happening inside the same heap memory, right? That is why not even a single additional space is required because the heap is built inside the array which is to be sorted. Second point, data in an array can be rearranged into a heap in place, right? Data can be rearranged here and there in the same array, right? Hence, the space complexity is big O of 1, right? Okay, so we are coming into the end of this session. I hope you understood how this heap sorting algorithm works and how this particular demonstrating of heap sort algorithm, implementation, algorithm, and all of these things are happening. I hope you found it very easy, and I hope you will use heap sort algorithm in your further developments, and all the best. We'll meet you soon.
Now let's try to understand what are the things that we covered in this tutorial. We talked about what is data structure and different types of data structure. We talked about arrays and its implementation. We talked about linked lists and different types of operation and different types of linked lists that we have. We also talked about stack and its implementation using arrays as well as linked list. We also talked about some of the common operations like push, pop, is empty, and full. We also talked about queues and its implementation, both with arrays as well as linked list. We also talked about some of the common operations like enqueue, dequeue, get rear, get front. We also talked about trees, and wherein we covered binary tree and binary search tree. We covered linear search and binary search algorithms. We covered sorting algorithms like bubble, insertion, merge, and heap sort. Thank you. I want to introduce you to Great Learning Academy, a free initiative by Great Learning where you can access 200 plus courses with 1000 plus hours of free content on trending high demand domains such as data science, machine learning, AI, programming, cloud computing, digital marketing, DevOps, management, and many more absolutely free. Award-winning academicians and leading industry experts design these courses. You can get a free certificate of completion when you enroll and complete these free courses. You can also get access to presentations, code notebooks, datasets, and quiz. We have courses in English and Hindi to give you the best learning experience in language you are comfortable with. Check out the description of this video to access the relevant courses on Great Learning Academy. So what are you waiting for? Register now and start your learning journey today. If you haven't subscribed to our channel yet, I want to request you to hit the subscribe button and turn on the notification bell so that you don't miss out on any new updates on video releases from Great Learning. If you enjoyed this video, show us some love and like this video. Knowledge increases by sharing, so make sure you share this video with your friends and colleagues. Make sure to comment on this video any queries or suggestions, and I will respond to your comments.